and they already have their slides on the web page. So I encourage you to look at the slides and think of questions to ask them during the last discussion session. I'd also like to announce that there'll be a questionnaire that we'll put online tomorrow, so people after the meeting finishes can give us some feedback about the meeting, which will of course be useful for the planning of next year's meeting in Vienna. Okay, so we're ready to start the next session. So Sean Hartnell will be the chair of this session.
Hello, so we have two talks this morning, and the first one is by Shu-Heng Shao. As usual, raise hands or write in the chat any questions, but we'll get to them after the talk. Okay, so Shu-Heng is talking about symmetries and their generalizations in topological phases of matter. And please go ahead, Shu-Heng.
All right, thank you. Okay, first I would like to thank the organizers for putting together this wonderful and extremely interactive conference during such a difficult time, and for giving me the opportunity to speak here. As Sean already said, I'm going to review symmetries and their generalizations in topological phases of matter. Global symmetry is one of the few universally applicable tools in analyzing strongly coupled quantum systems. Global symmetry can have 't Hooft anomalies, and these are obstructions to gauging the global symmetry. Even though the English word anomaly usually means something not normal or perhaps even sick, a global symmetry with 't Hooft anomaly is perfectly healthy. Both the global symmetry and the underlying quantum system are perfectly well defined. You will only run into troubles when you attempt to gauge this global symmetry. In recent years, the notion of global symmetry has been generalized in several different directions, and this has led to new constraints on renormalization group flows, new organizing principles of topological phases, and new dualities. This has applications in high-energy physics, condensed matter physics, and mathematics. In the talk today, I will review three particular generalizations of the ordinary global symmetries. The first one is the higher form global symmetry, which by now has become relatively standard. The second one is the subsystem global symmetry, which has featured a lot in various lattice models in condensed matter physics, such as fractals. The third one is the non-invertible topological operators. I should say that this is an enormous subject, and it's impossible to cover every topic in one talk. I have to apologize in advance for the variety of fascinating papers that will not be discussed below. Also, there are many other generalizations of global symmetries that unfortunately I will not discuss today. This includes, for example, the dipole symmetry that has featured in Damson's talk earlier this week, and also the asymptotic symmetry that will be discussed tomorrow at this conference. I will not cover these topics in my talk. This talk will be mostly about generalizations of internal global symmetries in bosonic systems. For an example of a gravitational anomaly, you can see Yuji Tachikawa's talk earlier this week. For anomalies in fermionic theory, you can see Gomis's and Putrov's talks at this conference. Finally, this talk will be structured from a more field theory / high energy physics perspective. You can see Xiao-Gang Wen's discussion later today for a complementary condensed matter perspective on topological phases. All right, so with all these disclaimers, let me start the talk by a brief comparison between global versus gauge symmetry. Global symmetry acts non-trivially on operators and states in our Hilbert space. It's an intrinsic property of the quantum system. It is therefore important to be able to characterize global symmetries abstractly and invariantly without referring to any Lagrangian description. I should say that the adjective global here doesn't necessarily mean the symmetry operator acts globally on the whole space. The adjective global here is really to distinguish from gauge. By contrast, gauge symmetry is not really a symmetry. It leaves all the operators and states invariant. It should really be thought of as a redundancy of our description. Gauge symmetry is ambiguous, it can be present in one presentation of the model, but not in the other. For example, the 2 + 1 dimensional free Maxwell theory is exactly dual to a free compact scalar field theory in 2 + 1D. There's a manifest U1 gauge symmetry in one presentation, but not in the other. So how do we characterize global symmetry abstractly? For an ordinary internal global symmetry in D space-time dimensions, it can be characterized by its symmetry operator, which will be denoted as U sub G, where G labels the group element of the ordinary global symmetry. It is supported on the codimension 1 manifold M, here in the argument, it's codimension 1 in space-time. For example, we can take the manifold M to be supported over the whole space at a given time. Then this symmetry operator is an operator that acts on the Hilbert space. More generally, we can take M to be extended along the time direction, then it's really a defect. The second property is that this symmetry operator is topological under deformation of this codimension 1 manifold. In particular, it is conserved under time evolution. That's why it qualifies as a symmetry. Third, the fusion between these operators obeys the group multiplication law. Just to illustrate these properties in the simplest possible example, let me do it in the case of an ordinary U1 global symmetry. In that case, there's an associated Noether current, which is a D-1 form in D space-time dimensions. And we can take the Noether current to integrate it on a codimension 1 manifold in space-time. The fact that the Noether current is closed, namely the Noether conservation equation, implies that the operator is topological under deformation of M. Finally, the U1 fusion rule trivially follows from the exponential expression. In the rest of this talk, I will generalize the ordinary global symmetry by modifying the above conditions. Here, I'm just repeating what I just said for the ordinary global symmetry. The first generalization that I will discuss today is the higher form global symmetry. Its symmetry operator is now supported on a higher codimension manifold in space-time. It's topological. The fusion of this operator still obeys a group-like fusion rule. In fact, for higher form global symmetry, the group has to be abelian. The second generalization is the subsystem global symmetry. Similar to the higher form global symmetry, it's supported on a higher codimension manifold in space-time. What's different from a higher form global symmetry is that there are restrictions on the possible manifolds it can be supported on. Furthermore, it's not completely topological under deformation of this manifold that it is supported on. Nonetheless, the subsystem symmetry operator is conserved in time evolution, and that's why it qualifies as a symmetry. The third generalization is the non-invertible topological operators. It can be supported on a higher codimension manifolds in space-time. But for most of this talk, I will focus on the case when it's codimension 1, just like the ordinary global symmetry. It's completely topological, but the fusion between the non-invertible topological operators is generally not a group, but a fusion ring, meaning that if you multiply 2 objects on the left-hand side, you get more than 1 object on the right-hand side. So these are the 3 generalizations that I will be focusing on in the talk today, and there are possibly even more generalizations if you combine different columns. So let me start with the first one, the higher form global symmetry. We are now in this column. The simplest case of the higher form global symmetry is a Q-form U1 global symmetry. In that case, the associated Noether current is a D-Q-1 form in D space-time dimensions. So we can integrate the current on a codimension Q+1 manifolds in space-time. This Noether current is closed, and that implies that the symmetry operator is topological, and the U1 fusion rule follows directly from the exponential expression. The reason that it's called a Q-form symmetry is because the charged objects are Q-dimensional. This is to be compared with the ordinary global symmetry, aka the zero-form symmetry, where the charged objects are zero-dimensional local operators. Higher form global symmetries can have 't Hoof anomalies, or even mixed 't Hoof anomalies with ordinary global symmetries. These are obstructions to gauging the higher form global symmetries. Such anomalies have to be matched along the RG flows. A non-trivial anomalies in the UV therefore imply that the low energy phase cannot be trivially gapped with a non-degenerate ground state. This is because the trivial non-degenerate vacuum in the low energy cannot possibly reproduce the non-trivial anomaly in the UV. In this paper, they demonstrate this idea in the example of a 3+1 dimensional SU2 pure Yang-Mills theory at theta equals 2π. There's a mixed anomaly between the ordinary CP symmetry and the Z2 one-form center symmetry. This mixed anomaly implies that the low energy phase cannot be trivially gapped, and that's to be contrasted with the expectation at theta equals to 0. And this is one example of how the higher form symmetry anomalies imply something non-trivial about the low energy phase under RG flows. Let me move on to higher form symmetries in topological quantum field theory, or just TQFT. TQFT is generally characterized by the extended topological operators, and a subset of them generate the higher form global symmetries. Let me focus on a simple class of TQFT in 2+1 dimensions. These are the abelian Chern-Simons theories. There's no local operator in the abelian Chern-Simons theory, but there are a lot of interesting Wilson lines. These Wilson lines generate the one-form global symmetry of the abelian Chern-Simons theory. These are lines in 2+1 dimensions, so they are codimension 2 in space-time. These Wilson lines arise as the Ward lines of the anyons excitations in the microscopic lattice model. Below, I will use Wilson line and anyon interchangeably. Anyons can have braiding with each other, as shown schematically in this figure. And the braiding between the anyons can be interpreted as the 't Hoof anomalies of the one-form global symmetry generated by the corresponding Wilson lines in the low-energy 2+1D abelian Chern-Simons theory. This interpretation has been pushed forward in these papers, and it has been proven to be very useful in analyzing various properties of the abelian Chern-Simons theory. These interpretations of the Wilson of the anyons and its braiding in terms of the one-form global symmetry and its 't Hoof anomaly, for example, has application in analyzing the possible gap boundary conditions of the abelian Chern-Simons theory. This perspective will be further discussed in Komargodski's talk later today. Let's consider a simple example of the abelian Chern-Simons theory, the 2+1 dimensional Z2 gauge theory. It can be described in terms of two one-form U1 gauge fields, little a and little a hat. The Lagrangians takes this form 2/2π AdA hat in 2+1D. This is the low energy continuum field theory of the famous Tori code, Halaki-Taif. There's a Wilson line generated by the A gauge fields wrapped around a non-trivial cycle L in space-time. There's also a Wilson line U hat generated by little a hat. Together, the Wilson line U and the Wilson line U hat generate the Z2 cross Z2 one-form global symmetries. It's a Z2 operator because U square is the trivial line, similarly for U hat. These Wilson lines are topological, meaning that they only depend on the topology of the line, but not the detailed shape of the line. The fact that there's a cross-term in the Lagrangian between A and A hat means that there's a non-trivial braiding between the Wilson line U and U hat. This can then be interpreted as the mixed hoof anomaly between the two Z2 here of the one-form global symmetry. How do we see this two-hoof anomaly explicitly? Let the space be a two torus with A and B cycles. The mixed hoof anomaly implies that if you wrap the Wilson line around the A cycle in space and multiply it by the U hat Wilson line wrapped around the B cycle in space, then these two operators fail to commute. The minus sign here in red signals the mixed hoof anomaly between the Z2 cross Z2 one-form global symmetry. Similarly, you have an algebra with A and B cycles exchanged. One significance of this algebra is that it does not admit a one-dimensional representation. The minimal representation is two-dimensional, and since we have two pairs of such algebra, they lead to a fourfold ground state degeneracy on the torus for the Z2 gauge theory. The fourfold ground state degeneracy is robust because there's no local operator perturbation that can lift the ground state degeneracy. In fact, in the Z2 gauge theory, there is simply no local operator at all. The fact that it's robust means that this degeneracy is not an accident of fine-tuning. It means something non-trivial and intrinsic about this topological phase. We can think about this topological phase described by the Z2 gauge theory invariantly characterized by its Z2 cross Z2 one-form global symmetry and its anomaly. And you can see the series of condensed matter papers as well as Xiao-Gang Wen's discussion later today for parallel discussion on how to think about this topological phase from a more condensed matter perspective. There are many, many other topics in higher form global symmetry, which unfortunately I will not be able to review today. Let me just briefly mention some of them. The first one is the higher group symmetry. This is a mixture of higher form global symmetries of different degrees. This has led to many non-trivial constraints on RG flows and many other interesting results. In the past couple of years, there has been a lot of developments in analyzing the higher form global symmetries in supersymmetric field theories, especially those arising from string or M or F theory compactification. And there has been really a lot of papers and progress, and Schafer-Nameki will describe certain aspects of this development later in her talk. Finally, the spontaneous breaking of higher form symmetry has been discussed in McGreevy's talks earlier this week. All right, so now we can move on to the second generalization, the subsystem global symmetry. We are now in this column. The symmetry of operator of a subsystem global symmetry can be supported on certain higher codimensional manifolds L in space. But unlike the higher form global symmetry, there are some restrictions on the possible higher codimensional manifolds L. For example, if the space is a two-dimensional plane, then the higher form global symmetry might only be able to be defined on straight lines on this two-dimensional plane. Also, unlike the higher form global symmetry, the subsystem global symmetry operators depend not only on the topology of the manifold L where it is supported on, but also on some of its detail shape. Excuse me. Nonetheless, it is conserved in time evolution, and that's why it qualifies as a symmetry. But notice that the time is now treated very differently from space. It is topological in time evolution, but not topological under general deformation in space. Therefore, a theory with subsystem global symmetry cannot be Lorentz invariant. The subsystem global symmetry acts non-trivially on the Hilbert space and on the operators. It's really a global symmetry rather than a gauge symmetry. It's also not in between global and gauge symmetries. In this little table, I compare the higher form global symmetry and the subsystem global symmetry. There are many interesting lattice models in condensed matter literature exhibiting subsystem global symmetry. The number of subsystem symmetry operators in these lattice models generally depends on the number of lattice points. And this leads to dramatic consequences on the low energy description of these lattice models. Observables in this system will vary at the lattice scale A, and hence they are discontinuous even in the continuum limit. And this is the hallmark of the phenomenon of UV-IR mixing in this class of lattice models. This point will be further discussed in Seiberg's discussion later today. This is somewhat reminiscent of the UV-IR mixing in the little string theory and in field theory on a non-commutative space. But they are different in many of the details. So before the discussion becomes too abstract, let me demonstrate some of these features in a simple quantum field theory with subsystem global symmetry. Let's consider 2 + 1 dimensional free field theory based on a compact scalar phi with 2π periodicity. This model, as well as its lattice version, were first introduced in this paper from almost 20 years ago in the condensed matter literature. The continuum field theory is given by this quadratic free Lagrangian. The novelty is that the spatial kinetic term is rather unusual. It takes the form of dx dy phi quantitative square. It has a U1 subsystem global symmetry that shifts the field phi by an arbitrary function of x plus an arbitrary function of y. This is a subsystem symmetry because I can take the function alpha x of x to be non-zero only at a particular value of x, but vanishes elsewhere. Therefore, for such choice of alpha x of x, this symmetry only acts on one column of phi, but not elsewhere. That's why it's called a subsystem symmetry. But let me emphasize again that this is a global symmetry rather than a gauge symmetry. We do not identify the configuration here with the ones that's being shifted. As usual, there's a Noether current for this U1 subsystem global symmetry, and it's given by derivatives of the field phi. The Noether conservation equation follows from the equation of motion of this free Lagrangian. This conservation equation is rather unusual because it involves two spatial derivatives in the equation. Let's forget for a moment where this equation comes from and just analyze it on its own right. Typically, if you have a Noether conservation equation, you can take the time component and integrate it on the whole space to obtain the conserved charge. In our case, the space is two-dimensional, but we can do something slightly better. We can take the time component and only integrate it along a one-dimensional straight line along the y direction, for example, in our two-dimensional space at a fixed x. This defines an operator qx of x for each point x. This turns out to be a conserved operator in the sense that if we hit the time derivative on this operator, it vanishes. It's easy to see that because you can commute the time derivative into the integrand and then use the conservation equation to write the integrand as a total derivative in the y direction. Therefore, we have an independent conserved charge, qx of x, at every point in x. And similarly, we have an independent conserved charge qy of y for every point in y. In the continuum, there are infinitely many such conserved charges, and that leads to the UV-IR mixing in this seemingly innocent-looking continuum field theory. The UV-IR mixing manifests itself in various observables such as the correlation functions. Another large class of models exhibiting subsystem global symmetries is is fractons. Fracton has become a very popular topic in condensed matter physics. It's a large class of lattice spin models with local interactions in the UV, but somehow exhibit various peculiar features in the low energy. First, it has a large ground state degeneracy that typically grows exponentially in the linear size of the system. There could be more complicated behavior of this ground state degeneracy in some of the more complicated fractal models. Furthermore, the ground state degeneracy is robust, just like the Z2 gauge theory we discussed before. Small deformations by local operators cannot lift the degeneracy in perturbation theory, and that means this large ground state degeneracy is not an accident of fine-tuning. Finally, various excitations of this fractal lattice model have restricted mobility. One key common feature of this model is the exact or emergent subsystem global symmetry, and that's responsible for various peculiar features of the models. The fractal models give rise to a large class of novel topological phases that do not admit a conventional continuum field theory description. Let's look at one simple 3+1 dimensional gap fractal model known as the XQ model introduced in this paper. Again, it's a lattice spin models, so you have two-level qubit at every link in your three-dimensional lattice in space. And the Hamiltonian is made out of local interaction shown schematically here. This is made out of sigma x and sigma z. I will not go into the details of the local interactions, but just show the picture schematically here. What's important is that this lattice model is gap, and it has a large ground state degeneracy on the torus with periodic boundary conditions given by this formula. Here, Li is the number of lattice sites in the I direction. As you take the continuum limit, you send Li to infinity. And therefore, the ground state degeneracy becomes infinite in the continuum limit. This large ground state degeneracies that depends on the number of lattice sites is a manifestation of the UV-IR mixing in this fractal model. So how do we characterize the subsystem global symmetry in this XQ model? This can be easily described in terms of a rather unconventional continuum field theory for the XQ model that has been developed in the past couple of years. The continuum field theory of the XQ model takes the form of a BF-type Lagrangian involving two kinds of non-relativistic tensor gauge fields, A and A hat. Here I'm suppressing their indices. The Lagrangian schematically take this form. It's called BF-type because it takes the form of a gauge field of one kind multiplied by the field strength of the other kind. The subsystem global symmetry operators are then identified as the Wilson operators of the gauge field A and A hat. These are known as the logical operators on the lattice. One kind of this Wilson operator is to take A and integrate it on a strip along the X or Y or Z direction. Another kind is to take A hat, integrate it along a line along the X or Y or Z direction in space. We have an independent such operators for each strip and line, and there are certain relations obeyed by them. These subsystem global symmetry operators lead to this many pairs of the clock and shift algebra, namely this algebra that we have already encountered in the Z2 gauge theory. Since this algebra does not admit a one-dimensional representation, it leads to this large ground state degeneracy. The minus sign here can be viewed as an anomaly of the subsystem symmetry, and we can view the XQ model as a topological phase invariantly characterized by the subsystem global symmetry and its anomaly. In other more exotic gap fractal models, such as the Ha-code, the subsystem symmetry operators are supported on fractal geometric objects on the lattice, and that make them even more complicated. So let me summarize part 1 and part 2 in this little table. In part 1, we discussed the Z2 gauge theory in 2+1D. is a topological phase that arises at the low energy limit of Kitaev's Tori code. It has foreground state degeneracy, and it's a topological phase invariantly characterized by its Z2 cross Z2 one-form global symmetry and its mixed anomaly. In the second part, we talk about one of the simplest fractal model known as the X-cube model. Its low energy limit is described by this BF type Lagrangian. And it's a novel topological phase characterized by its subsystem global symmetry and its mixed anomaly. I should say that there are also hybrid models, excuse me, that mix the higher form global symmetry and the subsystem global symmetry discussed in these papers. All right, so that concludes the second part, and I'm going to move to the third generalization, the non-invertible topological operators. But before I begin, let me motivate a little bit about why should we think about this generalization and also the higher form global symmetry. If I only want to work with ordinary global symmetry, when will I necessarily run into these two generalizations? And the answer is given by gauging. And let me start easy with gauging in 1+1D. If we gauge a non-anomalous ordinary ZN global symmetry in a 1+1D bosonic CFTT, then the original ZN global symmetry is gauged and disappears. But we gain a new symmetry, the blue ZN, in the orbifold theory T prime. This blue ZN has many different names in the literature, sometimes known as the orbifold symmetry, the quantum symmetry, the dual symmetry. One nice thing about this blue ZN is that we can subsequently gauge the blue ZN in the orbifold theory T prime to retrieve our original CFTT. So in 1+1D, we have this little relation that we can start with the CFT, gauge the red ZN to go to the orbifold theory. In the orbifold theory, we can gauge back by gauging the blue ZN. T and T prime are two different CFTs. They might happen to be isomorphic to each other, like the Ising CFT, but the red ZN and the blue ZN do not coexist at the same time in a well-defined 1+1D theory. Sorry, I think there's some background. Okay, I think that's good. We can generalize this relation in two different directions. We can generalize it in higher space-time dimensions. In higher space-time dimensions, if I gauge a zero-form global symmetry, I will actually obtain a higher form global symmetry. More generally, if I gauge a higher form ZN global symmetry, I will get a ZN higher form symmetry of a different degree. Alternatively, I can stay in 1+1D, but replace the cyclic group by a non-abelian finite group G. Then in the orbifold theory, I will not have a non-abelian finite group G. Rather, I will have various topological Wilson lines, but they do not obey a group-like fusion rule. They obey the representation ring of the finite non-abelian group G, but that's generally not a group. And this is our first encounter of the non-invertible topological lines in 1+1D. More generally, in 1+1D, topological lines are extended operators that do not necessarily obey a group-like fusion rules. These are lines in our 1+1D space-time, and the fusion rules take this general form. And when you multiply two objects on the left-hand side, you generally get more than one terms on the right-hand side. A non-invertible topological line is a line L such that it does not have an inverse obeying this relation. In recent years, non-invertible topological lines have been discussed from a modern perspective as generalizations of ordinary global symmetries. It carries many different names, sometimes known as the topological symmetry, fusion category symmetry, non-symmetry line, or algebraic higher symmetry in condensed matter literature, or non-invertible symmetry. Non-invertible topological lines are everywhere in 1+1D. They have a long history in rational conformal field theory. In fact, in rational conformal field theory, there's a systematic constructions of non-invertible topological lines that commute with the extended chiral algebra. Second, as I have already discussed, they also naturally arise from gauging a non-abelian finite group G in 1+1D. Third, non-invertible topological line can also arise from an anomalous ordinary global symmetry in a fermionic 1+1D theory after GSO projection. Non-invertible topological lines also exist in various lattice models, so they have their UV lattice realizations. One simple example is the golden chain. It's a one-dimensional chain, so the space is 1D, and there's an operator, and the Hilbert space of this 1D chain is not tensor factorized. And there's an operator that commutes with the lattice Hamiltonian, but obeys the Fibonacci fusion rule, which is not a group. There are also more constructions of such non-invertible lines in statistical model in 2 dimensions in these papers.
5 minutes, Shu-Heng.
Oh, okay, thank you. The existence of certain non-invertible lines imply that the low energy phase cannot be trivially gapped. That has been discussed in these papers and many of the follow-up papers that I will discuss below. And this is one reason we should view the non-invertible lines as a generalization of ordinary global symmetries, because the existence for certain lines have similar consequences as an ordinary 't Hooft anomalies for ordinary global symmetry. One example is the tricritical Ising CFT perturbed by a relevant operator, sigma prime. This relevant operator explicitly breaks the Z2 symmetry, but preserves a non-invertible line. This flow has been solved by Zohar in the 90s. It's known that the low energy phase is gapped with the twofold degenerate vacuum. The degeneracy cannot be explained by any symmetry because the only symmetry is explicitly broken by the relevant deformation. Rather, it's an inevitable consequence of the non-invertible line W that's preserved along the whole flow. In the paper from last week, there are more constraints of this kind in 1+1D that were derived. There has been a lot of development on non-invertible topological operators. In this paper from last year, these authors discover a large class of non-invertible lines in 1+1 dimensional massless adjoint QCD. And that gives rise to a large ground state degeneracy in the large N limit and also demonstrates the deconfinements of the Wilson line. Please also see Gomis's talk later today for discussion of more general QCD in 1+1D. The 2+1 dimensional bulk interpretation of the non-invertible lines have been discussed here. In the monster CFT, there are also non-invertible lines, and that leads to a kind of categorical generalization of the monster moonshot. In higher space-time dimensions, the absence of certain topological operators, more specifically the Gukov-Witten-like operators, are linked to the completeness of spectrum in gauge theory. And that was already discussed in Valenzuela's review talk on swampland last week. In the last couple of years, there has also been discussion about non-invertible topological operators in the condensed matter literature, known as the algebraic higher symmetry. Finally, topological operators have also been discussed in Cassini's talk in the algebraic QFT context. All right, so I will conclude my talk. So I discussed 3 generalizations of ordinary global symmetries. The first one is the higher form symmetry. The second one is the subsystem symmetry. The third one is the non-invertible topological operators. 1 and 3 can arise naturally from gauging ordinary global symmetries. And there are many other ways to arrive at these 2 generalizations. The subsystem global symmetry naturally arise from seemingly innocent lattice models, such as fractons. Their existence inevitably leads to UV-IR mixing. This more general perspective of global symmetries unifies many known phenomena into a coherent framework. For example, generalized global symmetries and their anomalies provide an invariant characterization of many topological phases of matter, such as fractons. But it would be disappointing if that's all we can achieve with this more general perspective. More importantly, this more general perspective has led to many new results and non-trivial constraints that are otherwise completely obscure. In this talk, I review several generalizations of the standard 't Hooft anomaly matching condition, and that leads to many non-trivial constraints on renormalization group flows. There are many more to be explored, and the development in the past few years has really relied on collaborations between high-energy physicists, condensed matter physicists, and mathematicians. And I feel like this is really an exciting time to be working on this subject. All right, so I will end my talk here with this slide, and thank you very much for listening.
Great, thanks, Shu-Heng. That beautiful and perfectly timed talk. So yeah, any questions, please raise your hand or type it into the chat. Carmen had a question. I don't know if it's already been answered. Does gauging non-invertible symmetries simply mean restriction to the identity sector?
Yeah, let me comment on that. Yeah, so Carmen, thank you very much for asking that question, which I intentionally leave out in this in the talk, but I really appreciate that you asked it. So I have a very implicit slide about it with gauging in quotation mark. So in 1+1D, the gauging of non-invertible lines have been developed, at least in the math literature, and it has been at least developed very rigorously in the context of 1+1D TQFT. And let me just briefly say, what does that mean? When we gauge an ordinary discrete global symmetry in 1+1D, we can think about them as summing over the background gauge fields for the discrete symmetry. Alternatively, that's equivalent to decorate your partition functions by various insertion of the symmetry defects. So you insert defects around various non-trivial cycles in space-time. For the non-invertible lines, I do not know of a background gauge field formulation, but we have the defects. We have the non-invertible lines. And gauging corresponds to inserting a mesh of such non-invertible lines on your space-time manifold. There are various consistency conditions that have to be obeyed by the line for you to be able to gauge these non-invertible lines. And that's the generalization of the anomaly-free condition. There are also freedom in how you gauge, quote unquote, these non-invertible lines. And that's a generalization of the discrete torsion. I hope that at least vaguely answered your question.
Thanks.
Okay, so I think the next question was from Xavier Magan.
Yes, hi.
Hello.
Comment just a little bit more on the intuition behind the relation between non-invertible topological operators and non-trivial gap phases. It was basically the last slice or the last to last slice. That one, yeah. The first, can you comment a little bit on the intuition?
Yeah. Thank you, thank you for asking that. I'm being very brief. I'm being very vague about the word certain here. So the idea here is that we have some set of lines, non-invertible lines, and you want to ask, is the existence of these lines compatible with a non-degenerate trivial vacuum? So in the gap phase, in 1+1D, a gap phase is characterized by just a set of topological local operators. You can think about them as the vacua of the gap phase. And if the lines are preserved in this gap phase, then the lines will act non-trivially on this topological local operator. So they should form some kind of quote unquote representation of the topological lines. And you have to solve this, this condition. And you also want to make sure that when you insert the line along the time direction, it gives you a non-trivial Hilbert space interpretation. And these constraints generally cannot be satisfied by a single topological operator. Generally, the representation for these topological lines is more than one dimension. In that case, that means the topological lines force the low energy vacua to be degenerate. There's a more fancy category way to phrase this condition, to phrase this word certain in a very elegant category language, but let me not get into that. The physics intuition behind is to check the consistency conditions of how the lines acting on the topological local operator. And you have to check various conditions similar to the Cardi conditions.
But what I don't understand is, I thank you for that answer. It was very clear, but I don't understand then why that is particular of non-invertible lines. So if I would have like a set of invertible lines, like a generalized symmetry, well, then I get also the same result. So it seems that this is particular of non-invertible lines, no?
So for ordinary global symmetry, they are invertible, and they can, if they do not have anomaly, then it's compatible with a non-degenerate vacuum. But when it has an anomaly, then it cannot be compatible with a non-degenerate vacuum. And in that case, you can show that a single vacuum cannot be a quote-unquote representation of this anomalous ordinary global symmetry. So what really goes into this word representation is more than just a group for ordinary symmetry. It also sees the anomaly information.
Thank you.
Yeah, thank you.
All right, Shu-Heng, there's an extended discussion in the chat. I believe there are two questions in essence. One is about, or maybe you want to read the chat. Is that easy? I mean, that might be easier.
Yeah, that might be. There are 20 chats when I just open it, so I don't know which one I should look at.
The dominant question, so Edward Witten asks, are there non-invertible symmetries above d equals 2?
Great, yeah. Thank you for that question. Yeah, so there are, so first of all, in higher than 2 space-time dimensions, there are certainly non-invertible topological operators. And one trivial example are the non-abelian anyons in 2+1 dimensional TQFT. And one can also ask, are there non-invertible codimension 1 topological operators in higher than 2 space-time dimensions? I add the adjective codimension 1 just so that they are more closely related to the ordinary global symmetry. And the answer is, again, yes. And one simplest example is in 2+1 dimensional transassignment theory, such as U1 level n, there are topological surface operators studied by Kapustin and Solina, and their fusion is generally not a group. There are also more constructions of non-invertible topological operators in higher D via gauging. Yeah, so there are many of them, but I should say that applications, dynamical applications of non-invertible topological operators in higher space-time dimensions are rather limited at this point.
Thanks. I think you implicitly addressed one of the other questions, which was, can we think of non-abelian anyons as generating non-invertible one-form symmetries in 3D? I think you said yes, right? Is it?
Yeah. Non-abelian anyon is a kind of non-invertible topological line. Yes, that's right.
And finally, I think, and this will be the last question, there's a question from Hugh Osborne. Do any of the anomalies discussed here relate to the kind of anomalies arising at one loop calculations as in the old axial anomaly?
So for ordinary global, well, in this particular talk, I think the short answer is no. Yeah, I didn't discuss. I think most of the anomaly I discussed in my talk are discrete anomalies.
All right, well, we have 2 more minutes if there are any other questions. Yes, from Greg.
So with usual anomalies, we have a notion of an anomaly field theory, 1 dimension higher.
Yeah.
What would be the analog of that?
Yeah, that's an excellent question, and that was implicit in this bullet point. So let me give a answer to that. So for ordinary, so if I have a, let's say 1 plus 1D for concreteness, if I have a 1 plus 1D theory with some global symmetry and anomaly, then I can couple it to a 2 plus 1 dimensional SPT. It's a classical SPT. I can cancel the anomaly. And then subsequently, I can promote the gauge fields to be dynamical and get a TQFT in the bulk. The analog of the TQFT for non-invertible lines were analyzed and discussed in this particular context in this paper. And that turns out to be the derived zero TQFT in 2+1D. I do not know of the generalization of SPT for non-invertible lines.
Right, that's a very special case. I mean, one would want a general discussion just the way you have the anomaly field theory in general.
Yeah, so I think the corresponding TQFT is the derived zero.
No, but I mean, that's your answer is very specific to this one example. I think there should be a general example.
Oh, you mean higher D?
General construction, just the way there is for anomaly field theories for the usual anomalies of zero form symmetries.
Yeah, that's right. In this, not for the non-invertible lines, and it's a special case, and that was addressed in this paper.
Okay, we are basically out of time, but maybe if Franz Klinkheimer has a very quick question.
Yes, it's not so much a question, it's to expand on the discussion of global versus local anomalies. So just for your information, the Witten SU2 anomaly is related to the Bardeen SU3 anomaly, which is perturbative. So there are certainly relations between global anomalies and local anomalies that we know already from ages ago, right? So perhaps this may also apply to your work, Mr. Shao.
Yeah, so in my talk, I focus mostly on global symmetry and its 't-Hoof anomaly.
Right.
Yeah, if you have a theory with some gauge theory presentation, and if the gauge theory has a gauge anomaly, then the theory is simply inconsistent. So I try to separate the discussion of system with global symmetry and putative theory that's just inconsistent because it suffers from gauge anomaly.
Yeah. Okay.
Yes, and the two are, usually can be related by gauging, if you wish.
Okay, but time is up, I'm afraid.
Yes. Let's thank Shu-Heng again for a wonderful review.
Thank you.
Next up is Sakura.
Okay, let me just share my screen.
Okay, so the next talk is by Sakura Schafer-Nameki, and she'll talk about higher form symmetries in string theory. Please go ahead.
So thank you very much, Sean. Thanks to the organizers for this fantastic conference and also for inviting me to speak here. As Shu-Heng already said, I'll be speaking about higher form symmetries in the context of string theory. That's an enormous field, and so I'll be focusing on one aspect in particular that has appeared and been discussed in these two papers with my fantastic collaborators, Laksha Bharadwaj and Max Hübner. So let me actually start with some motivation. Why would we consider this in string theory? You can hardly hear me. Greg, maybe you want to tune up the volume. I can also do this. Is this better? Greg? I don't know. Sean, you can hear me?
Yes, it's fine.
Yes, I can. Yeah.
All right. So where were we? So motivations. And we've seen higher form symmetries are by now very well established in quantum field theory. So what's the added benefit of looking at them in string theory? Well, the usual arguments really apply here. We have access in string theory to quantum field theories that may be strongly coupled, maybe non-Lagrangian, or in a regime that we cannot access otherwise, other than realizing them in string theory. So some examples of that are geometric engineering and 5D or 6D theories, in particular SCFTs, strongly coupled theories like holography, and then also non-Lagrangian theories like class S constructions. And indeed, in the past year, we've seen enormous amount of work, in particular on this geometric engineering avenue. So, for example, in 5-dimensional theories, in particular SCFTs, higher form symmetries were calculated, Toft anomalies, and even two-group structures were analyzed. Also in holography, the past years have seen some applications of these higher form symmetries to actually refine our holographic dictionary. And that goes into class S duals, ABJM, and also revisiting confinement in the Klapnow-Stassler context. What I'll actually focus on today is this third point, looking at non-Lagrangian theories, which we can obtain from, say, 6 dimensions via class S construction. So I'm not interested just in computing, say, one-form symmetries from 6 dimensions in class S. I'm interested in a physics question, which is sort of modeled with this very classic example of 4D n equals 1 super n moles, where we know the one-form symmetry is a diagnostic for confinement. So Wilson lines with area law indicate confining vacua, where the one-form symmetry is unbroken. The pyramidal law implies that we have deconfining, we're in a deconfining phase, and the one-form symmetry is spontaneously broken. So the goal of this talk will be to take this paradigm and generalize it to theories that may not have a UV Lagrangian, like in the Seiberg case. And the class of theories I'll discuss is n equals 1 deformations of n equals 2 class S theories. So to do that, actually, we need to first generalize or reformulate this Shu-Heng story in a more class S sort of point of view. So we actually have to do a lot of things we know very well, but in a slightly different formulation. And then at the end, I'll explain this generalization. Okay, so the plan is as follows. Some basics. So Shu-Heng already gave a very beautiful introduction to higher form symmetries. I'll just give some more background on that. Then I'll discuss one-form symmetries in 4D n equals 2 class S. And then the third part will be about n equals 1 deformations, in particular revisiting the Shu-Heng case, and then actually providing some examples for non-Lagrangian theories. Okay, so let's start with line operators. I'll have to talk about polarizations and then how we get to one-form symmetry. And the starting point is, say, a 4-dimensional gauge theory, pure, think of it as pure n equals 1 Shu-Heng mills. We have a gauge algebra G and a simply connected group capital G. So the set of lines is the weight lattice, not the root lattice. So these are basically what we would call the Wilson lines, and then the magnetic version, which are the Toft lines. And both of these quotients are isomorphic to the center of G. Now, the set of lines L is actually not a set of mutually local lines, because we have a Dirac pairing, and as we exchange 2 of these lines, we pick up a phase. So if we insert them in correlators, that gives us some additional phases. So that's what we actually call a relative theory. To actually get an absolute theory, which is a definite set of mutually local line operators, we have to pick a polarization, so it's a subset lambda in L, such that all the line operators in that set commute, and it's a maximum set. So for example, for SUN, L is just Zn plus Zn. The non-trivial pairing is between the Wilson and the Toft lines, and that's a 1 over n. So we can pick, for example, a polarization, canonically just the Wilson lines, that will give us what we call the gauge group SUN, or the Toft lines, which gives us the PSUN theory, or there are many other choices of polarizations. And we'll encounter at least some examples later. So what's the one-form symmetry once we have this set up? So we have a lambda polarization inside the set of lines. And the one-form symmetry is simply the Pontryagin dual group, lambda hat. So it's the Homs from lambda into U1. And I'll denote that by gamma 1. So in this example for SUN, lambda was Zn, and gamma 1 is also Zn. What we'll need is a slightly more refined notion of preserved one-form symmetry later on in n equals 1 when we have a vacuum. We basically would like to know what is the set of lines that actually have area long. So if I define as lambda r the set inside lambda that has pyramidal law, then really the one-form symmetry that's preserved in this vacuum is lambda hat over lambda r. And if that's non-trivial, then we'd say this vacuum is actually confining. Okay, so that's the background, and let's talk about class S theories now. The class S construction starts, of course, in 62.0. There we have an algebra of ADE type. That theory is a relative theory. We have a 2-form symmetry, and there are surface operators that are not mutually local. So when we compactify this on a curve, so some genus G and some number of punctures, And to get to a 4n=2 theory, we should think of this curve as embedded into T star C, so some local K3. To get the line operators of this 4-dimensional theory, we start with the surface operators of the 6D theory and wrap these on 1 cycles in this curve. So this is basically labeled by H1 of CG, comma Z. So in the simplest case, if you just have a Riemann surface with genus G and no punctures, the set of lines is just H1 of CG with values in Z hat, where Z hat is this two-form symmetry group of the 6D theory. So we can decompose this now into A cycles and B cycles. This is Z hat, or the A cycle ones, and these are the B cycle ones. And then we see again, there's a non-trivial pairing on these lines, which descends from the pairing in Z hat, and also an intersection pairing of the 1 cycles on the Riemann surface. So what we get from this compactification is a relative theory again. So again, we can pick some polarization. The simplest ones are just pick the A cycles or the B cycles. And then the 1-form symmetry of this class S theory is then just lambda hat. So the Pointryagin dual group to lambda. So here I simplified this problem. I just looked at a non-twisted theory. It's just genus G. There are many interesting refined notions that arise in class S from these twist lines. And I won't be discussing them because I'm actually trying to head to n=1 and the time is short. So before I go to n=1, I actually want to discuss a sort of an interlude on geometric engineering, because we can think of 4n=2 theories also as arising from type 2b geometric constructions where we compactify 2b on a non-compact Calabi-Yau threefold. So X here is non-compact, so there's a boundary del X. And now we can ask what's the 1-form symmetry of this 4n=2 theory that we get from this engineering compactification. And here the line operators are basically the 3 branes wrapping non-compact 3 cycles. So they give rise to line operators, modulo screening by local operators, which are these 3 branes in compact 3 cycles. So mathematically, this means we're looking at the relative homology of X with respect to its boundary and mod out the H3 of X. And those are the lines from this geometric engineering setup. And indeed, we can also write this simply in terms of some second homology of the boundary geometry. So what's nice about this point of view is it's computable for any sort of geometrical engineered theory, for example, for Argyris-Douglas type theories, which are not easily accessible otherwise. But also we can sort of check what we talked about earlier in class S. We have some class S theories will be ALE fibrations over Riemann surfaces. So if you have the simple case of no punctures, then there'll be just these types of geometries. These are local Calabi-Yau threefolds. And we can now compute for these geometries exactly this set of L from the homology. So the LE fibration here is governed by Higgs field, which satisfies the Hitchin equation that's written out here. And sort of phi is just sort of the field whose spectral curve is just a Seiberg curve. So you get some n-shaded cover of the base curve, which is the Gaussian curve. And now applying this to this problem, computing now these homologies, we find exactly the same as what we found earlier using just a class S description. Okay, so that's just a comment that this geometric engineering approach also allows you to calculate these higher form symmetries that applies not just to 2B, but also to M theory, to F theory, and the many developments that we can discuss later on. Okay, so what I want to head to is the n=1 deformations. So if you actually would like to get to 4n=1 from 6D, we don't compactify on a Riemann surface that's embedded into local K3, but actually in the local Calabi-Yau threefold. So here I'm taking the simplest sort of possible thing. It's a sum of 2 line bundles of suitable degree. And in fact, I have 2 sections, phi and psi. And I'm even simplifying this further. I'm starting with sort of phi being this n=2 Higgs field, and psi is just an additional Higgs field, so it's 0 form on the curve. And these now have to satisfy, to get to 4n=1 theory, a generalized set of Hitchin equations. So they're very similar to the n=2 case, but they're a slightly more complicated system of equations that we need to solve. And so each of these the spectral curves for each of these two fields, phi and psi, define an n-shaded cover over C. And the strategy now will be, we start with an n equals 2 Higgs field, and then we, what's in the literature called rotate to n equals to 1. And what it means is just we then turn on the field psi and then go to a particular point in Coulomb branch where we can actually solve the system of equations. So the case we're interested in is confinements. Actually, the starting point should be 40n equals 2 pure young moles. So I need to explain or recap briefly where this comes from. It's of course very well known. We start with SU2 for simplicity. This is the brain system. 2n has 5 brains, 2d4 brains. The Seiberg-Witten curve for that is written out here. So we should think of T as essentially the coordinate on the base curve, which is a P1. V is the coordinate on the curve, on the cover, and U is on Coulomb branch parameter. And now we can translate this Seiberg-Witten system now to class S construction, where we start with a genus 0 curve, and now we have 2 punctures, but these punctures are irregular, so they have poles that are of higher order than 1. In fact, here the pole order for phi is 3/2. So this quadratic differential is pole order 3 at both of these. So these are these so-called P0 punctures. So how do we go from n equals 2 super-young moles to n equals to 1 super-young moles for SU2? We have to now, in addition, consider this field psi. We determine what kind of boundary conditions it has at these 2 punctures, and then we sort of solve for these Hitchin equations, these general Hitchin equations. So the first thing I'll do is at t equals infinity, I'll just impose the psi asymptotes to essentially phi. So phi was this one form. So in fact, I need to contract with some vector field. So psi goes to mu times phi zeta. And then at t equals to 0, I just want psi to be regular. So now with these boundary conditions, we can now solve for these BPS equations. And one of the equations says phi and psi need to commute. And so if they're both diagonalizable, we simultaneously diagonalize them. And for generic enough spectra, the branch code structure actually of these 2 things has to agree, because one has to be a function of the other. So we can now solve this analytically. And given the time, I will actually just tell you how we do this topologically. So what we actually have to do is take the 2 fields, the spectral covers, and then actually match the branch cut structure so that it agrees. So we have one consistent cover of the curve. So I just described this to you, but there's also some analytic approach to this problem. Okay, so this is the curve for the field phi, so that has coordinate v. We have these 2 irregular punctures. There are 2 additional branch points. The branch points are the crosses, and then there are these branch cuts between them. For the additional field psi, this n equals 1 field, we have 1 irregular puncture and then 1 branch cut here, a branch point here connected with a cut. And so now we have to tune Coulomb branch moduli to bring these to the same sort of branch cut structure. And so one way of doing this is to collide these 2 branch points and to move both of these points to t equals to 0 and infinity. And there are exactly 2 loci where this is possible, and the resulting curve is written down here. So if you actually want to get to what's more commonly known as the n equals 1 curve, you also have to take now the limit mu goes to infinity, and then basically in some rescaled coordinates, we also introduce this n equals 1 scale, then we have these 2 curves. So there are 2 choices of the sign here, but those are the 2 curves that we can find. And basically those describe the 2 vacua of the SU2 theory. So one is simply, we have these 2 regular punctures connected by a branch cut. And in the other one, there is an additional sign change in the W coordinate, and that can be furnished by actually going around this cut, going with the cut around this branch point. Okay, so these are the 2 curves for the 2 vacua. So now we'd like to actually see what are the line operators, and are these, in which of these polarizations are these actually confining. So more generally, let's consider we have some lines. We have lambda as a polarization for the class S theory. Then actually the n equals 1 vacua, characterized by some curve sigma r, will have the following one form symmetry. So we need to first define what actually is the set of lines that have perimeter law. And we conjecture that this is this following set. So these are projections of one cycles on this cover that project non-trivial to one cycles in the base. So those are the perimeter law lines. So if you intersect those with the polarization, then those are precisely the ones that are sort of not, those are the ones we would like to mod out. So lambda over lambda cap IR is basically the set of lines we're interested in that have area law, and then the Pontryagin dual group of that is the one form symmetry in this vacuum. And if this is now non-trivial, then the vacuum is confining. And one way to see that this is the correct criterion is to remember, so an argument of Witten, that the confining, how the confining strings arise in this kind of setup from membranes that sort of end on relative cycles in the Calabi-Yau sigma. So let's look at how this works for SU2 again, very briefly. So if SU2, the line operators are the Wilson and 't Hooft lines. There are the following cycles. W is here, and then H is this relative cycle between the two irregular punctures. We need to determine now these sets of lines that have perimeter law. Both of, if you go twice around this branch cut, so 2W should be 0. We should mark this out. And then the I plus curve, the H line is also trivial. In the other case, H plus W is trivial. And so now if we actually put it all together, we have the different polarizations for SU2. These correspond to the following global forms of the gauge group, SU2, SO3 plus, and then the change data angle SO3 minus. Then in each of these two vacua, sigma plus and sigma minus, we find the following one form symmetries. And that's of course very well known in much more general terms discussed in the reading between the lines, but now we got this purely looking at this curve picture. Of course, this can be generalized to n equals 1 superangles. The branch cut structure is more complicated in this case. Again, there's a topological argument to collide the various branch points to then find that the curve for the n vacua is simply, you have a branch cut, a Zn branch cut that r times encircles one of the irregular punctures. And then we have precisely n such vacua. Okay, so I think I should probably, when did I actually start?
You got 5 minutes to go, 5.5 minutes.
Fantastic. So now let's actually do something new. So let's actually talk about the theories that actually are not sort of known theories where we know that it should be confinement, but things that using this sort of method, we can now argue for confinement, although there's no Lagrangian UV description. So the starting point is the 60 SUN theory. We put on a sphere with alpha irregular punctures. So irregular puncture for SUN basically means we have poles of order 1 plus 1 over n. The simplest case is just we have 3 of these punctures. Right, so 2 was the superangles case, we add the third puncture there. And this corresponds to essentially starting with a TN theory and engaging all three SUN flavors. So this is sort of a picture for this Pn,3 theory. And the line operators are again simply obtained in terms of the Wilson lines encircle the punctures and the 't Hooft lines span between the punctures. And then in this case, there's a relation that the sum of all the Wilson lines and sum of all the 't Hooft lines need to vanish. Again, this is sort of a relative theory. There's a non-trivial pairing, and we can choose, for example, the simplest electric polarization in this case. So just look at the Wilson lines. Okay, so now the logic is the same. We start with this n equals 2 thing, and now we go to the n equals 1. We need to, now this is the curve for the n equals 2, 2. So this is the V curve, Higgs field. It has these 3 irregular punctures, and then there are branch lines and branch points. And on the n equals 1, so this psi field has the following curve, where now these irregular punctures, 2 of them have been rotated, but the third one is just a branch point. So there's no singularity at that point. And so now again, we can analytically sort of find a solution to the Hitchin system, or we just look at the branch cut structure and these two things match. So in fact, this is sort of the structure in which we generate this picture. So once we repeat this and look at, for example, this electric polarization, we see that this theory, and this vacuum that's described by this curve has a Z3 times Z3 one-form symmetry, and so it's confining. And there's a whole family of this type, so we can generalize this to the SUN with now n P0 punctures. There are these line operators, which are coming just from W's and from H's as before, with the relation. So these are Zn to the n-1 and Zn to n-1. And then again, we have sort of the same procedure applied to this particular set of cuts in the plane. We match the two curves, the V and the W curve. We find that there's a vacuum that has this particular structure. And now looking at sort of the electric polarization, for example, can show that this actually has a preserved one-form symmetry, at least for n equals to n prime. Okay, so this is sort of a way of showing that with this method, you can arrive at confining theories that have no, at least obvious UV Lagrangian description, and so argue for the presence of confinement in such setups. Okay, I should conclude. I hope I gave a glimpse of why studying higher form symmetries in string constructions is interesting. I focused on this n equals to 1 construction, and because it sort of gives a nice prediction for interesting confining theories that we might not have found otherwise. In that particular context, it would be interesting to compute anomalies and to determine also what are the TQFTs that govern the IR of these confining vacua from the 6T point of view. And there are topics that I didn't cover, but I'm happy to discuss in the Slack channel. I think one interesting direction are these higher dimensional gauge theories and the higher form symmetries in that context. They're interesting Toft anomalies that have been proposed, and also higher group structures for such theories. So mixtures between 0 and 1 form symmetries, as Shu-Heng was already explaining. Okay, and then finally, in holography, there are interesting developments as well. And one thing that I think sort of in this context of confinement that might be interesting is one can revisit now the Klebanov-Strasler solution in the context of these higher form symmetries. So there's a 1 form symmetry, which one can see the imprint of in the holography, and then actually using the supergravity, derive what the IRTQT is that governs the theory at the deformed conical. Okay, so let me thank you for your attention.
Thanks, Sakura. Another perfectly timed talk. That's great. So we have time for questions, either in the chat or you can raise your hands. And there is already a question from Maria Pilar Garcia. Can you comment on the extension of your results to M theory?
Right. So in M theory, let me just go to the slide for the. So in M theory, you can again compactify, for example, on a singular Calabi-Yau threefold, and then ask in this 5-dimensional theory, what is the 1 form symmetry, for example. And again, it's about understanding where the line operators come from. In that case, for example, you have M2 brane swapping now non-compact 2 cycles, modulo screening by compact 2 cycles. And so in that way, you can then determine the 1 form symmetry of the 5D theory. Now that sort of tells you, it's essentially information that is sort of blind to where you are in this 5-dimensional moduli space, whether the Coulomb branch or the Higgs branch. So in some sense, it tells you potentially about the 1 form symmetry of the CFT itself. And of course, you can also extend this to M theory on G2 and then play a similar game, for example, with the G2 manifolds that give rise to N40 n equals 1 to the n most, for example, right? Something that I think my chair has worked on in the very, very far past. Is that answering your question? Okay.
We definitely have time for some more questions. There will also be a session, I should have mentioned this earlier, though, later today, Seiberg and Xiao-Gang will have a discussion on related topics where definitely any questions that occur to you later can be asked. So should I just wait another minute in case somebody thinks of something?
Dan Harlow.
No, I was just wondering if you'd thought about these non-invertible topological symmetries that Shu-Heng was talking about.
Yes, we have. How one would realize them in string theory. Yeah, that's a very interesting question. In particular, these O2 theories that were discussed by Irene and collaborators, potentially we could construct them in some string theory construction, also made from 6 dimensions. That'd be very interesting, but that's in progress.
All right, why don't we thanks Sakura again. Oh, sorry, there's a talk from Ed Witten. Please go.
In your talk, you were compactifying to 4 dimensions to get 4D theories. But presumably, if you simply worked in 6D, you'd have
a two-form symmetry.
Two-form symmetries. Has anything interesting been done in 6D?
So in 6D, we have this two-form symmetry. I just mentioned it very quickly here. So right here you have objects which sort of have a pairing FF is 1/n, for example, for SUN. And so it's a relative theory already from the get-go. So I think in 6D itself, so the theory itself, you really should define it as more a theory that is the boundary of a 7-dimensional theory. Most of the time, I think one of the points I think that is sort of interesting to note is whenever you consider any kind of background, be that a compact space times another compact space, any types of D plus P is equal to 6-dimensional space-time, you actually need to choose in some sense a polarization already in 6-dimensional. You have to choose already some kind of subset in this H3,
yes,
the set of self-dual 3 forms. And that's an important piece of information. So already also in the 3D correspondence, there's an important piece that one needs to take into account to actually get a full picture of the correspondence.
I guess the reason you say it has to be should be a relative theory, well, in four dimensions, when we can pick a Lagrangian sublattice without breaking 4-dimensional symmetry.
Yeah.
Whereas in 6 dimensions we can't.
Yeah, no.
I guess that's the difference.
Yes, I think that's true. Yeah.
Thank you.
Very good. Thank you. So again, if there are any more questions, there's this discussion session later. And thanks, Sakura, again.
Thank you.
Jaume, do you want to try to share screen now?
Hi, Nathan. Yeah, let me try that.
Hi, Eric.
Let me turn it. Okay. I'm over. Visible?
Yeah.
Great.
Zohar, do you want to try now?
Maybe try changing slides, Jaume, just to check that that also works. Yeah, it's good. It's good.
Oh, let me try the pen. Oh, oh, yeah, yeah. Okay, perfect. Should I unshare or?
Yeah, you can unshare. Zohar, do you, if you're online, do you want to try? Maybe offline. Xiao-Gang, are you online?
Yes, I am. So let me try to share.
Pedro, should we attempt screen sharing?
Yep. Just after Xiao-Gang is first.
Okay, let me try to do this. Yeah. Can you see my screen? And the cursor?
Yeah.
Yeah.
Yes, it's perfect.
Okay, good.
Okay.
Can I try?
Yep. So Nati, you're going to be using, oh, you have your own. Okay, good.
I tried to do it from the node, but it didn't
Oh,
work.
it's better if you have your own. So now you should be able to share. Are you on? Yeah, okay. So
Is it all right?
it's appearing twice. So we're seeing your next slide also.
Yeah,
So
let me try again.
that looks good.
Is it okay now?
Yeah, you want to try to move it to change it just to make sure?
Can you see the pointer?
Yeah,
Does it work?
yeah, it's working fine. So Zohar, you want to try now?
How is it?
So we're seeing the side panel, which probably you don't need.
I can probably.
Okay, that's perfect. So Eric, just to remind you, there's a discussion session just after. So
Yes.
if there are leftover questions, you can just channel them to the discussion session.
Okay, so I'll stop in the time.
So Jaume, if you want, you can share your screen already.
Oh, okay. You see it?
Yep. We'll start in just 1 minute.
Sure. 1 minute.
Okay, I'm happy to chair this session where it's 2 speakers. And the first speaker will be Jaume Gomis, and he will talk about infrared phases of 2-dimensional QCD. Jaume, please go ahead.
Okay, thank you, Eric. So I would like to thank the organizers for bringing us together into this kind of very exciting meeting and for the opportunity to speak. It's really a pleasure and an honor. So in this talk, I will describe work to appear with 2 students at Perimeter, Diego Del Mastro and Matthew Yu. So a central theme in physics, and one that transcends fields, is to determine the low energy phenomena that emerges from a physical system defined by a collection of microscopic degrees of freedom and interactions. The fact that many different types of phenomena can emerge that look very different from what you put in at very short distances is what gives physics its richness and beauty. The first qualitative question that I would like to answer, given a microscopic Hamiltonian, and that has dramatic consequences for the physics at large distances, is to determine whether the spectrum of the Hamiltonian is gapped or gapless, as this will clearly affect the long distance behavior. But actually, even though it's a simple question to pose, in general, it's a hard question to answer, because it's a non-perturbative problem to determine whether a given Hamiltonian is gapped or gapless in the thermodynamic limit. An example of a famous and rich example of theories where the phenomena that you see in infrared is quite distinct from what you put in, namely massless gluons, is Yang-Mills theory, which, in spite of the fact that a short distance is described by a Hamiltonian of massless gluons, it is believed, but not yet proved, that the theory develops non-perturbatively a gap. And this is a kind of a prime example of the kind of richness that you can get in physics by putting something in the oven that looks one way, and when you get out of the oven, it looks completely different. So one very natural question that we like to enlarge is the following. You can try to enrich the study of pure Yang-Mills theory by adding to the mix massless quarks coupled to Yang-Mills theory and transforming a representation R of G. And I'm going to call these theories of Yang-Mills coupled to massless quarks, QCD-M, and N is going to be the space-time dimension for the rest of the talk. So very natural questions. We have a tentative answer for the case of pure blue to be which QCD theories are gapped and which ones are gapless. Okay. More ambitiously, we would like to know what is the low energy description of a given QCD theory. So let me just make a couple of general comments about what can happen. Asymptotic freedom bounds which QCD theories in 4 dimensions can be gapped, because if you add too much matter, the theory is infrared free, and it's gapless because you get massless gluons and quarks in infrared. But there is a famous example of an instance. There is an example where you have a lot of control to essentially prove that if you add 1 quark in the adjoint representation, the theory is actually gapped. And this is the famous N=1 superior. Now we can try to ask a similar question in 3 dimensions. So something that can be reliably established. So in above 4 dimensions, we don't have the asymptotic freedom bound. So in principle, you could add any representation, any quark in any representation, and the theory would flow through strong coupling in infrared, and we don't know what would happen. But one result that we can establish is that the theory flows to conformal field theory in the large representation expansion. So one natural question was, and is still, whether by looking at QCD with quarks in a small representation, whether the theory can remain gap, just like the pure Young means remains gap. And it was found out that there are some examples where you could argue that such thing happens in 3 dimensions. But kind of the landscape of which theories are gapped or gapless, and where the transition from the gapless phase that you get in the large representation expansion to a possibly gap phase is very far from the unanswered. So the question I want to tackle and answer in this talk is the following. I want to answer this question in 2 dimensions. I want to ask and answer which QCD theories in 2 dimensions are gap and which ones are gapless. And as a second question, I want to ask what emerges into fact. What is the low energy description of a given QCD theory? Tell me the QCD theory that you want. Let's discuss what the infrared description of the theory is. So let me just remind you a couple of things about 2-dimensional QCD. So QCD in 2 dimensions is specified by a gauge group G and a pair of representations for the left and right moving quarks. Notice that in 2 dimensions, you cannot, unlike in 4 dimensions, write down a QCD theory just using left moving quarks. In general, you have to use left and right moving quarks. Okay? And this is the action. Okay? This is not an exhaustive list of all the symmetries, but I mentioned ones that will enter in the little time I have for this talk, which are flavored symmetries, one form symmetries, and non-invertible symmetries. One useful perspective in tackling this question is to think of the QCD theory that I wrote here, the Lagrangian that I wrote here, as being obtained by gauging a certain subgroup of the flavor symmetry group of the 3 quarks that you got in the default survivor. From this perspective, you can think of G, the Young-Mills coupling, as trickle and RZ flow from a very short distances that of three quarks. So the question that we want to ask is what happens in the infrared of such a theory. So before we go there, we have to I have to mention a couple of peculiarities about this theory in 2 dimensions. The QCD Hilbert space in 2 dimensions is split into distinct topological sectors. And you have to study them all if you really want to answer this question of what theories of gap and different gaplets. The physical picture for these topological sectors is that studying within a topological sector is equivalent to studying the theory in the presence of a flux tube that created by probe quarks that you put at infinity. Okay? And a flux tube in 2 dimensions possesses Poincare invariants. These are Poincare invariant vacuum, and you have to study the theory in all possible flux sectors that are labeled by an element, by a chart under the one form symmetry. I'll make now a quick argument that to tell you that for the purposes of this talk, which is determining whether the theory is gap or whether the theory is gap, it is sufficient to study the Hamiltonian in the sector with no flux tubes. And the quick argument I'm going to give you is that essentially QCD theory, these QCD theories in 2 dimensions have topological lines that are charged in the one form symmetry. And essentially by acting with the topological line on a given flux sector, you can change from one flux sector to the other. Okay? And physically, since these are topological lines, they have 0 energy density, and they cannot make a theory that was gapped into gapless. Okay? So this is, I'm just telling what kind of the raw physical picture, why it's sufficient to look at the theory where the flux sector is trivial. Okay? And it suffices to study QCD with a simply connected gauge group, simply because if you try to study the theory with a gauge that does not simply connect, so say G mod gamma, where gamma is a subgroup of the center, or with a church of theta angle that's also labeled by an element, by a chart under the one form symmetry, this can be shown to be exactly the same as studying QCD with a simply connected gauge group in the presence of a flux tube. So the summary of this slide is that in order to determine whether the theory, the theory is gapped or not, it will suffice to look at the theory with no flux tubes and with simply connected gauge groups. So let's try to first tackle the questions using general considerations and see how far we can get. And what I want to try to use is what constraints Tooth anomalies will impose on this question. So since Tooth anomalies are topological, and that means that they're invariant under symmetric deformations, including RG transformation. So any symmetry that has a Tooth anomaly that that is not broken by turning on the gates coupling will have to preserve the tooth anomaly along the RG flow. Okay. Famously, tooth anomalies constrains the infrared dynamics of the physical system, and the details depend a little bit whether the symmetry continues or discrete. Roughly speaking, what can happen is the symmetry that has the tooth anomalies continues, the symmetry can flow to a symmetry preserving gapless phase, or a symmetry preserving gapless phase described by a nonlinear Gauss component. The same can happen if the symmetry is discrete, except that there is one important difference, an important new ingredient that can emerge, and that you can have a phase in which the symmetry that has a tooth anomaly is preserved, but you have a gap system with topological order. And this kind of situation has played a very important role in topological phases of matter, and actually also the thing I mentioned about three-dimensional PCB. One peculiarity about, so now we're going to focus on this talk in two dimensions. One peculiarity about two dimensions that these two possibilities are gone. The first one is just a statement of the Coleman-Wagner theorem that says there is no continuously breaking in two dimensions. And this other one is just a statement in two dimensions that topological quantum field theories do not have topological order. Good. So after this discussion, a necessary condition for a PCB theory to be gapped is that it has no tooth anomalies for any continuous symmetry that is preserved along the RG flow. If a continuous symmetry, if there is a tooth anomaly, it will necessarily flow to a gapless state. Okay. So a gap theory cannot have any continuous chiral flavor symmetry, because if you have a chiral flavor symmetry in the deep ultraviolet, the gates coupling will not break it, and this will lead by elementary arguments to a tooth anomaly, where this B is the background gate field for this chiral symmetry. So the theory cannot have a gap theory. A necessary condition for a theory to be gapped is that it has no continuous chiral flavor symmetries, and likewise it cannot have gravitational anomalies. If it had gravitational anomalies, the theory would be gapless. Okay? So this is very general kind of armchair considerations allows you to constrain the quark quantum of PCB by demanding that the theory do not have either global symmetries, continuous global symmetries, or absence of gravitational anomalies. So this is a useful criterion because, for example, it allows you to prove that PCB with gauge group SG2 and quarks in a half integral representation is gapless, but it doesn't really answer, for example, whether PCB with SG2 gauge group and quarks with integer spin will flow to a gap or gapless. So it's a very general argument, but it's not completely known. In order to answer this question, we really have to get out of the armchair and do support. So now I'm going to describe a method that allows us to answer this question by actually looking at the Hamiltonian of the theory. So the Hamiltonian I'm going to describe is the Hamiltonian in the light cone gauge. Okay. In the light cone gauge, what you do is you treat one of the light cone coordinates as time. Okay. And you use this to evolve the states in the Hilbert space. This setup has very nice properties. One of the key features that it has is that if you want to determine the mass spectrum of your theory, what you have to do by virtue of this famous formula, you have to diagonalize the Hamiltonian of the theory. Now now you can try to construct the Hamiltonian of arbitrary PCB theory in the light cone gauge. You fix the gauge, and essentially you can integrate out the gauge field. And the non-trivial part of doing that is generate this interaction. This interaction has a simple physical meaning, just the statement that you have charge sources, and integrating out the gauge field generates a Coulomb potential between these charge sources. And where this JA is the quark current that we have gates to go from free fermions to PCB. Okay? And famously, the first important detail to mention is that famously, in two dimensions, the quark currents generate a current algebra at level K, where K is the Dynkin index of the representation of the quarks. So the name of the game here is to try to, well, what you would really like to do is to diagonalize P minus over the entire Hilbert space. So the first thing that you have to do is you have to write down the Hilbert space that's created by the quarks. Okay? And so here is the Fock vacuum, which in the light cone gauge is exactly the same as the non-perturbative vacuum. And you write down the most general state that you can get by hitting the vacuum with the quarks. Now, solving this problem of diagonalizing P minus is extremely difficult because P minus is actually a non-trivial way on this Hilbert space, and it's not a simple problem. But here we're after a very specific question, which is to determine whether the theory is gap or gapless. Okay? And now you can, by looking at this expression, the first thing to notice, this expression is positive semi-definite. So from here, you can establish two things. First, that a necessary and sufficient condition for a state in the Hilbert space to give rise to a massless state is that this state is a primary state of the current algebra generated by the quarks. And that's just the estimate that that's the only way that this operator can vanish. Okay? That's essentially the definition of an operator being primary under the current algebra. And two, the primary state has to be a gate singlet. It has to be a primary state that something that is the representation of G. And that's just a statement that we have fixed the gate, but you have the residual Gauss's law that you have to impose. Equivalently, you can say that the QCD theory will be gap if and only if the vacuum, the Fock vacuum or the non-perturbative vacuum is the unique primary singlet state in the Hilbert space. If that were not true, that would, by this argument, would give rise to massless particle. So now let's unpack this a little bit. And it will be useful to think a little bit from the perspective that I'm going to describe in order to answer this problem. So the first observation that's known for a very long time is that you have a collection of fermions in 2 dimensions that the Hilbert space of the fermions decompose into modules of a certain SO current algebra level 1. Okay. Now, we have constructed the theory by precisely gauging a subgroup of the flavor symmetry of the quarks, which was this SODIN R symmetry. And this gauging induces an embedding of the current algebras. So this was the current algebra that's created by the quarks, the quark current, and this is the current algebra generated by the free quarks in the deep ultraviolet. What we want to understand is what is the spectrum of primaries of G and how they transform under the representation of G. That will tell us information about when the theory is gapped. One very nice way of encoding this information is through by looking at how the modules embed. Essentially, what I want to do now is to decompose the Hilbert space of the quarks into modules of the G current algebra, because that's the kind of the order parameter that we will use to decide whether the theory is gap or gapless. And that can be very nicely done by decomposing the characters of the respective current algebras. So this chi is the character of the SO current algebra, and this other chi is the character of the G current algebra. And in general, unlike for finite groups, for Lie algebras, this B is a non-trivial function of some counting parameter that measures the energy of the state. These labels are the labels of the integrable representations of the respective current algebras, and they're a finite number of representations. Physically, what's the physical meaning? And that is the key guy. This guy is called the branching function. The key physical point will be that this quantity, B lambda, counts the number of primary states of the G current algebra that we're after that are in a given module of the SO current algebra. And B has a simple physical interpretation. It's actually a character of the commutant chiral algebra. So you have the chiral algebra of G and SO. You can think of B as a character of the commutant chiral algebra, which will necessarily contain the difference of the energy momentum tensor that you created in the deep ultraviolet from the free quarks minus the energy momentum tensor of the gates current. Okay. If the theory has a flavor symmetry, we'll have other objects like flavor symmetry current. Good. So let me repeat the main statement that I discussed earlier. We said that QCD theory is gapped even only if the vacuum state is the unique primary singlet state of the current G current algebra. Okay. This can be phrased now in terms of the branching functions with the statement that QCD is gapped precisely if the branching of any module of the SO current algebra into the singlet of G, the zero means the singlet primaries of the G current algebra is independent of Q. If it were dependent on Q, it would mean there is more than one singlet primary, and that would give rise to a massless spectrum. So let's just consider the branching of the trivial representation of the SO module into the trivial representation of the G module. And this has a very universal form. It has a trivial factor, a raw factor of 2 that's interesting, that essentially is determined by the central charge of the 2 current algebras. And then it has a power series expansion in Q. So now we have to determine what is the physical meaning and what constraints this gives us. The first estimate to say is that the leading coefficient, the coefficient A1 that multiplies the power of Q, is essentially a dimension of the flavor symmetry group. in physical terms, this would come from states that you create out of the vacuum, like this. If you have a flavor symmetry, if you have a flavor symmetry, then obviously the currents commute with the G current algebra and give rise to massless states. So the constraint that you want the spectrum to be gapped requires that A1 is 0 and that there are no continuous global symmetries. So we have derived from the microscopic Hamiltonian point of view the kind of fluffy arguments of Tooth anomalies have told us before. For a necessary condition for the theory to be gapped is that it has no continuous global symmetry. Now let's discuss the Q-square term. So that's, we have to, in principle, analyze all these terms order by order. Let's discuss the Q-square term. When there are no flavor symmetries, actually there is a unique state at level Q-square, and it's a state that's created by acting on the vacuum by a very particular combination of the fermions in the Hilbert space. And the precise combination that gives rise to a primary state and to this Q-square term is the difference of the energy momentum tensors acting on the vacuum, where this T is these T's are the canonical energy momentum tensor of the fermions in the deep ultraviolet, and TGR is the energy momentum tensor, the Sugawara energy momentum tensor of the G current algebra that's generated by the quark current.
John, we have 5 minutes talk on that.
Okay. So we don't want this Q squared to be there for the theory to be gapped. So the condition for the theory to be gapped, and another condition for the theory to be gapped is that the energy momentum tensor of the ultraviolet is the same as the Sugawara energy momentum tensor of the gauge theory. Okay. This has this imposes very strong constraints on the theory and has very dramatic consequences. One of them is to actually say that the branching function are exactly of this type. So the fact that the equation that you get by studying the theory of the branching functions at order Q squared to determine what are the primers at level 2 actually tell you the branching functions are essentially trivial, and there is only a non-trivial element that corresponds to the vacuum module. Okay? So we are done. We don't have to analyze high orders of Q because the Q square equation is so rigid that has allowed us not to consider. Essentially, it immediately makes all the other higher powers into divine. Okay? So from here, we establish that the necessary and sufficient condition for electricity theory to be gapped is that the ultraviolet canonical fermion energy momentum tensor is the same as the Sugawara energy momentum tensor of the quark current. Now, this equation may look a bit strange because it's an equation that relates an operator that's quadratic in the fermions to an equation that's quartic in the fermions. But we have to remember that these operators have to be normal order. So now you can try to analyze what this equation is. And it gives rise to an interesting, to remember that these TAs are the representation matrices under which the quarks transform under the gauge group G. So imposing that the two energy momentum tensors are the same gives a Jacobi-like identity for the generators TA in the representation R under which the quarks transform. And it looks something like this. And that just comes from comparing the energy momentum tensors and doing proper normal ordering. It turns out that a beautiful result is that the solution to these equations are in one-to-one correspondence with symmetric spaces. And these were classified by Arkani. Okay. Another way of saying it is that the space of solutions of this equation describes conformal embeddings of the GK current algebra into SO current algebra. And since these things have been classified by before, we have a complete list of the possibility theories that are gapped. From this equation, essentially, we're able to read the collection of gauge groups and representations that give rise, that solve this equation, essentially. And any other theory that's not in this list will be gapless. So let me just flash, because I'm running out of time, what the actual answer to the problem is. So here I listed all the QCD theories that are gapped in 2 dimensions. Let me point out a couple of things. The first one is that notice that I didn't lie to you and that all the representations here are real. You may worry that, for example, here I have the unitary gauge group where I have a U1 factor here, but now you have to remember in 2 dimensions, you have an ABJ anomaly. And the flavor symmetry, the classical flavor symmetry of the quark can be killed by the ABJ mechanism. So in fact, none of these theories have a continuous flavor symmetry. For the classical groups, you can see that there is a strong restriction of what is the quark content that will give rise to a gap theory. At most, you can get theories that have representation that are rank 2. Something else to say is that almost all of these theories are vector-like, and that just comes from solving the equations for the 3 to be gap, with one very important exception. If you consider a Gates theorem, the product of unitary Gates groups, actually the charges under the various G1 factors can be chiral, as long as, of course, you cancel gauge anomalies. So the point is that this is the complete set of two-dimensional QCD theories that are gapped in infrared. Anything else that you want to write down will be necessarily gapless. So in the last minute I have, let me just tell you, the other thing that we would like to do is to give a description of what emerges in the deep infrared for a gap or gapless theory in QCD theory. An obvious conjecture that you can try to make is that what you're going to do is just take the G-square infinity limit that's just going to the deep infrared of the Lagrangian that I wrote down. And actually, this Lagrangian is a famous Lagrangian. It's a Gates WGW description of this coset. Okay? And this coset, in fact, as you would expect from physical grounds, is a topological quantum field theory when the QCD theory is gap, and it's a non-trivial conformal field theory when the theory is gapless. So here I just wrote a few examples of the kind of conformal field theory that you get when the theory is actually gapless. So this first example is the theory that was studied by Tooth, which is SUN with an F fundamental quarks. And using this reasoning, you can prove that the theory flows to a UNF level N WGW model. Let me point out that this theory in the infrared nicely reproduces the Tooth anomalies of the flavor symmetry of the theory in the deep ultraviolet. I mentioned this example because this is an example of a theory that flows to something that you recognize, which is SU2 theory with a quark in the 7-dimensional representation. This flows to a tricriticalizing model. Using the fact that the theory has interesting Tooth anomalies for discrete symmetries now in the ultraviolet, you can predict and sometimes test the fact that actually these minimal models on general two-dimensional conformal field theories have interesting Tooth anomalies for symmetries that you may not have considered before, like time reversal symmetry. So I'm probably essentially out of time, so let me just conclude. So QCD theories in 2 dimensions exhibit a whole host of interesting phenomena, including supersymmetric spectrum by virtue of Tooth anomalies, non-perturbative quark condensates, quark deconfinement, etc., etc. So even though they are, of course, simpler than 3- and 4-dimensional theories, they have a lot of punch in them. In this talk, I have shown that the problem of determining what theories are gapped in 2 dimensions can be solved. Now you can use these results to study what happens to QCD when you give a small mass to the quarks in the ultraviolet, or you add some other kind of marginal or relevant difference in the ultraviolet. You can study this in the infrared by deforming the infrared description with those operators. It's been interesting that the Hamiltonian method has been kind of very fruitful in tackling this problem. So you may wonder whether one should get the courage to try to tackle these problems in 3 dimensions. Actually, Feynman initiated a program of trying to solve QCD in 3 dimensions, and followed up by beautiful papers by Carabelli and Nair. So maybe it's now time, given that a similar method has been quite fruitful in 2 dimensions, to try to tackle it in 3 dimensions. So with that, I'll stop and thank you for your attention.
Okay, Jaume, thanks for this very nice presentation. We have a few minutes left for questions. I see there is a question by Veronica. Can you ask the question?
No, I was just clapping.
Oh, sorry. There is a question by Igor. Sorry, Igor, can you ask the question?
Yeah, thanks for the very interesting talk, Jaume. So one criterion you could have is, basic criterion is that this gauge WTW model has 0 central charge in the infrared.
Yes.
Right. So do all the examples that you listed of gap theories, they presumably all have that, right?
Have that, yes. But the thing that's interesting is that the condition was derived by doing a computation in the deep ultraviolet without making any assumptions whatsoever about what happens in the infrared.
Right, right. Well, it's just a formula for the central charge of the gauge.
Yes. It turns out that this equation, this equation essentially is the statement that the central charge of that coset, if that's the right answer for the infrared physics, has central charge.
So this is a necessary and sufficient condition, basically,
Yeah.
that this infrared central charge is vanishing, right?
Yeah, but I want to distinguish that statement. I mean, in the second statement here, there's an assumption. There's an assumption that the infrared theory is described by this limit. In the computation the people provided, there is no assumption. I just look at the Hamiltonian of the theory and look for the condition. I just want to distinguish these two statements. The first statement will still be true, and this could be wrong for some reason. The second one about the infrared limit. It could not be. It could be given by some other object, another description.
Yeah, maybe I was naive, but I was always just assuming that the infrared theory is just this gauge WZW model. And,
this is, I guess, I would make it if you guys in the middle of the night.
Okay, we still have time for a very quick question. Joanna, could you ask your question?
Yeah, very quick question. So, hi, Jaume, can you just follow up on your very last point about QCD3? I mean, how much of these very beautiful structures do you expect to survive if you go to higher dimensions?
Well, I mean, many special things are very specific to this two-dimensional work. But in 3 dimensions, there is this formalism that was developed by Nair and Carabelli and Feynman originally. Sadly, it's actually, as far as I know, this is the last problem that Feynman worked on. In 3 dimensions. And there is some, they're using a usual Hamiltonian formulation, not the Lycon formulation. And there is some nice structure, reminiscent of 2-dimensional theories, where you study vector bundles over a 2-dimensional surface. You have double Giolio models appearing as wave functions and so on. So I do not, I mean, I do not know whether I'll be able to, I mean, whether this is feasible, but it doesn't look completely impossible. I mean, the work that has been done so far, I mean, I'm not an expert on it, so let me rephrase that. Has done some work that has, with some intriguing success for computing the QCD string tensions. But it's also fair to say that I do not understand in what sense those calculations are in a reliable self-consistent approximation. So the answer is that I do not really know whether 3 dimensions will be definitely much harder, not to mention 4 dimensions.
Okay, thanks.
Okay, in view of the limited time, let's stop and let's thank Jaume once more again for this nice presentation. And I should say that after the next talk, there also will be a discussion session for those of you who want to continue the discussion. So, but let's now continue with the next speaker, who is Zohar Komargodski, and he will talk about higher central charges and gapped boundary.
I'm not going to share, right? Okay.
Okay, Zohar, please go ahead.
Thanks so much to the organizers for this magnificent event, from which I already learned a lot, and I think it's extremely well organized, and also for letting me present this work in collaboration with Justin Kaidi, Kantaro Mori, who is now in Tokyo University, Sahan Saif-Nashri, who is my student, and Shu-Heng Shao, currently at the IIS. So let me just start with a very slow review. We've known for 40 years or so from the work of Alvarez, Gomis, Witten, that 1+1 dimensional systems are forced to be gapless if the chiral central charge is non-vanishing. I will refer to this combination as the chiral central charge throughout this talk. But from a modern perspective, when we think about 1+1 dimensional dynamics, we have to distinguish 2 cases. One is when this chiral central charge is a multiple of 8, and it's possibly non-zero. Then the terminology nowadays would be that this system has a gravitational anomaly, but it's of the 't Hooft type, a 't Hooft gravitational anomaly. So a 1+1 dimensional system with a non-vanishing chiral central charge is not invariant under diffeomorphisms. But the type of non-invariance under diffeomorphisms should be distinguished between 2 cases. One is when the chiral central charge is a multiple of 8, and the other when it's not. So when it is a multiple of 8, the non-diffeomorphism invariance of the 1+1 dimensional theory can be ameliorated or cancelled by adding an auxiliary bulk system, which is 2 + 1 dimensional. So in particle physics, we think about it as an auxiliary 2 + 1 dimensional system. In condensed matter, it's often a physical system. So in this 2 + 1 dimensional space, we should add something in order to fix the non-diffeomorphism invariance of the 1 + 1 dimensional system. And if it's a multiple of 8, we only have to add the gravitational Chern-Simons term in this 2 + 1 dimensional system, and that's it. It's just a classical field theory in 2 + 1 dimensions. It's not a quantum field theory, just a classical field theory. So that's the situation of a 't Hooft gravitational anomaly. However, if the chiral central charge is not a multiple of 8, the non-diffeomorphism invariance cannot be cancelled by adding a classical field theory in 2 + 1 dimensions. And such theories are nowadays called relative theories. So in order to cancel the non-diffeomorphism invariance of the 2 + 1 dimensional system, of the 1 + 1 dimensional system, we must add a non-trivial physical quantum theory in 2 + 1 dimensions. This quantum theory in 2 + 1 dimensions ought to be either a gapless theory or a non-trivial topological field theory in 2 + 1 dimensions. So this sort of non-diffeomorphism invariance of a 1 + 1 dimensional system is much worse or much more constraining than this one. Now, let me just review a very classic example from condensed matter theory. Condensed matter theories have come up with the quantum Hall effect, in which we have a chiral mode on the 1 + 1 dimensional boundary, which has chiral central charge 1. It's just a chiral compact boson. And this is the boundary of a non-trivial topological field theory in the bulk, which is a U1 level K Chern-Simons theory. So this is a nice example of a relative theory. Because the chiral central charge on the boundary is not a multiple of 8, we cannot cancel the non-diffeomorphism invariance of a single chiral boson by adding a classical field theory. So we're forced to add a topological field theory in the bulk, and this is, of course, the claim to fame of the quantum Hall state. An example which is a little bit more standard is 8 chiral bosons moving on the E8 lattice, for instance. This is a system of just 8 chiral bosons, so it has a chiral central charge 8. And actually, this system does not require a 2 + 1 dimensional bulk, which is dynamical. We just need a classical field theory in 2 + 1 dimensions, and we can cancel the gravitational anomaly. So the topic of this talk would be the very general question of given a 2 + 1 dimensional topological field theory, we might have edge modes, like in the quantum Hall effect. But the question is, can it be that the edge modes cannot be lifted, cannot be made gapped, even if the chiral central charge is vanishing? And the answer is non-trivial. Let me give you an example. Consider U1 level K times U1 level minus K prime Chern-Simons field theory in 2 + 1 dimensions, for which I wrote the Lagrangian here. This theory, because it has a K and a minus K, so the total chiral central charge vanishes. And if you're just a very naive physicist, like I was up until a few months ago, you might think that there must be a way to gap the boundary, because the chiral central charge vanishes. The boundary, namely the edge modes, have no diffeomorphism anomaly. And since there is no diffeomorphism anomaly, why would there not be a way to gap the boundary? But the answer is non-trivial. The answer is that there does not exist a way to gap the boundary unless a very strange number theoretic condition on K and K prime is satisfied, namely that KK prime is a square of a number. And if it is a square, you can define gapped boundary conditions. So this Chern-Simons theory is the simplest example, as far as I'm concerned, of a system that has a boundary that is fully gravitational diffeomorphism invariant. There is no 't Hooft anomaly, but there is a funny restriction, which if it's not satisfied, the edge modes would be protected and gapless. So there is no way to get rid of the edge modes in this theory unless this funny condition is satisfied. So the example I've just given is for an abelian theory, but there are plenty of non-abelian examples. Let me just mention a very esoteric non-abelian theory, which is the Fibonacci enyons. Actually, they appeared in several talks already today. This is just G2 level 1 Chern-Simons theory. It has a chiral central charge, which is fractional. It's 14/5. And clearly, it leads to a relative theory in the boundary with gapless edge modes. But if you take 20 copies of it, then the chiral central charge is divisible by 8. And you might think, that you can gap it out now because the chiral central charge, because now there exist boundary conditions with vanishing chiral central charge. But it's not true. In fact, there is a theorem that no power of G2 level 1 has a gapped boundary. Another thing that I want to say before I get into the actual content of this talk is that there is some connection between the question of gapped edge modes and interfaces. So if two topological theory have an interface, there is a famous folding trick in which you bring T2 over T1 while you reverse the orientation of T2. So the question of the existence of gapped or topological boundary conditions for T1 times T2 bar is equivalent to the question of gapped or topological interfaces between T1 and T2. These are identical questions. And mathematicians, including these very nice and influential papers, have defined a group structure, which is like the right language to think about gapped boundaries. So the group structure is that if two theories, T1 and T2, are such that T1 times T2 bar has a gapped boundary, then we might declare these two theories to be equivalent. This defines a group, which is called the Witt group. It's an abelian group, and you can study it. This group has something to do with with gapped or topological boundary conditions because of this folding trick. So these two subjects are related, though not identical. So this leads me now to introduce the main topic of this lecture. Are there additional chiral central charges that we're unaware of that would explain why some Chern-Simons theories lead to boundary conditions with fully diffeomorphism invariant edge modes, but they cannot be gapped? That sounds like an anomaly, that you cannot gap something. Maybe there is a new anomaly. So the essence of this talk is about whether there exist new obstructions or some nice obstructions to gapping the boundary other than the chiral central charge. So we're asking if there is anything beyond the famous gravitational anomaly of Alvarez, Gomis, and Witten. Of course, this subject is of relevance to several communities, and given that I only have 15 minutes left, probably, I won't be able to cover all the points of view, but I'll give you a flavor of what kind of arguments we use in the upcoming paper to attack this problem. So the central idea is the following. This is perhaps the most important idea. So if a topological field theory has a gapped boundary, you can think about this gapped boundary as a topological boundary. Now, what does it mean for a boundary to be topological? It means that you can move the boundary without changing the partition function. There is no displacement operator response theory for the boundary. And this leads to far-reaching consequences that you will see. So let's take any topological field theory and carve out a cube. And on the boundary of the cube, we'll put our gapped boundary conditions. Now, because gapped boundary conditions and topological boundary conditions are the same, you can shrink the cube without changing the partition function. This is not true for the chiral. This is not true if there are chiral edge modes on the boundary. Then shrinking the cube would change the Casimir energy and it changes the partition function. But if the boundary of the cube is gapped, you can shrink it without paying any price. And now that you've shrunk it, you can replace this tube by a linear combination over anyons with non-negative integer coefficients. Just because a very thin object in Chern-Simons theory must be a combination of anyons, because the anyons give a complete set of the superselection sectors of the theory. And so the existence of a topological boundary is equivalent to the existence of a very special linear combination of anyons that's equivalent to that gapped or topological boundary. And so the whole point is to try to understand what are the restrictions on this very special enyon that I will call curly A, which exists only if there is a gapped/topological boundary. So the first thought experiment you can do is to consider the annulus, putting the Chern-Simons theory or the topological field theory on an annulus. And in the inside boundary, you can put this special enyon or the gapped boundary conditions. And on the outside, you'll put the famous chiral algebra, rational conformal field theory boundary conditions of Elitzur, Moore, Schwimmer, Seiberg, and anticipated, of course, by the work on Jones polynomials by Witten. So by shrinking the interior, I'm doing the same trick now of replacing this special boundary condition by a sum over anyons. I get a sum over chiral characters. So the existence of a topological boundary / a gapped boundary from the two-dimensional rational conformal field theory point of view is completely equivalent to the existence of a holomorphic modular invariant. And this is very constraining from the two-dimensional point of view. It leads to the fact that this linear combination of anyons has to be invariant under the S matrix in some sense, and it has to be invariant under the T matrix, and it leads to a constraint on the quantum dimension of this very special anyon curly A. So it leads to a bunch of algebraic constraints that you can put in the computer. The way to say it from the rational conformal field theory point of view is that the chiral algebra can be extended to have one character. So it's something that can be implemented almost algorithmically on the computer. And if you were to do this exercise for U1 level K times U1 level minus K prime or the Fibonacci anyons, you would see that there is no solution. For theories of the type T times T bar, which is a theory in its time reversal, of course, there must be a gapped boundary because by unfolding, there's a trivial interface. And you can find an explicit expression for this very special anyon A, which is equivalent to this bubble of nothing tube curly. So there you can find it explicitly. It's one of the only examples where there is a general explicit expression. Now, for abelian theories, this constraint immediately implies that the total number of anyons must be a complete square. And that explains why KK prime had to be a complete square in our U1 example at the beginning of the talk. So from these considerations, you can immediately derive that for abelian theories, the number of anyons must be a complete square. Otherwise, there cannot be. Sorry. So in addition, you can derive that for abelian theories, this curly anyon A is comprised of generators of an anomaly-free one-form symmetry. So these are some particular things for abelian theories. And this connects to some developments in the subject long ago, like a decade ago, by Kapustin, Saulina, very nice works by this group and the condensed matter people and many others. So for abelian theories, what I've said so far can be shown to be completely equivalent to the existence of an anomaly-free one-form symmetry. Now, it could be that there is more than one anomaly-free one-form symmetry group of the right dimension. And for instance, this appears in the low energy limit of the toric code that Shu-Heng mentioned. But I won't get into it for lack of time. Now, the gapped boundary that you can obtain in theories where this curly A, special anyon A exists, is you should think about it as condensing this anyon. And for abelian theories, we understand what it means to condense an anyon. It's the same as gauging a one-form symmetry. Here, I just want to emphasize that for non-abelian theories, while everything I said so far is true, namely that the existence of this curly anyon A is what you need to have a gapped boundary, what it physically means to condense A is not as clear. And Shu-Heng referred to it at the end of his very nice review talk. These are some papers that he also cited in the end of his review talk. Trying to understand what it might mean to condense a non-abelian anyon A, there is no clean path integral interpretation yet. So now let me get to the main, summarize the main results in the last 5 minutes. The chiral central charge famously appears in the three-sphere partition function. And it's an obstruction to having a gapped boundary. This is the gravitational anomaly of the edge modes. So the main point is that there exists many other chiral central charges, which are likewise obtained from partition functions on some three manifolds. They are the phases of some partition functions on three manifolds. So this is a central theorem that you can prove, that a gapped boundary for any topological quantum field theory, whether it's abelian or non-abelian, implies that the partition functions on length spaces with index n are positive numbers without phases, as long as this GCD condition is satisfied. Now, NFS is the Frobenius-Schur indicator. It's essentially the order of the T matrix, or more physically, the spins are some roots of unity. Thetas are the exponentials of the spins. There are some roots of unity, and this is the minimal integer, such that all these powers are 1. So there is a series of length spaces. If you were able to compute their phases through this formula, the phases of these partition functions, you would find very nice necessary conditions for the existence of edge modes, which are massless. So this provides essentially a list of higher central charges, of which the chiral central charge is the simplest example, which you obtain by plugging n equals 1. And these are all non-trivial obstructions to gapped boundaries. You can check that they work in examples. You can ask if this list of new chiral central charges is complete, namely if it's a necessary and sufficient condition. So in general, the answer is no. But for abelian theories, we found a slight enlargement of this list of new chiral central charges, which are complete. So they're necessary and sufficient. So instead of just looking at the length spaces with index n that satisfy this condition, you can look at length spaces satisfying a slightly more general condition, and you can prove that this is complete. So given any abelian theory, you fit it into this machine, and this provides a necessary and sufficient condition for having protected edge modes, even if the chiral central charge vanishes. I'll finish with listing just a few fun facts. So you can prove that every abelian theory, if you stack it 8 times, you take 8 copies of it, it always has a gapped boundary. This is a mysterious correct result. However, as I said at the beginning, some non-abelian theories do not enjoy this property, and any number of times you would stack them would still not lead to a gapped boundary. There is also a curious symmetry that we have found in abelian theories between the K matrix and the linking matrix, which defines the surgery manifold. I won't talk about it, I have no time, but it sounds like it's related. It can be understood through the 3D correspondence. In fact, many things that we found look like they could have a geometric interpretation from the 3D correspondence. And finally, a fun fact that is useful to remember is that it's easy to prove from this formalism that every abelian theory that has a gapped boundary is actually a discrete gauge theory, a discrete abelian gauge theory, and vice versa, every discrete abelian gauge theory has a gapped boundary. That's not true for non-abelian theories. So just let me conclude. There is a list of very natural generalizations of the gravitational anomaly chiral central charge of Alvarez-Gomes-Witten. They're computable. This list is computable. We know we have a formula for these chiral central charges like this. These are the phases of this combination, where theta are the spins and d are the quantum dimensions of the anyons. And they provide rigorous obstructions to having a gapped boundary. To prove that this is true, you must study properties of this anyon curly A. And so this is a natural extension of the chiral central charge, which would be nice to understand better. I'll now quickly go over 5 questions that remain open. So as I said, for non-abelian theories, we were not able to find a complete set of chiral central charges, complete in the sense that it's necessary and sufficient. So we have not been able to do that yet. But for the abelian theories, we've succeeded. So it would be nice to complete this program for the non-abelian case. Also, another thing that I mentioned in passing is that sometimes there is more than one gapped boundary condition, such as in the Z2 gauge theory. It would be nice to count them. There is also a very interesting and canonical question about the interplay between boundary conditions and symmetries. So even if some theories have gapped boundary conditions, if you want to preserve some symmetry, you might not have any gapped boundary condition. So it would be nice to understand if this can be, these obstructions can be measured by some yet new central charges. Probably a very difficult question is to understand what does it mean to condense this non-abelian anyon A, which appears naturally when you have a gapped boundary. So to understand what's inside this tube, we must condense A. We know how to do it algorithmically, but not in a very nice path integral formulation. And that's very annoying. And finally, this whole talk, even though I didn't say it very clearly at the beginning, was about bosonic theories. And there should be extensions to spin theories of many things that we found. For those of you interested in the relationship between this talk and Jaume's talk, there is a very telegraphic slide at the end, which you can look up. But I'll just leave this slide for now. Thank you.
Okay, Zohar, thanks very much for this very nice talk. So we have a few minutes left for questions. Are there any questions?
Let's see, there are 19 in the chat.
So I saw a question in the chat. Let me start with that. That was from the, let me see, from the Harvard notes. Let me see how it was. Just a second, there was it now.
I cannot read all of those questions now.
No, but there was a question. I cannot find it now.
Yeah, I can ask the question.
Oh, just ask the question then.
Yeah, so I wanted to ask, so you have this abstraction to having a gap boundary by evaluating the partition function on length spaces. I just wanted to know if this kind of abstraction, do you know if it generalizes to higher dimensional setups, to higher dimensional TQFTs? Like if I have, like a TQFT in, I don't know, in 5 dimensions and I evaluate it on a length, I evaluate partition function on a length space and the face is non-trivial, then I know I cannot have a gap boundary or not.
I think it's probably a very good question. I was thinking about it while you were speaking. I cannot come up with an intelligent response on the spot. I have to think about it.
Okay, thank you.
The proof that we have for these statements involves at many points properties of 2+1 dimensional topological filters that I'm not sure generalize. So I have to think about it.
Okay, thanks.
Okay, there's a special request from Pedro Zohar. He says, I would like to see the last slide. Maybe Zohar could show it while replying to the other questions. So maybe you could show the last slide.
There is another question I see, but I cannot see from home.
Yeah, there is a question by Ed. Can you ask the question, Ed?
Me? Yeah, my question was, it's a mixture of a question and a comment. You have this equivalence relation involving gap boundaries. I wonder if we can visualize it as follows. Think of the boundary as existing in time. So we're trying to change the Hamiltonian of a system, transforming it from one TQFT to another while preserving the gap. And then a gap boundary suggests that we can transform one into the other, changing the Hamiltonian, keeping the gap. Do you think that interpretation is correct?
I think it's 100% correct.
Okay.
In the mathematical literature, they never talk about a gap. They talk about topological interfaces in topological filters. But the condensed matter interpretation is, of course, that we actually have a Hamiltonian that flows to a topological filter, and we try to change the parameters continuously while never closing the gap. So there's a small jump that I've not emphasized. The notion of gap and topological we should think about them carefully. It seems clear that they are the same, but the notion of gap is something that requires a Hamiltonian, while the notion of a topological interface or a topological boundary does not require a Hamiltonian. It can be phrased purely in the language of fusion categories or braided categories.
Thanks.
Okay, there is also a question from the Weizmann notes. If the two-dimensional CFT with higher central charges have consistent boundary conditions, like it is so for the gravitational anomaly.
I didn't understand the question.
Well, maybe can the Weizmann notes ask the question by unmuting?
Hi, sorry. No, I was trying to ask if the 2D CFT has higher central charges, does this have consistent boundary conditions and all? Like if your 2D CFT has gravitational anomaly, you don't have boundary conditions. So I was asking generalization for the high central charge.
Okay. You're asking a question about these two-dimensional relative or non-relative theories, whether they themselves have boundaries. Okay. I believe this question should be approached with care, because given that many of these theories where the higher central charges are non-vanishing, or the chiral central charge is non-vanishing, they're relative theories. They require some of them are relative theories. They require a bulk. So the question of a 1+1 dimensional, a boundary which is 0+1 dimensional, you have to think about it carefully, because this must extend now into the bulk. So I have to think about the setup in which this question can be asked, consistently. So I don't have anything intelligent to say now.
Thank you.
Okay, are there any more questions?
In 11 dimensions? Oh, I see. Do we know what happens in 11 dimensions? I assume this is in the context of the swamp plane, which also requires the existence of gapped boundaries. question. Okay, thank you.
Okay, any further questions or comments? Well, if not, then let's thank Zohar again for this very nice presentation. And this is the end for this session. And we will start soon then with the discussion session by Seiberg and Wen.
No, not soon, right now.
Well, I mean, right now, that's what I mean by soon.
Very good. So we want to start at exactly 20. So in this 1 minute, let me just say a few words. Well, first, let me thank Jaume and Zohar for beautifully giving the example and sticking to the suggested time perfectly. And let me remind you that the idea of these discussions, Nati and Xiao-Gang will give us 20-minute introduction to prime us. And thankfully, they already sent us the PDF. So for the non-experts, do check out, I hope you checked out the PDF beforehand to motivate yourself to think of questions. Speaking of which, Nima.
Are we connected?
Pedro seems to have been disconnected.
Am I connected?
Yep.
Yeah, we hear you.
Nothing. So I can take over until Pedro comes back. So I guess he was going to say you now have 20 minutes. So Nati, are you going to go first?
Yeah, I'm going first. Can you see my screen and pointer?
Yep.
And can you hear me? I assume you do. So first, I'd like to thank the organizers for this fantastic conference, which was subject to almost impossible boundary conditions. So I really congratulate them for this heroic achievement. And this is the first presentation Xiao-Gang is going to follow. And since we're going to have some kind of a bird's eye view of where we are and where we are heading, and I have only 10 minutes, I decided not to have references on the slides. We have had enough references elsewhere. Otherwise, it will clutter the slides and the presentation. So the first question I would like to address is, why should string theorists care about this topic, the topic of phases of matter? And in fact, over the years, I've heard many senior people, very famous physicists, making comments like the following: condensed matter physics is not fundamental physics. String theory is fundamental physics, but condensed matter physics is not, and therefore I'm not interested in condensed matter physics. Another comment I've heard many times is that quantum field theory is already fully understood. There's nothing new to be discovered in quantum field theory. Quantum gravity is the real frontier, and there's no reason to pay attention to quantum field theory. Well, the first comment I would like to make is that I strongly disagree with these two views. Looking historically over the last several decades, we have seen deep and productive cross-fertilization between condensed matter physics and high-energy physics and string theory. I think it's fair to say that almost every idea in high-energy physics or string theory either had its roots in condensed matter physics or had implications in condensed matter physics. And I prepared slides, which I'm not going to show, with a long list of examples. Based on this past track record, I expect developments in condensed matter physics to inspire more developments in high-energy physics. And for this reason alone, I think string theorists should be interested in the subject. In addition, and this is in addition to the intrinsic interest in the subject. Since this is a discussion session, I could focus on many different aspects of the topic, and I decided to focus on a particular aspect, and Xiao-Gang is going to focus on another aspect. And the aspect I'll focus on is something that has appeared in many of the discussions and presentations in this conference, including beautiful presentation by Jaume earlier today. And this is the question of separation of scales. It appears in all of science, including physics. In philosophy, it's known as reductionism. In quantum field theory, it is known as the renormalization group. And this is the statement that physics of phenomena at one length scale are almost independent of phenomena at shorter distances or at longer distances. This didn't have to be so simple, but it is a fact that this is true. And ultimately, this fact stems from the fact that physics is local. Locality means that what happens at different scales is almost independent. More technically, we started short distances by some theory in the UV. It can be on a lattice or in the continuum. And then we describe what happens at long distances in the IR using an effective universal description. And it's effective because it is independent of most of the details of the short distance theory. And that another reason it's effective is that it's very useful. And this picture has been very useful in two directions. First, quantum field theory that appears here in the IR allows us to classify and organize all possible phases and also the transitions between them. So this is an application towards condensed matter physics, but also in the opposite direction. New physics, new phases teach us something about quantum field theory. So this has been a dominant paradigm in physics in general and in quantum field theory in particular over the last several decades. However, there are some notable counterexamples which I think should be highlighted. I think that we can call them all UV-IR mixing. This is what characterizes them is that separation of scale breaks down. And there are some long distance, low energy phenomena that reflect high energy physics. We've seen some of that already in this conference, reflecting the fact that this is common in gravity. In gravity, if you try to localize a lot of energy in small volume in order to probe what happens at short distances, instead of probing the short distance theory, you create a large black hole that hides the short distance physics. So this is well known and it appeared in some of the discussion sessions. Also, dualities in string theory relate small distance and large distance. T-duality is the prime example of that. And also many questions and confusions in quantum gravity circle around this issue and the issue of locality, and I can point to the information discussions and to other discussion sessions here. Now, somebody could say that in the context of quantum gravity, space-time will ultimately be emergent. And if space-time is emergent, the notion of distance is emergent. And therefore, we shouldn't be surprised that long distances and short distances are mixed together because the whole notion of distance is going to be an emergent approximate concept. How about theories which do not involve gravity? Well, we have some examples which provide counterexamples to the separation of scale paradigm, also come under the name of UV-IR mixing, and they arise as follows. First, we can start with string theory and turn off Newton's constant. If we turn off Newton's constant, we have a non-gravitational theory. That has been a very productive and useful machine to produce quantum field theories, and we heard about them in many talks in this conference, including the talk earlier today about the 2-0 theory and its compactification. All these theories are standard quantum field theory, but in certain peculiar examples, what this machine produces is not a standard quantum field theory because it exhibits UV-IR mixing. Let me mention two prominent examples. The first is a little string theory, and it's characterized by having no local operators and T-duality. These two facts reflect the UV-IR mixing. T-duality means short distance and long distances are the same, and no local operators prevent us from exploring things at the point. Another example is the example of an ordinary field theory, but not on a commutative, but on a non-commutative space. One way to think about it is to say that the degrees of freedom of the theory are dipoles. And if we give the dipole high momentum in the x direction, it actually grows in the y direction. And therefore, the interactions do not lead to separation of scales. The UV-IR mixing is prominent here because as we try to make high momentum in one direction, the space grows in the orthogonal direction. The same phenomenon appears also by computing loop diagrams. And when we compare the theory on the commutative space to the theory on the non-commutative space, the theory on the non-commutative space has fewer UV divergences. And these UV divergences that we lose manifest themselves as new infrared divergences, again reflecting UV-IR mixing. In fact, I think that the phrase UV-IR mixing first appeared in this context. Another example appeared more recently, not out of string theory, but examples from lattice models. And I like to call them exotic lattice models, exotic because they have this UV-IR mixing, sorry. They include model of fractals, but also some models without fractals. And the characteristic fact about all these models is the subsystem symmetry, which eventually leads to the UVIR mixing. This was summarized beautifully by Shu-Heng this morning, so I'll be here extremely brief. The main point of a system with subsystem symmetry is that different submanifolds of space have different group elements. So we have a huge symmetry group where the group element is labeled by a position in space. For example, we can act on the XY plane at different values of Z, and different values of Z correspond to different group elements. So we have a huge global symmetry group. Since this is a global symmetry, operators and states must be in the representation of this subsystem symmetry. And if we have a huge group, the representations could be huge also. And as a result, there could be a very large ground state degeneracy. Ground state degeneracy that depends on the number of lattice points. This is very unusual in continuum field theory. In fact, it's almost impossible in continuum field theory where the number of ground states is finite. Also, the observables of the system are constrained by this enormous symmetry group. And if we have operators that are charged under the symmetry and we balance the charges and we have a non-zero correlation function, we can move one of the operators a little bit. And as we move the operator in space a little bit, the correlation function does not balance the charges. And as a result, the correlation function is zero. So correlation functions are going to vary on the lattice scale, even in the continuum limit. All these really manifest the UVIR mixing. If we try to incorporate that in a continuum quantum field theory description in order to describe the long distance behavior, we must use discontinuous fields, which is really opening a Pandora box. I'm not going to discuss it here. So let me end this presentation with a list of questions and challenges that I hope will provoke interesting discussion here. The first question is, what is quantum field theory? We know many formulations of the theory. We can start with continuum Lagrangians and perform perturbation theory or non-perturbative calculations. We can use lattice, bootstrap, integrable theories, have some solutions. There are some string constructions, etc. None of these formulations is perfect. Every one of them has its issues. But the main point is that none of these formulations really cover all cases. Sometimes we have the lattice, sometimes we have a string construction, sometimes we have a lattice and so forth. I feel it's important to look for other formulations. Other formulations will give us both deeper understanding about what's going on here, will also lead to new theories, as new theories are constantly being discovered, and more pragmatically, they will lead to new methods to perform calculations. Another aspect of it is that we should look for generalizations of quantum field theory. I highlighted here UVIR mixing, and I gave some examples. But for all I know, there could be other interesting theories, non-gravitational theories, that go beyond the standard framework of quantum field theory and will force us to generalize it. So I think I'll stop here and let Xiao-Gang continue. Thank you.
Thanks, Nat. So Xiao-Gang.
Okay, just as Nati said, I'm going to give another example of a very close relation between string theory and the condensed matter theory. And the relation is so close, so actually I can give my presentation using a slide from a string theory. So here I'd like to thank Erin for her excellent talk and slides. And so this basically some kind of like a strong planned program in condensed matter physics. So a big question in condensed matter is that which effective field theory describe a condensed matter system? Can we classify them? More formally, we can ask what kind of effective field theory have a UV completion in so-called local qubits model. Yeah. For the time being, we'll say without symmetry. So in this presentation, we just ignore symmetry. Also, we ignore the fermion. So the qubits really means a bosonic model. Okay, and certainly not every effective field theory can be UV completed as a local qubits model. Okay, so there may be anomaly cancellation and maybe there's other additional constraints. So that is the issue. And in string theory or in quantum gravity, we like to have effective field theory, which is weakly coupled to Einstein gravity. And but in condensed matter, this condition is more relaxed. So anything with emergent gate theory also be very interesting, or emergent fermion, even though we start with a bosonic model. And even an emergent complete standard model. So that's connect this qubits model to particle physics. Or can we have emergent graviton? You know, so all those when you have those properties, so that this effective field theory became more interesting. Okay. For the emergence of graviton right now is probably still kind of open. We don't have example with emergence of a Lifshitz gravity, which is linearized Lifshitz gravity, but not Einstein gravity with a linear dispersion relation. And when you have this, so with those emergence interesting field theory, so in condensed matter, it was called a new phase matter. Okay. And if this interesting field theory have an energy gap, then we call them have a topological order. So actually, this name of topological order is motivated by Witten's Jones polynomial paper, and this which is it's a paper which gave rise to the topological quantum field theory. So that's really the motivation to name topological order. So so in this strong-planned program in condensed matter, so there's similar thing like a landscape, which is a consistent a field theory which is consistent with the lattice qubit model, local qubit model, and there's a strong plan which is more is inconsistent. So there's something something wrong. So the key words here that those, even though for the field theory in a strong plan they are apparently consistent, you know, but somehow it's inconsistent. So what that really means. So so in condensed matter, there's a way to give this apparent consistent a more concrete definition. That is apparent consistent effective field theory can be viewed as a boundary of a local qubits model in one higher dimension. If these local qubits model are in a trivial phase, and then this effective field theory on the boundary will be in the landscape. Means this effective field theory actually have a UV completion in a lattice model in the same dimension. However, if this lattice qubits model or local qubits model are in a non-trivial phase, topological ordered phase, and then the boundary will have abstraction to have a qubits realization in the same dimension. So this is so therefore this question of strong plan and the landscape can be answered very directly using this one higher dimension of this holographic point of view. Okay, so this is very much sounds like an anomaly, you know. So this holographic point of view basically says that this bulk topology order in the bulk of quantum liquid is an abstraction for effective field theory to have a local qubits model UV completion in the same dimension. Okay, but this really sounds like an anomaly. And but somehow want to say that this anomaly actually is more probably called as a generalized anomaly. That is this strongness correspond to so-called generalized anomaly, which actually correspond to a bulk topology order. And so within this holograph picture, the usual anomaly is correspond to bulk invertible bulk topology order, which can be cancelled. So there's an anomaly cancellation. So all the this invertible gravitational anomaly, I think, is kind of more narrow sense, more usual anomaly we'll talk about. But however, from holographic point of view, most topology order in one higher dimension are not invertible. So their boundary probably can be viewed as a generalized anomaly. So this really led to a very strong interest in gravitational anomaly in condensed matter theory, although in condensed matter people don't discuss gravity, but gravitational anomaly is a very good concept to understand which effective field theory can come from lattice model or qubits model, which effective theory cannot. And also we like to have this anomaly-free condition. So what are the anomaly-free conditions for this generalized anomaly? Again, we see a very strong connection to study in string theory. And one of anomaly-free condition in string theory in Swampland is a completeness hypothesis, but in condensed matter is called remote detectability principle. So that means every excitation can be remotely detected by other excitation by braiding remotely or some other operation remotely, which two excitations do not touch. So in order for effective field theory to be realizable by qubits model, their excitation should have this kind of remote detectability principle. Okay, and then another is a relation is again in string theory. There's a cobordism conjecture, and so that's if you translate that into the into condensed matter, they really say that all the effective field theory coming from a lattice model can connect to trivial phase by domain wall. Means it can have a boundary to the trivial phase, to the vacuum. Okay, and also if two effective field theory cannot be connected by domain wall, that means they have a generalized anomaly, and their generalized anomaly are different. So their different generalized anomaly means they cannot be connected. And so that's really from holograph point of view. That means because you have non-trivial bulk, the boundary would extend into the bulk. So that's why at the boundary they cannot be connected to each other. So all these are really related. And similarly, there's a notion that there's no global symmetry in quantum gravity. And but in condensed matter, this became a little bit of a trivial statement. That means no global symmetry in qubit system without any symmetry, because we try to replace quantum gravity by qubit system without any symmetry. But however, this statement actually is a little non-trivial because the low-energy effective theory of a qubit system may have an emergent global symmetry. But this emergent global symmetry should be all behave like a gauge symmetry. Or actually, it's not really there. It's just approximation. And then because of the topologization can have all kind of dimension, point like, string like, and etc. So therefore, this emergent symmetry can be very general. And as Shu-Heng talked about in his talk. And the most general version at the moment, we see that is described so-called algebraic, is algebraic higher symmetry, or it's a mathematical foundation. It's a fusion higher category theory with a fiber functor. And this something replace group or higher group. So there's so this connection to the mathematics also very very important. So here's my summary. This is just my last slide. So just summarize this very close connection. Thank you.
Thank you very much. So people can, of course, raise their hand to ask questions. But there was a question in chat, which just a naive question that I also have by Charles Wang. So the question is, if you just find some condensed matter state in the wild, so in the real world, would you expect it to be described by a local qubit model, or would it have to be?
The answer is yes and no. Okay, in condensed matter, the most system we're interested in is an electron system. So it have a fermion with a U1 symmetry and maybe with a gate interaction. But however, if if you only study interest in the quantum magnets, we call this quantum spin model. The quantum spin model really is a qubit model. So actually, so in my presentation, I mainly talk about the possible effective field theory from a quantum spin model or from these quantum magnets. Okay, but for the metal and the conductor, one should generalize this a little bit to consider a fermionic model, a local fermionic model. So that's another thing.
Thank you. So Shu-Heng, you had the question or comment?
Yeah, Xiao-Gang, thanks for the nice presentation. So you discussed this notion of local qubit model without symmetry. I'm just curious, if I take a single qubit, so two state, and with a trivial Hamiltonian, is that in your swampland or it's not?
No, it's the single qubit is already a qubit model, so it's in a landscape.
But
and so the swampland really is referred to some kind of effective field theory, which is whose definition is not so complete, and in some sense, okay. And then we ask whether this effective field theory can be realized by some local qubit model as a low energy effective theory or not.
But a single qubit has a 't-Hoof anomaly. Right? A single qubit has a SU2 global symmetry, but realized projectively as SO3.
Yeah. So that would be okay. Yeah, that's a very good question. So that would be another issue. So here I'm talking about the local qubit model without any symmetry. Okay, and then there's the previous question is about the. Maybe you should consider local model with a fermions. Fermions have this Z2 fermion parity symmetry. And then the classification of a swampland as landscape will be very different. Now you're asking, if you have a qubit model with some symmetry, then its corresponding swampland landscape also became different. And that's really very interesting question, because most condensed matter systems do have a symmetry. The qubit model do have a symmetry.
Right.
So then the definition of swampland and the landscape shift again. So this really, this really corresponds to study of anomaly, gravitational anomaly, tooth anomaly. But here I want to emphasize that all those anomaly study have the more general point of view using swampland landscape picture, using holographic picture, and that's maybe is a more general way to view all those anomalies. Yeah, that's my point. Yes.
Okay, thank you.
Zohar?
Thanks. I actually have a short question to both speakers. So for Xiao-Gang, isn't the generalized anomaly exactly what I talked about? Isn't this the higher central charges? This is the situation where there is a non-trivial topological theory in the bulk.
Yes.
The edge modes are protected by higher central charges.
Exactly. And so if I rephrase your results in this holographic picture, it means that the anomaly is about topological order there are several to say that who is this topological order is a commuting projector model. Okay, that's one way to realize. Another way, mathematical way to realize that this topological order is a Drinfeld center.
That's right.
Yeah. And
but the Drinfeld center criterion is extremely difficult to check algebraically. So the point is that you can just measure the phases on length space partition functions, and
so that's why I think this length space indicator is really impressive. Yeah, I'm really glad to learn this.
Well, thank you. Can I also ask a very short question to Nari, or should I wait?
No, go ahead.
Yeah, go ahead.
So just as a general thing in EFT and in effective field theory, the way I understand it is that it's an expansion in some separation of scales, right? I mean, it captures and it gives you some asymptotic series in some ratio of two scales, and maybe sometimes you can get non-perturbative effects from effective field theory, but that's usually difficult. Now, if there's UV-IR mixing, what is the point of effective field theory? What is it generating for you? Which expansion?
So I don't know a general answer, but I know I can answer it in specific context. So in the little string theory is well defined and there are observables. And it is separated from the underlying string theory. This is the expansion, and there's a well-defined theory, and people computed some observables in this theory. The problem is not with that. The problem is that the theory as it stands does not have UV-IR mix. It does not have UV-IR separation if you look at it at short distances. The same is true for the theory on the non-commutative space. There's a well-defined theory, There is a perturbative expansion. Say if you look at say phi to the fourth, and people even prove renormalizability. So the same thing works, and you can compute various things. The surprise is that some UV divergences become unexpected infrared divergences. But there's nothing wrong with the theory, just that it does not fit your general framework. The theory describes everything, both the UV and the IR, and we don't have this separation if you try to take the answer and slice it apart. And the same is true with these exotic models, that there are correlation functions that can be computed using the theory, and they exhibit peculiar features. Let me give you an example. There are correlation functions between operators at separated points. Everything looks nice. And then, say, in infinite volume, but at special non-coincident points, there are divergences. So two operators at different points, and you move the points, they suddenly a divergence. A divergence that can be regularized by putting the system in finite volume. This is a typical UV-IR mixing. There's a singularity when one point goes to a specific point, even though there's no operator there, and it's cut off by the size of the box. The size of the box is infinite, the answer is infinite. And on a case-by-case basis, I can give examples. I do not know a general framework. I do know that this does not fit the standard picture of the Wilsonian renormalization. And I really wish I understood it better. That's why I think I picked this topic for a discussion session. I did not report a result of a topic I understand, but I bring it more as a question to point for future research.
Thanks. Kumar?
Yeah, thanks for the talks, both Nathy and Xiao-Gang. I have a question for Xiao-Gang. So your parallel that you're drawing between local qubit models and the quantum gravity and swampland issues, is that just a parallel, or you really view local qubit models is a way to think about quantum gravity? What is your take on that? Is it just analogy or more?
Yeah, at the beginning, I thought it's just analogy. And because it's a two parallel theory, two different theories, there's a similar analog. But then after hearing the talk in this conference, and then this parallel is so amazing because of this swampland landscape point of view for quantum gravity, and the similar this local qubits model, it's such a strong parallel. So I cannot help to think maybe these two are the same. So I don't want to really say that, but I really want to entertain this idea. Maybe the two are the same. So basically, or maybe I'll put another way. So because the condition for swampland and landscape, whether there is a difference from quantum gravity point of view and from this condensed matter point of view, can we find some condition which they are really different? So then that really means the two theories are really different. But I don't really understand a swampland from string point of view very much. But from a little bit, I understand the similarity is striking. So that's part I want to emphasize. But it would be really interesting to see whether there's some anomaly-free conditions which are really different from effective field theory from quantum gravity or effective field theory from qubits model, whether they enjoy really different anomaly-free condition. That's the question, yeah.
One question I have in that analogy is that in the swampland, we expect that the theories that you get in the EFTs that you get for quantum gravity are measure zero compared to all the allowed ones. Is that the same for the local qubit models or not?
You mean landscape as measure zero from this swampland?
Yes.
And yeah, I would say sometimes it's hard to define what to measure, but in general, yes. And the boundary for, okay, swampland belongs to boundary for topological order in one higher dimension, and the possibility of topological order in one higher dimension is infinity. So therefore, the landscape is a boundary for trivial topological order. So that's a one from infinity. So in that sense, it's a measure zero.
Nice. Okay. Thank you.
Irene?
Yes. Yeah, so first, thank you so much, Xiao-Gang. I really loved the analogy and the slides. It was very fun. And I found it super interesting. I mean, I think indeed there are many analogies. And also from Nati, like the UV-IR mixing, I think this is another topic which we deal a lot with in the Swampland program, because we precisely try to understand this quantum gravity imprint at low energy. So it's precisely try to understand this, whether there is a UV-IR mixing imposed by quantum gravity that goes against the Wilsonian effective field theory approach. And I had a question for you, Xiao-Gang, more concrete about one of the things you said. I didn't understand very well the analogy with the completeness hypothesis, like that seems that it has to be complete, otherwise you have some anomaly. I was wondering if you can elaborate a bit on that.
So actually one example for this is following. Let's consider a purely Feynmanic model. Or maybe let's consider this standard model. In a standard model, we have a neutral fermion that do not couple to any gauge theory and gauge field. So that means that this neutral fermion, like a neutron, for example, cannot be detected by braiding with a gauge flux. Yeah, there's no gauge flux which you can detect this neutral fermion by braiding. So from that point of view, the standard model is incomplete. It's anomalous. It belongs to swampland, basically. From this qubit model point of view, at least belong to swampland of a qubit model. And so if you believe this qubits unify everything, produce elementary particle, then that's a prediction that there must be additional discrete gauge theory, which produce a gauge flux, which allow you to detect neutron by braiding. So there's new cosmic string. And so this is mathematically, this is more or less established. So in order for something to be realized by the local qubits model, all the topological stations should be able to detect each other. I think this is really analog to the completeness hypothesis. Yeah. So that's one of anomaly free condition. Yeah. Since you also mentioned this UV-IR mixing, I just want to mention that there's a so there's a proposal that there's a symmetric tensor gauge field coming from fractons. Fracton with this UV-IR mixing and the symmetric tensor gauge field is very close related. And so one may have a similar thing in the swampland landscape, because the fracton phase have energy gap, which can be served as a bulk topological order. And their boundary will belong to the swampland with UV-IR mixing. So that is one way to think about it. The boundary of a fracton phase belong to swampland with a UV-IR mixing. That's so that's maybe the so you have these two topics combined. These two topics, there's something. Yeah.
Do you have examples of fractons in string theory? Maybe someone already said it, but I missed it. Is there any clear example of a fracton appearing in string theory compactification?
Yeah, I don't know. Yeah, but just
people try to construct fractal models using string theory by stacking D braids.
Nice.
So, but I do not know how far this could be pushed. So basically, there are layers of D brains, say the XY direction, XZ direction, and YZ direction. You have stacks of them, and they couple to each other. And then there's restricted mobility because of the structure. Some particles are constrained to be on one of the planes or the intersection of the plane. And there are various variants of this idea. But so as far as I know, usually string constructions are helpful because you take a problem that you don't know how to analyze in ordinary field theory. You give the brain construction, and then it's easy to analyze using the braids by drawing pictures. This is when it's effective. In these examples, as far as I can see, it is exactly the opposite.
Yeah, I just want to mention that in incandescent matter, people try to construct a theory with emergent gravitons, but nowadays when you're looking back on those theory, surprisingly, those theories actually are fractal models. So, but at that time, around 2006, we don't see this connection. So it just say, oh, there's some theory with emerging the symmetric tensor field. But looking back, those are actually fractals. So I should, this would be really, really intriguing whether fractal have something to do with quantum gravity.
So Harvard Node, you were waving. Do you want to skip? So we'll come back to Johanna after. Go ahead.
Yeah, I was just wanting to follow up on Xiao-Gang's response to Irene. But so you were mentioning the neutron, and you're saying that the standard model was kind of incomplete because you're going to detect neutron from far away. But the neutron is unstable. So I wanted to ask if this remote detectability hypothesis for condensed matter would also, does it work for literally every lattice excitation that I can have, even if it's something that is decaying to something else? I should still be able to detect, every.
Yeah. A neutron is unstable because it can decay into proton and electron. So I can think about hydrogen atoms. So it became hydrogen atoms. So hydrogen atom is no, not hydrogen atom is actually, sorry, it's neutron to not, you have neutrino, I'm sorry. So I'm thinking maybe like a helium-3, let's say helium-3. So helium-3, let's assume it's stable. Then it's still neutral fermion.
Good. I just wanted to ask, like, this remote detectability is just about exactly stable stuff. Okay.
No, it doesn't matter exactly stable. So as long as you have so just a neutral, basically neutral composite fermion is a sign of a swamp land, basically.
But so the claim in a lattice model, like the claim is that I can detect any excitation in a lattice model from far away, even if it's.
Yeah, that's right. Okay. If it's that theory coming from a lattice qubits model, the statement will be different if your lattice model have intrinsic fermion. Then the standard model can be realized by this intrinsic fermion lattice model. But then you have to assume you have a fermion to start with. But if you assume you have if you prefer strong localness, so we only have a qubits, nothing else, then the emerging standard model have some constraints.
Okay, thanks.
Johanna?
Yeah, so I have a quick comment about gravitational anomalies and then another question to Nati. So the comment about gravitational anomalies that were discussed, I just wanted to mention quickly that they, of course, play an important role also in a different context of relating string theory and condensed matter, which is that they contribute to the hydrodynamic expansion as studied in applications of the ADS-CFT correspondence to such systems. And indeed, as being present in this hydro expansion, they have actually been studied by experimental condensed matter physicists by looking at the divergence of the entropy current. And so there's really effects of these gravitational anomalies which can be measured in the lab. I think somebody asked about experimental contacts. So there's quite a few experimental contacts of all these ideas. But really, I have a question to Nati. I mean, we already discussed quite a lot UV IR mixing and fractons, but since you mentioned that you would like to see an extension of QFTs now in the context of discussion, can you give another example of an extension of QFT that would be relevant both for high energy physics and also condensed matter?
The quick answer is no. I mentioned 3 examples, and I know 3 examples, and honestly, I don't know what to make of them. I'm totally baffled by it, but I don't think we can deny that they exist.
Mm-hmm. So what are these?
Somebody could dismiss all these examples as saying not being relativistic. And if you want to study only relativistic theories, maybe one can prove that this cannot happen, and then we don't need to address this question. I think that this view would be too narrow. I think that these models are trying to tell us something, but I have no idea what.
Okay, so it's a question for the future then.
Instead of the audience asking me, I'm asking the audience.
All right, thanks a lot.
Kobe?
Yeah, since the topic is new phases of matter, I would like to point out another new phase of matter that we considered recently. It is with Vadim Kaplanovsky in Mati Jarvenan, and the point is that phases of matter are not only determined by symmetries and anomalies, but also by the dynamics. So what we considered was the case of nuclear matter. Nuclear matter in large N is necessarily a crystal. In holography,
like in the Sakai-Sugimoto model, nucleons are instantons of flavor symmetry. And one can get quite easily the analog of the Skir model for the properties of a baryon or a nucleon. But the question is what happens to nuclear matter? And so for that, you have to analyze lattices of nucleons, which means to solve the ADHM equation, which is very complicated. But what we did, we approximated it to a two-body interaction based on this ADHM equation. And from that, we were able to determine the phases of the system, which are in fact very rich and complex. So there are all kinds of phases depending on the different weight of the non-abelian interaction. So I recommend people to look on that point, because I think that non-abelian lattices, not necessarily in the context of nuclear matter and instantons, may be also relevant to various different condensed matter systems. And we have developed techniques to analyze these phases. Thank you.
So Steve Schenker had a comment that maybe he wants to say out loud. If not, I can read it.
Sure, I'll say that. I just wanted to, in this topic of extensions of local quantum field theory, there's this very interesting phenomenon, I guess, first pointed out by Zamolodchikov, of the TT bar deformation of a conformal field theory. That seems to have various non-local aspects of a quote unquote kind of continuum theory. And it doesn't seem to have some strong UV-IR mixing. The higher energy doesn't seem to make the length of the shortest length bigger. But nonetheless, it does seem to be something that goes beyond local quantum field theory. There are pictures where it has something to do with like points becoming little rods. But it seems like it might be a nice example to try to understand there's holographic kinds of interpretations of sort of understanding some self-contained formalism for what it is. It doesn't seem obviously gravitational either, but it does seem to be something beyond the typical kind of quantum field theory rules that we're used to. That I just wanted to raise it and wonder if people had ideas about how one should think about it.
So are there any comments on that? Okay. Andy, you had a comment on that?
Yeah, Nadi, maybe you would go even further. Would you say quantum gravity is an extension of quantum field theory?
I think the answer is yes, but perhaps this answer is not very useful. Honestly, if I had, well, speculations are free, so I'll try to make a speculation. There's one structure which includes both quantum gravity and quantum field theory. Sometimes they are the same, like in ADS. Sometimes we need to go a little bit beyond, sometimes not. But it's surprising that we already, by asking about systems that are not gravitational, we have a lot of hints that the standard framework that we have does not describe all cases. Now, I do not know whether these examples are very special, but it is a fact that all these examples that I mentioned are examples that I think to some extent also the TT bar example that Steve mentioned. These are examples that people stumbled on. They did not try, people did not say, let's look for a model which has UV-IR mixing, or let's look for a model that violates the standard paradigm that we use. Instead, people explored something and they stumbled on these examples. And that's common to all these examples. The way I view it is that it might very well be that there are many other examples like that we haven't yet stumbled on. And once we have more examples, maybe somebody will get a clear picture of what's going on here. It could also be that these examples are very esoteric and they send us in the wrong direction and they're very misleading. But that's what's exciting in research. We don't know and we'll explore it.
Nima?
Yeah, I have two questions. I think one of which was alluded to already, but I'll bring it up anyway. I guess my first question is for Xiao-Gang. in this idea, when you have gravity, for why we sort of morally think that that the entire charge lattice should be populated, we should have all charge objects and so on. It has a lot to do with black holes and horizons, and the fact that you can make up any solution that you want at long distances, and where without gravity you might have a singularity that would give you a reason to throw it out. With gravity, those solutions can exist, and with the singularities hidden behind horizons. So I guess my first question is there an analogous sort of moral reason that you would expect this in condensed matter systems? I don't see one, but I don't know about the subject. And relatedly, and this is also a more general question even about quantum gravity, but a very basic aspect of this, of the all charges being realized, is are consistent theories of quantum gravity forced to have fermions? And analogously, are condensed matter systems forced to have fermions? I think that's the most basic example of whether the entire set of possible charges is populated. And it certainly doesn't look like all condensed matter systems are forced to have fermions, whereas all consistent quantum theories of gravity we know of do have fermions, at least the ones I know. So anyway, that was my question to you. And maybe I'll just quickly ask the question to Nati, although this again was alluded to. In the non-gravitational examples of UV-IR mixing, I'll put the TT bar example aside because that's funny from a number of points of view. But the ones that you mentioned all involve some breaking of space-time symmetries. Either you break rotational invariance like the Fracton examples, or you turn on a magnetic field like for non-commutativity and so on. Whereas the sort of the UV-IR that mixing that we think is there universally because of gravity doesn't do that. Do you think this is a technicality? You think that might be possible to find examples that are more like the gravitational sort of UV-IR mixing, even without turning on backgrounds or breaking space-time symmetries?
Okay, I'd like to answer the two questions since I was asked the second, but I would like also to say something. Sure. So again, the quick answer is that I do not know. In the context of fractons, I think the main point is not that, but the point that was stressed by the condensed matter people is that at least some of these models, the theory depends not only on the topologies, these are generalizations of topological field theory, but also depend on the choice of foliation of space-time. In their case, it's a foliation of space. And at least for many of the examples, once you have a foliation of space, it's true that you ruin the rotation symmetry, but this is part of the data needed to specify the theory. This is similar to your question about fermions. If you have a theory with fermions, you also need to specify choice of spin structure. Or in a theory without fermions, you don't need to specify. So it's not exactly the same, but it's kind of reminiscent. Regarding the relation to, regarding your point about the completeness of charges, the way I see that, and I think you and I discussed it at length more than once, in quantum gravity, we don't want any global symmetries for reasons that you articulated very well. In condensed matter physics, we think that the short distances, there isn't any symmetry. These may be lattice translation or something like that, but we don't say the system with short distances has an F4 global symmetry, because you have no global symmetry at short distances. And there might be emergent symmetries at long distances, but they will only be approximate, very much like in the context of gravity. For the completeness charges, most of the completeness charges can be the exclusion or the way we argue that the charges are complete are through the gauge charges are complete or through the lack of higher form symmetries, or in a more sophisticated way, the lack of the non-invertible lines, non-invertible symmetries, like the ones that Shu-Heng discussed this morning. And these two arguments of no higher form symmetries and no non-invertible operators exist in condensed matter physics and in gravity at short distances. So in condensed matter physics, because we start from some lattice system that has none of that, and in gravity because this is being postulated. So the details are of course completely different, but the statement of no global symmetry, populating all the charges, etc., seem to be very similar.
Yeah, maybe I just want to add as a, in some condensed matter research, people try to produce a lattice model with an emergent spin-2 field, basically graviton. But those are very kind of limited in the sense, kind of near the flat background. So always near flat background. And at the moment, the only success is emergence of a Lipschitz gravity, with a omega k cube dispersion relation. And but I don't know. Maybe it's interesting to study the black hole in Lipschitz gravity. I don't know, but this whether there's something one can address. So actually, the lattice model with emergent Lipschitz gravity has been constructed, but whether the boundary of phase transition domain wall can be viewed as a black hole in this model, things like this have not been studied.
Okay, any other comments about Nima's questions? Shiraz, go ahead.
Hi. Of the three examples you raised, Nati, two broke Lorentz invariants, namely non-commutativity and the fractons. But the third one did not break six-dimensional Lorentz invariants, right? The little string theory preserves six-dimensional Lorentz invariants. It has other slightly weird features like a continuum of states even when the theory is put on a five-dimensional torus. But it was six-dimensional Lorentz invariant. So I was wondering whether that addresses some of these concerns. Also, related to that, you explained to us how UVIR is violated in the other two examples you studied. For instance, in non-commutativity, something going in this direction becomes big in that direction. What is the analogous phenomenon? Is there a clearly statable analogous phenomenon for the little string theory? Is it just that high energy colliding strings become big, or is it something more?
Well, unfortunately, I do not know how to answer the question. These are the best questions are questions I can't answer.
Okay, Dan, you had a question?
Yeah, I just wanted to comment about this connection between swampland conjecture type things and local systems with the local tensor product Hilbert space in condensed matter physics. So I think that in holography, this connection is quite close because we think that the boundary theory is a local quantum field theory, and in particular, you can study it on a disconnected space, and the Hilbert space has to have a tensor product structure, regardless of what's going on in the bulk. So, I think that analogy has been pretty fruitful over the last 5 or 6 years. You can basically show that at least in ADS CFT, the completeness hypothesis is just a consequence of this fact that the Hilbert space of the dual CFT has to tensor factorize on a disconnected space. I just want to make two comments about that. One is that, the kind of intuitive thing is you can just say, well, if the space-time is emergent, then all the gauge fields in the bulk need to be emergent too, and emergent gauge fields always obey the completeness hypothesis. So that's one way of kind of understanding the connection to what Xiao-Gang was saying. More generally, I think this factorization of the Hilbert space on disconnected spaces with disconnected boundary can be used to argue that there should be no topological surface operators of any kind in bulk. And I think all of these conjectures in some level are just saying there shouldn't be any topological surface operators in quantum gravity, which I think certainly from this factorization point of view is obvious, because if you have a topological operator, you can move it right up to one boundary, or you can move it right up to another boundary. And it's the same operator either way, but in a tensor product Hilbert space, that's not possible. So then finally, just a question to Nati. I know you don't like Lagrangians, Nati, and I know why you don't like them, but if you want to give someone a quantum field theory, it sure is a pretty efficient way to give them a quantum field theory. Can you imagine some other way that's as efficient? I mean, most of the other ways are just like, here's a list of all the correlation functions, which is not very efficient.
So if I can try and answer, I don't think it's fair to say that I don't like Lagrangians. I love them. But as I said in the slides, these are different presentations, and every one of them has its advantages and disadvantages, but none of them is universally valid. So I do not even know how to write a Lagrangian, say, for the 2-0 theory. Yeah. So this is not going to work there. Also, many of the integrable systems solved without ever mentioning an underlying Lagrangian. The connection to a Lagrangian is often described only after the fact. Once you look at the solution, you say, aha, this solution is a solution to a particular Lagrangian system. Now, I'm making blanket statements, and there are many counterexamples and so forth, because it's a very complicated setup. All I have in mind is that Lagrangians is not a magic bullet that solves all the problems.
But it would be a pity if we had to make do with the list of all the correlation functions, right? I mean,
well, it would be a pity if this is the final answer, but at least it's correct.
Yeah.
and for what it's worth, it's not correct in the little string theory, because you don't have the local operators. This is just to show that there's still a lot to understand.
Harvard Note, did you have another question? Go ahead.
Yeah, so I have a question for Xiao-Gang Wen. So you've been describing like this very nice analogy between the more topological aspects of the gravitational swampland program and the one in condensed matter. But in the swampland, you also have like more dynamical statements where you constrain kinematic, like precisely constrain kinematic properties of states, like the Wigger-Arty conjecture and stuff like that. And so I wanted to ask if there's something like that in the lattice swampland program, or if this would be a point where we can really see a difference between the two.
Yeah, actually, I don't quite understand your question. Let me see.
I'm just saying that, for instance, in the swampland, we say that there has to be a particle whose mass is lower than its charge in Planck units, something like that.
Oh.
So can we say something like that from the lattice point of view?
In some sense, yes, and but in different aspect. Actually, there are certain, for example, certain field theory in swampland, because it's a boundary of a certain special kind of topological order in one higher dimension, then this field theory has to be gapless. So that's what is we just hear that there's a talk, Zohar's talk, yeah. So it's so this kind of thing appears, and also if there are some field with a low mass, and then there may be separation of energy scale. And when you have a separation of energy scale, and there'll be interesting. That's be very interesting question. So let me say that another way. Suppose you have a lattice theory, and you have a separation energy scale. The low energy effective field theory for the low energy particle alone may be anomalous. There's this well-known phenomenon. And so therefore, if you ignore some high energy excitation, then the original lattice theory became anomalous theory and belonged to swampland. And so actually this is why in condensed matter, the study of swampland is so interesting, because when we have energy scale separation, when you study low energy physics, then the phase diagram dynamics coming from those low energy particles actually belong to swampland physics. And it's better to study them as a boundary for topological in one higher dimension once you ignore the heavy part of the theory. So this may be an effective way to study low energy dynamics. And I think in this, today we hear this for this non-abelian gauge theory. And if you only consider a fluctuation of a gauge field strength, but no charge is allowed, and assuming charge very high energy, then this theory may be anomalous in some sense, and then or may have some different symmetry. So that may provide some dynamics. Yeah.
So there are no situations where we can say something like there has to be like certain kind of charge excitations whose mass is much below the lattice spacing or something like that. So of course, naturally things to happen at the lattice scale. But
yeah, that's what I mean by energy scale separation. When I say energy scale separation, let's consider some particles whose energy much less than a lattice scale. And those particles may give you effective field theory, which may be anomalous, maybe belong to swampland. And under this assumption, you can treat this system as an anomalous theory and treat them as a boundary of some topological order. But once those light particles became heavy, this approximation, this point of view, no longer valid. So then you should not think that way.
Okay, thanks.
Irene, you have to say something?
Yeah, maybe another way to ask this is if you can somehow quantify how approximate the symmetry can be. Like if something goes wrong, if you try to suppress a lot the breaking effects or to have the very small gauge couplings. And I was wondering if maybe you can see it because there is some anomaly, but the gauge field is massive. So as long as you are below some energy scale, seems fine, but then you can get sensitive, I don't know, to when that phase, and then you get sensitive again to some sort of anomaly.
Yeah, it's related to the questions. Let's
Yeah,
consider Z2 gauge theory. Let's consider Z2 gauge theory. And the Z2 gauge charge would have a Z2 symmetry, emergent Z2 symmetry. And but once we ignore the Z2 gauge flux, then we really have a Z2 global symmetry. And but once the Z2 gauge charge, Z2 gauge flux have same energy scale, suddenly we don't have any symmetry. This just became Z2 gauge theory without any symmetry. So I think that was the thing I refer to. But however, those emergent Z2 symmetry in some sense exact Z2 symmetry, I think. And let me see, can I say that? Yeah, because there's a Z2 charge have this Z2 fusion rule, so which is exact, not approximate. Even that's what I'm thinking. Yeah.
So let's go to Greg Moore. Greg, so you mute. Okay.
Yes. I had a small silly question for Nati and then a comment on Nati's first slide. The silly question: if you had a periodic renormalization group flow, would you say that's UVIR mixing?
Maybe, yeah.
Okay. I mean, I have been in talks where people have claimed to make perturbations a little bit like the TD bar, but not exactly where they claimed periodic renormalization group flow. The comment. So you had a list of approaches to quantum field theory on your first slide, and maybe I missed it, but I think you left one off. If you ask a mathematician what is a field theory, then the mathematical community actually has an answer. You might not like the answer, but they have an answer. And their answer is that you have a geometric category of some kind. I could be more precise about what is a geometric category. And it's an N category, it's a monoidal N category. And you have a target category. I see people are smiling, but I think you should take it seriously. And you have a target category, which is also a monoidal N category, and a field theory is a functor from one to the other. And that captures a lot. That captures a lot of the stuff about defects, generalized symmetries, and so on. The Bordism category need not just be a simple Bordism category, which is what you would use in topological field theory. You can have all sorts of extra structure. You can have a Riemannian metric, a spin structure, all sorts of tangential structures. And so that also comes, so that's what mathematicians mean by a field theory. And they apply, that's a very flexible notion. They apply field theory, the ideas of field theory in very remarkable ways. I mean, just look at conferences on the geometric Langlands correspondence, for example. And as people were asking about what are generalizations of quantum field theory? Well, there are a lot of monoidal N categories out there. That gives you a lot of generalizations of field theory.
Okay, we're running out of time, so let's just, okay, Igor, you have just a comment based on what Greg asked?
Yeah, actually, yeah, since Greg brought up RG limit cycles, I just wanted to mention if one is willing to accept that quantum field theory, say with ON invariance, continue to non-integer n and say in 3 minus epsilon dimensions, if one accepts this as an okay quantum field theory, then recently Christian Jepsen, Fedor Popov, and I actually wrote a paper on a completely perturbative periodic RG flow. A disclaimer is that it's not a unitary theory. You always have some operators with negatives, homologic type metric, so it violates the F theorem, but nevertheless, it's something that just follows from beta functions computed at two-loop order. And there are various other examples that Christian Jebsen and Fedor Popov are pursuing now. So it's possible completely perturbatively from beta functions.
Okay, let's just finish with the last question or comment of Jake McNamara. Go ahead.
Hi, yeah, my question's for Xiao-Gang. One swamp lane conjecture I don't see analogy in a local qubit model is the absence of free parameters. So I was wondering if you have any comments on that, because in quantum gravity, we expect that every free parameter in the Lagrangian is the VEV of a dynamical field, but I would think that a local Hamiltonian has tons of free parameters, and I don't see them being realized necessarily as the VEV of some dynamical excitation.
Yeah, indeed. This is maybe this is a big difference. That is, the qubits model have a lot of free parameters. It's very, very ugly. So only effective field theory maybe is nice and beautiful. And just a lot of those free parameters became irrelevant at the effective field theory level. But indeed, they have a lot of models. But on the other hand, I feel this free parameter issue probably is related to the following. You know, in the I don't want to really say that qubit model really quantum gravity is because although space-time metrics not specified, it's a lattice model. But however, some kind of a space-time framework is kind of there. There's a sense of a closeness, a distance, a sense of neighborhood is somehow predefined. And so this feature, how this feature was, that would be different from gravity. But what I really want to stress is a really a question. You know, I'm surprised that the condition on effective field theory, which coming from quantum gravity, and the condition on effective field, which come from qubits model, is so close. So it would be really interesting to see whether there's some difference condition, that some conditions are really different. You know, you say this effective field can only come from quantum gravity, cannot come from local qubits model. That would be really, really interesting. So then we can understand this issue better. Yeah.
Okay, Petr has a final question, but okay, go ahead. We're running out of time, but maybe you can just pose it and people can try to answer it in Slack. Go ahead, Petr.
Okay, so let's just ask a very naive question. How does this very mathematical corner of condensed matter, I mean, from an outsider, beautiful structures, but full of categories and so on, can you give us a brief description of how does that connect to experiments and to the more traditional condensed matter where we see materials and bands and stuff? Are there parts of it that are totally disconnected and parts of this that are more connected, or is it still, or everything is connected, or everything is disconnected? Could you just give us some flavor of how that works?
Yeah, and I think this question is asked more in condensed matter community. It is a right direction for condensed matter. And but on the other hand, it's really that I think in the quantum material, we indeed facing this so-called highly entangled quantum system. And so there's an issue about how to characterize this highly entangled quantum system. How to characterize many-body entanglement. And we know that when you have a symmetry, we need a group theory to characterize symmetry. But it looks like to characterize quantum entanglement, those anions, non-abelian statistics, or more generally, this category theory appear to be a right language. So that's why those kind of category theory somehow enter condensed matter, because it looks like it happened to be the right language to describe a highly entangled system. And you know, it's for the experiments, usually experiments only realize some very special states, like Ising category. And but to study Ising category, one don't need to study category. One can using Majorana zero mode. So most people do not use a category language to study Ising category, but using zero mode language. And so that's you can obtain condensed matter experimental available results. And but however, I think the Ising category probably is maybe most complicated experimental relevant category we encounter in condensed matter in real material. Although it's still not confirmed yet, but there is very likelihood there are certain quantum Hall states are described by Ising category. And this Fibonacci category, there are some expectation, some proposal, but it's far from confirmed experimentally.
Okay, so let's close the session, but of course people can continue to communicate via Slack. So thanks very much, Annette and Xiao-Gang, and we'll be back.
Thank you. Sorry again, Nati and Xiao-Gang.
Yeah. Thank you.
Thank you.
So let's see. So Xavier, I don't know, is that how you, do you want to try to share screen now?
Sure thing. Is that working?
Yeah, we're seeing the side panels. You want to?
Right. So let's see if we can do that. Is that better?
Yeah, that's perfect. Thanks.
Hey, Pedro, if you're there, can I just ask a quick question?
Go ahead.
Just saying, I'm logged in on two devices for technical problems with my laptop. So my speaker works on one and the video works on the other. So I'm going to share my slides from one laptop, but I'll be speaking into another. Just so if there's some confusion about why there's two of me, that's why there's two of me.
That's okay, but the sound is not so great. I don't know. Okay, we can hear you, but it's a little bit.
Oh, really? Okay, let me try to. Is that a little better?
I think it's worse.
Oh, it's worse. Okay.
You probably need to mute one of your devices, Nima.
Oh, it is muted.
Okay, we can hear you. Okay, I'm just.
Okay. All right.
Nima, you have to disconnect the audio from one of the devices. So
okay, I'll do that.
Join the audio.
I'll do that. Yeah. Okay, thanks a lot.
Can you hear me okay, by the way? Just while
Yeah, let me make you co-host so you can share screen. One second. Okay, you should be able to share screen now.
Do you want me to give it a try?
Yeah.
Should I try now?
Yep.
Can you see my slides?
Yeah, it looks good. Yeah.
Okay, great.
Okay. So Steve, you're the chair. So Steve Giddings will be the chair. So Steve, we can start in 3 minutes.
Okay, you want to start on time?
Yep.
Okay.
Thanks.
And just to clarify, did you want to have all questions at the end of the talk?
That's what we're doing usually. So people raise their hand or you can read from chat. So
okay, but save them till the end.
Right. So it's 25 plus 5 for.
Right. I'll give a 5-minute warning, I guess.
Great.
Okay. Okay, well, it looks like it's time to begin. And our next speaker will be Xavier Siemens, whose title is there, Results from the Nanograv Search for Nanohertz Gravitational Waves and Cosmic Strings and Other Sources. I guess there's been a slight change in the title.
Yeah, sorry about that. It's a pleasure and an honor to be here. Thank you for the invitation. Yeah, so I'm going to tell you about our latest results, our latest published results. And Nanograv is the North American Nanohertz Observatory for Gravitational Waves. There's about 200 of us in the US and Canada. And we collaborate with partners in Europe, Australia, India, China, and South Africa to form the International Pulsar Timing Array. We were fortunate in 2015 to become a Physics Frontier Center in the US, and we just renewed our support actually this past April for another few years. So we're part of a suite of experiments that are exploring the spectrum of gravitational waves. You've all heard of LIGO, of course, at the highest frequencies. LIGO is sensitive to binary black hole systems with masses between a few tens of solar masses. We operate at a few nanohertz and 11 orders of magnitude away in frequency. So our black holes are our black hole binaries are billions of solar masses. And we're also sensitive to sources of primordial gravitational waves, which I'll discuss toward the end of this presentation. Our bread and butter source is supermassive binary black holes, as I mentioned. We know that supermassive black holes exist at the cores of galaxies. We also think that galaxies evolve through mergers, meaning early in the universe, smaller galaxies merge together to form slightly larger galaxies, and so on. And this hierarchical set of mergers that results in the size and structure of galaxies that we observe around us today. When these galaxies merge, the supermassive black holes at their centers will also merge, producing a variety of signals. The loudest one, the one that we expect to detect first, is the stochastic background, which is a red noise process, which is the superposition of all of the gravitational waves produced by all the supermassive black holes that are merging in the universe. But we are building a gravitational wave detector, and there are other sources at these frequencies, which include cosmic strings, inflation, and phase transitions in the early universe. So let me talk a little bit about our detector, how our detector works. The first component is our pulsars, which are a kind of neutron star. They have strong magnetic fields, and they emit radiation beams, radio beams out of their magnetic poles. And if the rotational axis and the magnetic axes are not aligned, then they sweep in space like the beacon on a lighthouse. And so if we observe them as point sources of radio bursts, basically, they're basically like clocks that are spread out throughout the galaxy. So that's the first component. The second component are radio telescopes. We are fortunate to have access to some of the most sensitive radio telescopes in the world. Up until December of this past December, we were using Arecibo. You probably heard that unfortunately that telescope collapsed. We still have about 15 years of data from that radio telescope, which we will continue to use and will anchor future data sets. We also use the Green Bank telescope. This is a 100-meter dish, and we use the Very Large Array and the Canadian H1 Mapping Experiment telescope. So how does our experiment work? What we do is we keep track of every rotation that a pulsar is doing over many years. We construct something called a timing model, and I'll refer to this later when I discuss the results. And that timing model predicts when a particular pulse from a pulsar will arrive at our radio telescope. So what are the pieces of this timing model? Well, the pulsar is somewhere in the sky, and the Earth moves around the sun once a year. So when the Earth is moving toward the pulsar, the pulses will arrive a little bit earlier. When it's moving away, they'll arrive a little bit later. So the sky location, for example, is one of those parameters in our timing model. The pulsar could be in a binary system. We model that entire binary system as well as the pulsar is orbiting around its companion. Then when the pulses arrive depends on the state of that orbit. So all those things, the so-called deterministic part of the time of arrival of a particular pulse from a pulsar goes into a timing model. But we don't get it quite right. We have differences when we go and then measure the times of arrival. We have differences between the model time and the actual time. This is called the timing residual. And the gravitational waves will change the time of arrival of pulses. If you imagine you have an array of such pulsars spread out through the galaxy and a gravitational wave passing through the galaxy and stretching it and squeezing it, that will change the time at which these pulses arrive. So we look for gravitational waves in this timing residual data. What allows us to do this experiment and do this experiment so well is that the pulsars that we use are just outstandingly accurate. We can predict the time of arrival of pulses from our best pulsars to a few tens of nanoseconds. So over a time scale of 15 years, we can say, oh, next year, this particular pulse will arrive at this time, plus or minus, say, 30 nanoseconds. That precision is what allows us to do this experiment. It's not enough to have one pulsar, even though these are even though pulsars, some subset of pulsars, millisecond pulsars are amazing clocks, there's still complicated astrophysics that needs to be modeled and understood. And really what we're looking for is a correlated signal in our data, not just what we could see in a single pulsar, because we wouldn't know whether that's a gravitational wave, but rather a correlated signal from all of our pulsars. As an example, if you have a stochastic background of gravitational waves, then the gravitational wave perturbations are going to be correlated among different pulsars according to this plot down here called the Hellings and Downs curve. And what this shows is if you have two pulsars with an angular separation as given on the x-axis, then the arrival time deviations from the pulses will be correlated, most correlated when they are at zero angular separation, anti-correlated at around 80 degrees or so, in this sort of quasi-quadrupolar shape that you see here. So we have, in Nanograv, we have produced several data releases, the 5-year data release, a 9-year, 11-year, the 12.5-year, that's the data release that I will be discussing the results of during this talk. And each time what we've done is we've increased the number of pulsars that we time. That's really key to our sensitivity, is having as many pulsars as possible. And we've also been improving the instrumentation to improve the accuracy that we can make the measurements of these times of arrival of the pulses. And we're working right now on putting together a follow-up data set, the 15-year, which I will also discuss briefly. The plot on the right here shows each of these dots. The color represents the radio frequency. We make measurements at different radio frequencies with our radio telescopes. And each of these points is an epoch at which we took an observation. And this just shows the enormous increase, starting with our 5-year data set a few years ago, in the enormous increase in the number of pulsars that we time, and also just the sheer number of data points that we have taken over the years. This 12.5-year result got a lot of press. Here's an example and I will tell you what this result means. Before I do that, I want to, in case you're not familiar with this, I'm going to be talking about white noise and red noise, and I just want to clarify what that is right away. So if you plot the power spectrum of a noise process versus frequency, red noise processes are processes that have more power at low frequencies than at high frequencies, so they'll have a spectrum. This is really a log of the power spectrum. This is log frequency. So they'll have more power at low frequencies than at high frequencies. And then there's also white noise processes, which have the same power at all frequencies. In our data, we have several kinds of red noises and several kinds of white noises that we add in. You might have also heard of blue noise. We don't have that. That's not a noise type that shows up in our data. So so before I discuss the results, let me tell you a little bit about the model that we use. So each of our pulsars has a timing model, and I described this earlier when I was talking about the sky location, the binary parameters of the pulsar frequency, a spin down, all those sort of non-gravitational wave deterministic pieces are in the timing model, and each pulsar has one of those. The pulsars also have several kinds of white noise and also some red noise as well, intrinsic to each pulsar. So we have, in the case of the 12.5-year data set, we have 45 pulsars, so n is 45 here. So we have 45 of these boxes. And in addition, we add a common signal, which is a signal which is common across pulsars and it's possibly correlated. And the gravitational wave stochastic background, no matter the source, will first show up in our data as a common red noise process, a red noise process that has the same amplitude and spectral index across all of our pulsars. And in due course, we will build up enough significance that we should detect correlations that this is indeed due to a gravitational wave. So here are those boxes again. So that as I mentioned, we model this red noise piece as a power law. So it's just A times F to the minus gamma. So each pulsar has its own amplitude and its own spectral index for the red noise, and that's important. And then in addition to that, we add a common signal. So a signal that has the same amplitude and the same spectral index across all pulsars. And these quantities, A sub CP and gamma sub CP, that's what was in the plots in our 12.5-year paper. If you saw it, this is the quantity of interest. This is and we made a strong detection of a process with a common amplitude and spectral index across pulsars. You can see it here in a couple of different forms. Just ignore the green traces here in both of these plots. The blue and the orange are two similar ways of calculating what the amplitude and the spectral index are. And you can see we get very nice closed contours. And this is dominated by the lowest two frequency bins in our data, which is shown on the left. So how do we actually measure the significance with which we detect various things like a common process or maybe correlations? What we do is we use a Bayes factor to compare different models. And these Bayes factors tell us how much more or less likely one model is compared to another model. So the first model down here is a pulsar called pulsar intrinsic noise only. So what's that? That's this model. That's the model where you only have these boxes here. So each pulsar just has its own set of noises, and that's all that goes into the model. So that's this box over here. The next model that we compare that to is a model with a common amplitude. All right, so that is this model here. It's these boxes up here plus this common signal boxes down there. And we compare those two models, and what we find is a Bayes factor of several hundred to a few tens of thousands, depending on the details of what we do. So this is a strong detection of a common red noise process in our data. And the next question we want to ask is this common process correlated? And there are different kinds of correlations. The middle box here, HD, that stands for Hellings and Downs. That's that quadrupolar correlation that I showed earlier. There are other kinds of correlations that we could have in our data coming from, for example, some systematics. A monopole would come from a clock systematic. A dipole would come from a solar system ephemerity systematic. And when we compare a model that has that red noise, which is correlated, versus that same red noise, but without the correlations, we see a Bayes factor of about 2 to 4. that means that there's 2-to-1 to 4-to-1 odds of the noise process being there. This is nothing to write home about. What is interesting is that these other systematic types of correlations that we considered are disfavored. So this one is, I would say, not particularly favored nor disfavored. The monopole and dipole correlations of this red noise process are disfavored. So here's another way of seeing that that the base factor of 2 to 4 is nothing to write home about. These are the correlations as a function of angular separation in our 11-year data set and our 12-year data set. Yeah, you could think that there's something here, that fits the blue Hellings and Downs curve, but you can also fit a straight line here, which is shown in the monopole in the orange here, pretty well as well to this data. So that sort of tells you that we're not really seeing any kind of strong evidence of correlations. Another thing you can do is to figure out what are the chances that noise alone will give you a base factor of 2 to 4. And we do that in a couple of different ways. We do phase shifts in our data, which is very similar. If you're familiar with LIGO, they time shift their data. They do time slides of their data, and this is a very similar thing. We do phase shifts on our data that breaks the correlations. Another thing you can do is change the sky location of the pulsars, but not tell our code that you've done that. And so you're basically breaking all the correlations, the Hellings and Downs correlations. Both of those give you very similar results, with the chances of noise alone giving you this base factor of about 10%. So yeah, you're somewhat out in the tail here of the distribution, but 10% of the time, in the absence of correlations, will still give you a base factor of 2 to 4. So where does that leave us? Well, we are definitely detecting a common red noise process, but that means that it has the same amplitude and spectral index across pulsars, but we don't yet know what this is. It doesn't have significant quadrupolar correlations, which will be the telltale sign of gravitational waves, but curiously, it does favor monopolar and dipolar correlations that would come from some known systematics that we could have in our data. So we're following this result up in our 15-year data set, and we're collaborating with our international colleagues who have their own independent data sets. So stay tuned for results. We are currently doing this, and we expect to have results, I would say, on the timescale of about a year or so from now. All right, so let me talk a little bit about cosmological sources of gravitational waves, which are of most interest to you all. I think so. We do expect the most promising source are supermassive binary black holes, and we do expect to make a detection if the astrophysics, if we understand the astrophysics well, which we think we do, quite soon. We may be seeing the first hints of it right now. We're just not sure. And this will be followed by the detection of individual binaries that stick up above the background. So what about cosmic strings, inflation, phase transitions? There's a couple of questions. How can we distinguish between different types of sources? Suppose we detect a background. How do we know that it's supermassive black holes and not cosmic strings, for example, or some other source? And if there's more than one stochastic background in our data, how do we distinguish between, how can we measure that? So I'll try to talk about this a little bit in the next few minutes. These sources are speculative, but they're very important, because a positive detection would have profound consequences. So as you know, cosmic strings can form in phase transitions in the early universe. Cosmic superstrings are fundamental strings that are stretched to macroscopic scales by the expansion of the universe. And in the simplest models of superstrings, they behave very much like the cosmic strings of field theory. They're characterized by a mass per unit length mu, which is usually expressed in terms of the Newton's constant times mu, which is dimensionless. So for example, gut strings have a value of g mu of 10 to the minus 6. And pulsar timing arrays are actually currently the most sensitive experiment to cosmic strings, and they give the best constraints. This is the constraint that we got up until before the time that we detected this common red noise process. And note that this is several orders of magnitude below the gut scale, which is really quite nice. So this is a plot from a paper that Ken Olam and Jose Blanco Villado and I wrote a few years ago, with the best upper limits coming from pulsar timing arrays. This shows omega, the spectrum, omega versus frequency for, this is the pulsar timing array limit here shown in this wedge. And I show here the background due to supermassive binary black holes and the slope of this line here, basically. So what I was trying to show here is that these two, the two slopes in omega of supermassive binary black holes and cosmic strings are at this frequency quite similar, and they may be quite hard to tell apart. That was several years ago. In the meantime, we have detected this common red noise process that we don't know what it is. There were a lot of papers about cosmic strings on the archive that are citing this. I believe, I hope that this is the latest one that I'm aware of, and I think that there's the interpretation of what kind of cosmic strings you're seeing depends on the particular model of how cosmic strings evolve and the emission model that you use. But I believe that the results were more or less the same. Maybe someone in the audience can correct me if I'm wrong. Yeah, understood. Yeah, I'm almost done. So this is what I have on the y-axis is the log of the amplitude versus the spectral index. This is taken from this paper down here. What is shown here is for different emission models. So mono is a monochromatic emission just associated with the size of the cosmic string loop that's producing a gravitational wave, kink emission, cusp emission, and all of these emission models essentially give, they're very robust. They give more or less the same result. They're in about the same area. And the contours here show the nanograv common red noise process. So what you see here is that the common red noise is, if this is produced by cosmic strings, then they would be produced by cosmic strings at with a G mu of a few times 10 to the minus 11. And this is a little bit higher than our upper limit that we had earlier, and I'll be happy to talk about that if someone has that question later. In the case of cosmic superstrings, you have reconnection probabilities that are less than or equal to 1, and there's a couple of reasons for that. One of them is that strings interact probabilistically with a probability proportional to the square of the string coupling, and also that these models have extra dimensions, and even though strings will meet in 3 dimensions, they'll actually miss each other in the extra dimensions. Though both of those effects have reduced the reconnection probability for cosmic superstrings. And here you see the effect of the reconnection probability, again, in a plot taken from this paper. If you reduce the reconnection probability, what that does effectively is to raise the density of strings in the network. And low values of the reconnection probability are disfavored by the data. I would say, before you read too much into this, I would say, we're analyzing more data. These contours are very broad. And so we'll eventually these contours will settle into something that we really believe. At the moment, I wouldn't overinterpret this, the data. Let me put it that way. So let me talk a little bit about phase transitions in the last few minutes. So the horizon at the QCD phase transition time is about 10 kilometers, and this is stretched by the expansion of the universe to about a parsec or 3 light years. And this is about the wavelength of gravitational wave sensitivity. This was actually pointed out by Ed Witten back in the 80s, the first person to my knowledge to point this out. And of course, if there's any kind of process, that interesting physics that is going on at the QCD phase transition time that generates gravitational waves, then the gravitational waves get stretched into the PTA band today. So as far as we know, the QCD phase transition is not a first order phase transition, it's just a crossover, but there are beyond the standard model situations which can lead to first order phase transitions and other interesting physics where you could in fact produce a background due to bubble collisions and other things like that. So to summarize, we expect the detection of a stochastic background from supermassive binary black holes in the next few years. I haven't mentioned inflation actually, so let me say a little bit about that now. this red noise process that we're detecting, if it is due to gravitational waves, is certainly not from vanilla inflation because the amplitude is too large. That's already ruled out by cosmic microwave background experiments. There are modifications to inflation where you can have a blue spectrum and omega, so you can have, satisfy the constraint that comes from the CMB and then have a rise that might, but vanilla inflation is certainly not what we're seeing. For cosmic strings, the PTAs are the most sensitive experiment, and we've already ruled out a bunch of a chunk of the parameter space. However, when it comes to distinguishing the two, this may be complicated because the spectral index looks like it's similar-ish to what you get from supermassive binary black holes. However, that really depends on where you end up on the omega versus frequency part of the spectrum. But if you end up where I showed earlier on the plot, it may be hard to distinguish. However, distinguishing the two is not just about the spectral index. There are other things like anisotropies that we could use. The background from strings is expected to be very isotropic, whereas the supermassive binary black hole background is not. So any deviations from isotropy would be a very good telltale sign. And of course, LISA in 2034 will settle any lingering doubts. However, I think we can resolve this before then. And I also mentioned phase transitions, and there's potentially the same problem depending on where you end up on the spectrum of the produced by phase transitions. So I will leave up my last slide, and I am out of time, so I will stop there. Thank you.
Okay. Thank you for a talk with some tantalizing results and questions, anyone? Let me see, I see Eva.
Thanks for the really interesting talk. When it comes to the supermassive black holes, would your results be able to help with questions about how they formed, how rapidly they were able to form, and that sort of thing, which I gather are sort of persistent puzzles in astrophysics?
So that's a great question. So the pieces that come into the predictions of the background are the galaxy merger rates, the masses of black holes that live in a certain mass galaxy, which does tie into what you were asking directly, I think. And also what the environments are like at the cores of galaxies. So those are the three main ingredients that I had a few slides about this, but I actually took them out of this presentation. Those are the three main ingredients that enter the calculation of the background. So once we measure the spectrum, we can solve the inverse problem, and we can turn it around and say, okay, well, this must be the galaxy merger rate. This must be what the environments at the centers of galaxies is like, or the cores of galaxies are like that black holes live in. And this must be the masses of black holes that live in a certain mass galaxy. This is called the M sigma relation. So to the degree that the M sigma relation will shed light on your question, getting to the bottom of the M sigma relation or MM bulge relation, we'll answer the question that you asked. We will be able to shed light on this. I think what you were asking though is, how do we get such massive black holes so quickly in the universe? I don't know how much we'll be able to say about that particular question, other than whatever light we may shed on the M sigma or MM bulge relation.
Okay, looks like Sandip Trivedi next.
Hi. Yeah, no, thanks for a very interesting talk. I had a sort of similar question to Eva's, but just more simply, how massive would the supermassive black holes have to be to account for your red signal you might be seeing? Just ballpark.
Billion solar masses.
Billion solar masses.
Yeah. At least those are the black holes in the standard model that we use to produce our sort of nominal spectra for these black holes live at the centers of galaxies, and they're order billion solar mass.
So like order of magnitude like M87, if I'm right? Or is that off?
Exactly. Yes.
Okay. Very exciting. Thanks.
Okay, maybe one from the chat. Sethi asked, can you comment more on observing the gravitational memory effect from PTAs?
Yeah. So all of these are really great questions. So the memory effect is very generic to any system that produces gravitational waves. Generally, there will be some memory that accompanies it. And that's where, for us, so my graduate student here at OSU is actually working on this. One of our flagship searches is for black hole, for memory type searches. And my graduate student is actually working on this. And so the merger rate of supermassive black holes is sufficiently low at our strains, at the strains that we are sensitive to, something like 10 to the minus 15, 10 to the minus 16, that we may detect one every 10 or 100 years or something like that. So we're not, at least, we understand the physics correctly, the astrophysics is right. The expectations for the rate of these bursts from supermassive black holes is quite low. We could get lucky, of course, but the rate is expected to be low. But like I mentioned earlier, the memory is very generic. There's all kinds of systems that emit memory that have a memory signal associated with them, and this is really why we search for them, because of the unknown unknowns. So that's as much as I think I can comment on this question. It's a really nice question.
Okay, and then I'll defer to the organizers here. Should we allow one more question, or do we need to move on?
I would say you can ask. You can have one more question.
Okay, let's have Xiao-Gang.
Yeah. Here you mentioned this cosmic string in early universe. I wonder whether there's any constraint on the energy scale of a cosmic string from this astrophysics of observation.
Yeah, I mean the energy scale is that's another great question. The energy scale is basically given by G mu, right? So G mu 10 to the minus 6. So you're basically, so that's the gut scale basically, and the results indicate a G mu of a few times 10 to the minus 11. So it is 2.5 orders of magnitude below the gut scale.
So what that means the cosmic string beyond this scale is ruled out, or something. I try to understand the meaning of this graph.
Right. Yeah. That's right. That's correct. I mean, if this, the only signal that we're detecting right now, this common red noise process, is centered here. There's nothing up here. There's nothing down there. So G mu of 10 to the minus 9 is not allowed. So right now, if the signal is due to cosmic strings, then the cosmic strings that would produce it, that are allowed to produce it, are something like a few times 10 to the minus 11, maybe 10 to the minus 10, something like that. 2 to 3 orders of magnitude, 2 to 2.5 orders of magnitude below the gut scale.
Okay, thank you very much.
Okay, so I presume we should wrap up. I'll just mention, though, there are a couple of questions in the chat that you may want to look at, but I'll go ahead and end the session there. So thank you for, again, for a very interesting talk.
Thank you.
Thank you. Thanks, Steve. So welcome, everyone. Hope you are having an uneventful morning, afternoon, or evening, and a relaxed one. And we go to our last informal discussion of the day. So it will be on particle physics. And I remind you, the first 20 minutes are totally up to Lance and Nima, followed by 30 minutes of informal discussion. Please turn your camera on when possible for those 30 minutes. And raise your hand and wave if you want, if your comment is related to what is being discussed right now. And so without further ado, I pass it. I don't know who goes first, if Lance or Nima.
I'll go first.
You go first? Okay, so it's a pleasure to pass it then to Lance.
Can you see my slides okay?
Yeah, it's perfect and we can hear you perfectly.
All right, great. Thanks very much, Pedro, and the other organizers for the opportunity to lead this discussion of the challenges facing particle physics in the future. And this will be joint with Nima. And I prepared some slides, which I'll say are more experimentally oriented, and then Nima will sort of move in a little more theoretical direction. And I'm told that Nima has practiced his talk and timed it out to exactly 11 minutes. So Pedro stopped me in 8 minutes and 40 seconds or something. So precision timing is at work here. So anyway, one of the challenges that particle physics faces, and I think everybody's aware of this, but just to sort of set the stage, is that we have a terrific theory already. I mean, we have string theory, of course, but we also have a theory that makes concrete predictions for the results of particle physics experiments, and it has been tested repeatedly over and over again. And it answers many questions about the structure of matter, but obviously not all, or we wouldn't be still searching for things. One of the key successes and also frustrations with the standard model is that once the Higgs boson was discovered, it became a complete self-consistent renormalizable theory. Before the Higgs was discovered, we basically knew something had to happen around a TeV, or fundamental properties of quantum mechanics like unitarity would be violated. But now that the Higgs is there, everything's self-consistent. And so the standard model doesn't provide us with a lot of clues to its eventual downfall or extension. So you can predict things based on naturalness and so on, but they're not as crisp as on unitarity. Now, we all know that the standard model is missing many different things that we have to have, such as dark matter, inflation, dark energy, baryon asymmetry of the universe, neutrino mass generation goes outside the scope of the standard model. The flavor structure is not understood, lots of clues there, gauge unification, a natural origin for the weak scale, and of course it's missing the graviton. Of course, for that we do have string theory, and maybe for some of these other things. But we need experiment to tell us the right way. We need to know the direction that leads us towards string theory. Now, one of the ways of getting clues, and the main way of getting new clues, is of course experimentation. And the most direct experimentation is at the energy frontier. And right now the energy frontier is really occupied by a sole machine, the Large Hadron Collider. I just want to point out that the Large Hadron Collider has a long road still ahead of it. So the Higgs boson was discovered around 2012. This blue curve shows the integrated luminosity collected and then projected past around 21 or so. And so the Higgs was discovered based on this tiny amount of integrated luminosity. I forget exactly, somewhere around 20, 50 inverse femtobarns. Anyway, we're now around 2020, and there's more like 200 of these units of inverse femtobarns. So a lot more than when the Higgs was discovered. And that's told us a lot more about the Higgs than we knew in 2012, more precision, and everything agrees with standard model predictions so far. But as we move on through a sequence of additional upgrades, in particular, this LS3 will really increase the luminosity fairly dramatically. We should get over 10 times the current amount of data. So that means 10 times more particles, new particles produced if they're there. And you can measure various things depending on how much background there is, to anywhere between 3 times to 10 times better. So there's going to be a wealth of measurements going on at the LHC over the next decade or so. And what about beyond that? Well, this more or less takes us to the second half of the 2030s, and the future of the energy frontier beyond that is much less clear. So there have been a variety of machines proposed at different levels of design readiness, which would try to address various issues. For example, the International Linear Collider, if it were decided by Japan in conjunction with decisions in other major corners of the world, like the US and Europe, to go ahead, it could be constructed and start taking data sometime in the 2030s. And that would be a precision machine to try to address, in particular, Higgs precision modes that are very hard to see at the Large Hadron Collider because the environment is so much cleaner than an electron-positron machine. There's another SLAC based idea for this is a fully superconducting machine. This one would be a cool copper, but it hasn't been explored and studied as long as the ILC has. There are also other ideas for electron-positron machines. If you want to make the Higgs in abundance, you can build a circular machine, and this would be the last circular E plus E minus machine. Of course, that's what they said about LEP, which is in the LHC tunnel. So this FCCEE addresses some of the same kinds of physics and Higgs precision measurements as the ILC. And then a circular machine allows you, if you have that large circular tunnel, to put a proton machine in it eventually that could go up to around 100 TeV in the center of mass. Now 100 TeV in the center of mass for protons is, smaller for the constituent quarks colliding. Another way that people have talked about to get to very high energy in the constituent center of mass is by colliding muons. I have to say this is, there's an awful lot of work that would have to be done to make a muon collider realistic. When you produce muons, they're very, very angry swarm of bees, and you have to cool them down and make them into little tiny beams to get high luminosity. So that's a bit of a challenge. Other methods to get very high gradient linear acceleration to make machines like this much shorter involve plasma wake fields and laser wake fields or direct laser acceleration. But I think everything on the bottom line here needs an awful lot of development before it can make a realistic machine with the luminosities you need to do physics. But the particle physics experiment is not just occupied by the energy frontier. There's also frontiers that involve flavor physics, precision physics, rare physics, and so on. And here's just a list of different experiments that go in that direction. I see time's running short, so I'm not going to spend much time on them, but there's special purpose. For example, the G-2 of the muon, which you've heard about, it's precision measurement, charged lepton violation, lots of B physics. There are many flavor discrepancies currently that bear watching. This is from a Twitter page, and I kind of call it muonom in jest because it rhymes with QAnon, which some of us in the US have been listening to recently. But anyway, these are all anomalies that involve muons, and it's actually from an experimentalist on LHCb, so not surprisingly, most of them involve Bs. And here's the muon G-2. And this shows the theory prediction. Sometimes the theory is extremely precise. In other cases, it's a bit murkier. And these are all cases where there's some pull or just some discrepancy from the standard model. I just want to say that the situation with muon G-2, this quoted error is 4.2 sigma, and that's based on a certain dispersive evaluation of a contribution called the hadronic vacuum polarization. And that's been sort of the traditional way to do it. But more recently, the lattice has been able to start shrinking the errors down. One lattice group in particular claims errors that are comparable to the dispersive measurement, but with a different central value that would significantly reduce this discrepancy. So to conclude my section, what can theorists do in this effort to confront the standard model and hopefully find its downfall? And one is to think of new theoretically compelling and experimentally predictive frameworks for new physics, especially those that have novel signatures, so new experiments can be designed or new triggers added to the LHC, and to compute precise consequences of the standard model where needed experimentally. In some cases, it's very important, like muon G-2 as one example, and devise new ways to analyze data, perhaps including machine learning. And finally, to apply theoretical technology to other areas that aren't necessarily exactly particle physics. For example, there's been work on applying scattering amplitudes to LIGO. So I'm going to turn it over to Nima now. So Nima, please go ahead.
Let's
Thank you
thank
very much.
Lance while Nima sets up the screen share.
Can you let me share my screen, Pedro?
You are not host. Nathan, Nima should be host.
Yeah, there is a two of me.
Okay. Yeah, now you are co-host. Yeah.
Hold on a sec. I'm still disabled. Sorry, Pedro.
Maybe there is another Nima.
Yeah, there's two Nimas, unfortunately. All right, great. Yes, thank you. Just 1 second. Okay.
You were within your time, Lance, with 1 sigma.
All right, great. Wonderful. Okay, can you see my screen okay?
Yeah.
All right, wonderful. All right, I'd like to thank the organizers for the invitation and also thank Lance for giving a terrific overview of the big picture. Given that we're supposed to hopefully trigger a discussion, I'd actually like to take a step back and talk about a 0th order, perhaps even -1th order issue that's related to the topic at hand. I think one that most people in the field acknowledge implicitly, but which I think would be good to talk about explicitly, which is the by now pretty much complete divorce, not of string theory from particle physics, but of string theorists from particle physics. And whether or not this is a good thing or a necessary thing, obviously for my part, I think it's neither, but that's, I think, part of the discussion worth having. Now, historically, string theory was closely connected to particle physics and the ambitious program of unification. And immediate antecedent was the amazing observation that a standard model generation is embedded into a 16 of SO10. And the story of anomaly cancellation, the E8 cross E8 heterotic string compactifications, and the discovery of stringy mechanisms that could solve many open issues with guts was then and remains today absolutely mind-blowing. The idea of supersymmetric unification somewhere very close to the string scale also has experimental evidence from the remarkable picture of coupling constant unification in theories with low energy supersymmetry. 3 lines don't have to meet at a point. They didn't have to meet close to the string scale. The scale didn't have to be close to what we need in the simplest models of inflation or of Majorana and neutrino masses. Very unlikely to be a coincidence. And so for many years, string theorists were happy to have this close association with particle physics, even if already since the late 90s, less of the activity in the field was focused on getting the standard model out of string theory. It's fair to say that things have changed significantly with the non-discovery of SUSY at the LHC. Whereas pre-LHC, many, certainly not all, but many leading string theorists would say, 1, the LHC will discover SUSY, and 2, string theory loves SUSY and unification. Today we have crickets instead. Actually, I've written cicadas there in response to what we've seen from the LHC. This was meant to signify quiet, but the cicada joke is a very poor one since those bastards are really loud. Anyway, I think now the attitude more is, well, string theory is mainly about quantum gravity. It doesn't really have that much to do with particle physics. We don't really care that much about the connection to particle physics. And that was a sociological comment, but I think it's very likely in the minds of many people, there's a physics reason for taking this attitude, which is the plausible picture that string theory is an enormous landscape of vacua. Now, people may say they love it or hate it, but de facto, most string theorists live with and live in the landscape. In many ways, this is an even more extreme and impressive sort of unification, but also in the minds of most people, I think it means not only that the standard model is not the unique vacuum of the theory, but that it's unlikely to be special in any way. And this makes the connection to particle physics appear either hopeless or only of parochial interest to our little corner of the landscape, and perhaps not particularly deep or important. Now, I personally think the existence of a vast landscape and even the possibility that some aspects of our vacuum are selected for anthropically are totally reasonable things. But I disagree that it makes the connection to particle physics hopeless. Indeed, I think it can have a dramatic impact on how we think about particle physics and can inspire new models for particle physics we would have otherwise dismissed as crazy. And in fact, this is exactly what happened to me. My own best bet for what's going on at the TeV scale since around 2004 to 2006 is the minimal version of split SUSY. And I won't say anything about the model in detail, except to point out that it did make a correct prediction of the Higgs mass to lie between 120 and 135 GeV. Mild prediction, but it's at least not wrong. The associated fine tuning for electroweak symmetry breaking makes this picture crazy without the landscape, but much more plausible with it.
And I certainly hope to be alive to see gay genomes discovered at some accelerator in my lifetime. So I'm going to the gym and trying to work out so I make it as long as necessary. In any case, I think it's fair to say nowadays string theorists are, for the most part, no longer actively pursuing the connection to particle physics of the real world. And I think this is totally understandable as a short-term strategy. But in my view, it's a real mistake in the long run. And that's because string theory remains by far the most magical structure we've ever encountered in theoretical physics. And the magic seems directly connected to the particle physics of the real world. Even if we're frustrated in turning what various eminent people have called the 0th draft of the picture into a first draft, it's certainly impossible for me to ignore how spectacular that 0th order draft actually is. And I want to stress here that I'm not here to be a scold. The motivation I'm talking about for thinking about the real world is not a punitive one. It's not to punish things or rule out ideas, but it's a creative one. It's for creative reasons that the real world knows exponentially more about physics and math than physicists and mathematicians do. We've seen this time and again. The questions posed by nature are vastly deeper and more fruitful, even only, quote unquote, for learning about the inner structures of theoretical physics than the questions we humans would pose left to our own devices. Okay? So having said all of this, let me make a few more specific comments on possible opportunities for connections with particle physics, starting with a couple of speculative ones. So first, I want to talk about some funny clues that run counter somehow to the narrative that there is nothing special about our vacuum or in some random corner of the landscape. Of course, there are some famous 0th order observations along these lines. Many of them, I just chose 2. The 1-generation standard model is nearly the simplest chiral gauge theory. Why would that be? Why is theta QCD so small? There are other things. There are patterns in the structure of the fermion masses that seem to be associated with zeros in Yukawa matrices. There's the famous numerical coincidence between the weak scale and the geometric mean of the scale of the CC and of the Planck scale and of the neutrino masses. And this last point is related to one of my hobby horses that I mention every chance I get, that at a quite detailed level involving all the factors of pi, the proximity of the scale of the cosmological constant and of neutrino masses makes it just such that the standard model itself has an ADS3 cross S1 vacuum, where one of the dimensions is compactified, stabilized by neutrino Casimir energy at a size around 20 microns. Why did the parameters arrange themselves to make this funny vacuum exist? There are no obvious anthropic reasons for any of these things, and so they all look like funny clues to me. Another opportunity is the following. We know that the UVIR connection in gravity violates the Wilsonian effective field theory paradigm. So why isn't it that UVIR hasn't helped us somehow understand the origin of the cosmological constant or the Higgs mass in a new way? There's actually an inspiring example of this in a 1987 paper by Greg Moore, who found an Atkin-Lehner symmetry beyond modular invariance that explained why a certain non-supersymmetric 2D compactification of string theory nonetheless had vanishing one-loop vacuum energy. And this arose due to a delicate UVIR cancellation between the field theory and stringy regions of integration over the fundamental domain. Later, Lerche et al. Gave a simple mechanical explanation for this by observing that in this model, the vacuum energy is the integral of a total derivative that vanishes on the boundary of the fundamental domain. Now, for many years, I was looking for a simple version of this phenomenon in field theory. And very recently, just last month, together with Keisuke Harigawa, one fell into our laps in thinking perhaps of the dumbest possible models for explaining the muon G-2. And I don't have the time to explain in detail, but here there is a clear violation of Wilsonian naturalness, not for relevant operators like the CC or the Higgs mass, but for the leading dimension 6 operators for G-2, which is explained by a total derivative phenomenon that gives a 0 for classes of contributions of G-2 at all loop orders. So to me, this is another motivation to go back and think about this possibility again in the deeper settings for things that we care about, like the CC and the cosmological constant. Let me now turn to some of the active current research trends that are strongly motivated by making statements about the real world, of which you've heard a lot about at this meeting. We have the swampland program to rule out effective field theories that can't be coupled to gravity. And we've also been learning more about surprisingly stringent bounds on effective field theories with and without gravity from basic physical principles such as causality and unitarity. I won't say anything about them individually, but I'll say that at least in my mind, these two strands of work are clearly strongly connected to each other. And the challenge of the two programs is clear. The swampland talks about aspects of physics we definitely care about, but it's still difficult to make precise statements. Meanwhile, we have surprisingly precise statements we can make about higher dimension operators and effective field theory, but they're mostly about things we don't care about. So can we merge the strengths of these two programs to get precise statements we do care about? There's been a lot of progress recently, so I'm optimistic. But let me just mention sort of three random concrete challenges in this direction. One, can we have, just to take an example, an SU 2021 to the 2021 gauge theory coupled to gravity and D equals 9 space-time dimensions? Two, are the landscape of all possible CFDs connected by bulk string theory somehow? For example, is there some part of the string theory landscape which has the ADS3 dual to the 2D Ising model? And three, we know quantum gravity breaks all global symmetries, so can we reliably compute in any regime, most likely the super-Planckian regime, the amplitude for quark-quark-quark lepton scattering that violates baryon number in the real world? And can we put an upper limit on the proton lifetime? I'm more optimistic about the first possibility than the second, but those are both clear questions about quantum gravity relevant to the real world and relevant to these general programs. A final theoretical comment I'll make, which is putting my money where my own mouth is. I want to mention what I think many people see as a big tension between two gigantic things we know about string theory. On the one hand, it looks to be the huge unified structure with many different backgrounds of solutions of the same theory. On the other hand, any quantum system is dual to its own private theory of quantum gravity and ADS. How can both these things be true? Now, to me, since the more universal, more unified physics is seen in the flat space limit, it's an indication there's extra magic in the ability to find a flat space limit, giving further theoretical motivation to look for that extra magic in the flat space physics of the S matrix. Now, we've already been seeing for years now real magic in the properties of particle scattering amplitudes with hidden structures and symmetries well beyond toy supersymmetric models, deeply connected to the particle physics of the real world. And they're also showing more and more strong signs of connections and extensions to string theory and string amplitude. So again, for my money, there's room for something really magical and amazing to happen here, which is of course why I'm working on this subject. All right, so I want to end with two more general comments about the culture of theory and experiment and what thinking like a particle physicist brings to the table. I think there are broadly two strategies for work in our field. One strives to make increasingly accurate but approximate statements about the real world out there. The other is driven to make exact statements about imaginary worlds, and here possibly even connect to experiment by trying to engineer close replicas of those imaginary worlds in a lab somewhere. The culture of particle physics is clearly more closely associated with the first way of doing things, and is inspired more by the presence of some external divine magic out there. The second way is closer to at least some aspects of condensed matter physics and is more driven by human ingenuity, both theoretical and experimental. I think they're both vitally important, and thinking about connecting string theory to a particle physics is a good way to remember the existence of the first strategy. And I think finally, the biggest challenge of all for particle physics is getting new experiments, both long-term planning for huge projects, as well as thinking of novel, smaller scale probes of fundamental physics. And theorists can play a huge role in this endeavor. I think another aspect of the intellectual health of the field, even if it's not remotely your day job, I think it's great for theorists to hang out with experimentalists, to talk to them, to get to see the world through their eyes. I can tell you it's fun, it's stimulating, and it's a wonderful reminder that there is a big wide world out there filled with things that we need to understand and explain. All right, thanks a lot.
Thank you. Well, let's all thank Nima. Oh, thank you very much, Nima and Lance, and you were indeed on time. Yeah.
You look shocked, Pedro.
No, not shocked at all. No, of course I knew. Of course, Nima would be on time. Okay. Very good. So I remind you, camera on if your internet allows it, and we'll give priority to people that have not yet participated much in the previous discussions, and I encourage everyone, especially those, to raise their hand. And perfect example, Matt.
Yeah, thanks. Thanks, Lance and Nima. I enjoyed those overviews. I just wanted to add a few comments that sort of reinforce a few things that have been said. The first one is Lance only had time to briefly flash a slide about kind of non-collider experiments. And I wanted to emphasize that there's huge progress happening there. So he had mu to E on the slide, for example. There are a lot of these charged lepton flavor violation experiments, MEG2, mu3E, mu2E, Comet. And these things are poised to improve limits by orders of magnitude in the next 10 to 15 years. So we're going to have indirect probes of kind of tens to 100 TeV with reasonable assumptions, new physics talking to leptons violating flavor there. And maybe even more exciting, there are electric dipole moment experiments. There's actually another conference that I was attending earlier in the day at MIT this week where there are a bunch of AMO people doing this stuff. And they're already probing one loop new physics at 100 TeV with reasonable, minimal flavor violating assumptions. And they're going to improve those bounds by multiple orders of magnitude in the next 5 years. I think that's an expectation they have, and they seem to have the tools to do it. So even before we have any future colliders, we're going to have data coming in about the 100 and even 1,000 TeV scale. So I think the experimental landscape right now is super exciting.
Can I add something to that, Matt? I mean, the story of EDMs is incredible to me. I remember as a graduate student for like decades, the limit on the electron EDM was stuck at around 2⁻⁻27 e-centimeters from the work of Gene Cummins at Berkeley. And then stunningly, over the past 6, 7 years, as you know better than I do, it's improved by 2 orders of magnitude. And it's going to order, and as you say, they think it's easy to get another 2 orders of magnitude on the 5-10 year timescale, which is absolutely stunning. It's like definitely reaching into the mini split world, for example, absolutely reaching into that world. So, but more generally, probing physics, like you said, at the 100 TeV scale, I think it's amazing what they're doing.
Yeah, I think that's a really, all the things you mentioned, Matt, are really great places to look for new physics. Another thing I realized I missed for lack of time is like neutrino-less double beta decay. That's also, lepton sector delta L equals 2, to see whether neutrinos are really violate lepton number, the neutrino masses.
And proton decay. Particle physics progressed a lot over the years by getting lucky. And it's true that every factor of 10 in proton decay is only buying you the 4th root of 10 in the mass, in the reach for the mass scale. But still, if we're going to get lucky sometime, I think that's the most just place that we could get lucky. And it would be totally incredible to have access to a scale, of around 10 to the 15, 10 to the 16 GeV. So
Daniel has a comment related to this.
Yeah, I just wanted to emphasize, I think the fate of B-L symmetry is really an interesting and important thing for us to think about. We think it can't really be a symmetry. It's the only, sort of reliable global symmetry in the standard model. It either has to be broken or it has to be gauged. And I'm actually very curious, in string compactifications and so on, right? So, I mean, for example, if it's just broken, right, then we can have the proton being unstable, neutrino-less double beta decay and so on. But if it's gauged, that can be interesting too, because then probably there have to be strings that we could think about the cosmology of. Or you could say, it could be broken to a discrete gauge subgroup, or it could just be gauged with a very small gauge coupling. Probably that's not what happens, but to me, it's a very real world question that gets directly at these kind of swamplandy kind of questions.
Yeah, that's a great point. I mean, B-L also has a big impact on baryogenesis and the evolution of baryon number in the early universe.
So I had another thing I wanted to say, but I could also wait if you want to go to other people first.
No, go on.
Okay, so the other kind of orthogonal thing I wanted to mention is maybe more of a social thing, because Nima said that string theorists have kind of disconnected from particle physics. But I think another thing that's happening is a lot of particle theorists are disconnecting not only from string theory, but even to some extent from quantum field theory. I feel like there's a big movement toward very pure phenomenology in recent years. And in some ways, there are healthy things happening. People thinking up lots of new ways to look for dark matter, for example. But I feel like among the students who are coming into the field, there's sort of an increasing sense that these are just two disjoint fields, and to be interested in one is not to be interested in the other. And I don't think that's a good thing for the field. I think it would be good on both sides to have more have more connection. And I think string theorists have useful things to say to people who are interested in particle phenomenology. And I have one just kind of contrived example of something that I recently saw in arXiv. So I don't want to blame anyone by name, but there was a model of fitting some anomaly in data where somebody needs to postulate a charged particle with a charge of about 1,000th of the charge of the electron, for instance. And we can get those things from kinetic mixing, but in this case, that doesn't work because of some cosmological constraint on the dark photon. Now, my instinct is to say there are no vacua, or at least there are probably very few vacua where there are charged particles with, integer quantized charge that's 1/1000th the charge of the electron. But I don't know how to prove that. And I think a lot of these swampland debates people have been having are focused on very difficult dynamical questions about things like moduli stabilization. But even these kinds of kinematic questions of like what kinds of charges are allowed among light fields in the theory are things that are interesting in particle physics. And I think there are probably things that string theorists can say about this. At least I think a lot of you probably have intuitions about this that clash with the intuitions of a very low energy minded person who says it's technically natural for me to add this thing with a tiny charge, so why don't I do it? And I don't know, I would like to see more, maybe this is too old-fashioned string theory. This is the sort of thing people talked about more in the old days with the heterotic string. But what kinds of charges and representations can you get in the low energy EFT? And what are the rules that tell us things that you can't get? I don't think there's been a lot of work on that in the swampland program, but I think, to me, it seems like a very interesting question where there's overlap between the interests of very phenomenologically minded people and the interests of people interested in questions about geometry and F theory and all of those things.
By the way, I just want to say that was the motivation for my can you get an SU 2021 to the 2021 gauge group in 9 dimensions, just to put it in odd dimensions, very close to 10, very extreme. Is it or isn't it part of the string landscape? I think that's a baby step in the direction of the kind of thing you're interested in. Maybe Cameron has something to say about that, actually. Yeah.
Thanks for the interesting talks, Lance and Nima, both of you. I think my comment is related to perhaps to what Nima touched upon in his review. That is, it's a golden opportunity for string theory. And particle physics question is not by any means abandoned by a portion of string theory or in swampland questions. In fact, a lot of questions that are arising in swampland directly bear on particle physics. So I think it has actually, I think it's a shift of paradigm for particle physics. Namely, particle physics was pushed to these questions like hierarchy problem or naturalness questions and all this because the view was the quantum gravity is decoupled from these kind of questions. The UV and IR are decoupled. You just talk about whatever you want. Why don't we have this? Why do we have this so small? What is that relation? Without talking in the gravity in the mix. So string theory actually is saying you cannot do that. You cannot, the prior in seeing what is natural or not, cannot ignore the fact that gravity is part of the mix. And so with that being part of the mix, some natural questions will be very different. Naturalness, the prior for the questions of what is natural or not will be on the prior of what includes gravity as part of that mix. Just to give you an example, just applying the weak gravity conjecture, for example, to de Sitter space was recently led to this result of Festina-Lante that Montero, Van Riet, and Wencken discussed, which gives you an interesting relation between the mass of the electron and the dark energy. Basically, roughly speaking, it predicts not a Schatten result for the mass of the electron, but for example, suppose you measure the mass of the electron, it predicts the dark energy should be less than 10 to the minus 89 in fundamental units. Now, it is not 10 to the minus 120, but goes some ways towards closing the gap. So there are these kind of ideas which actually give you suggestions that ideas from what appears to be unnatural is actually connected to other piece of particles. And so I think there's a deep golden opportunity for this for particle physics, actually. So
I don't know if Volodya was waving or if he was just no here.
I was not waving, but I have some question in mind to Lance. Yeah. In your opinion, actually, what is the opinion of phenomenological physicists of the state of lattice QCD calculations? Are they satisfied with it? Is it enough for their for the comparison with experiment, or they are longing for better methods? And isn't it our debt
Are you talking specifically about the mu1 G-2 or more generally?
Not just generally, computations on lattice. Once I was on a seminar of lattice gauge theorists at CERN, I was amazed by the complexity of their methods, how they glue together the perturbative results and then non-perturbative from the lattice. I found it somehow theoretically not very satisfactory. Isn't it our bet with respect to the phenomenologists to invent a better method?
So let me just say I'm not a lattice gauge theorist, but I follow it a little bit from a distance. But I would say that lattice gauge theory is really improving a lot these days. It's always been a series of extrapolations because you have to extrapolate to zero lattice spacing, to infinite lattice size, to physical quark masses. Well, actually, that last extrapolation, they pretty much can run with physical quark masses now. So that's really great. But there's still a lot of studies that they do about the chiral limit to help understand things better. So
so they don't need our help.
I think they, like most people, need to confront each other. So like we have the situation with the mu1 G-2 where there's one collaboration that has much smaller error bars. And there's going to be a healthy, confrontation of that number as future other collaborations try to bring their error bars down too. One thing I didn't mention is that they can actually compare intermediate results that are not exactly the mu1 G-2, but they are easier to calculate on the lattice. So they can check very consistent things. And these things can also be computed using the dispersion relation approach, using the data. So you can actually get a more crisp confrontation between the dispersive approach and the lattice for an auxiliary quantity, which is not exactly G-2. So I think we're going to see some big advances on that in the next couple of years.
If I can add something, I think ironically, Volodya, I would say that, of course, indeed, right now, what dominates the error, for example, for the hadronic contribution of G-2 on the lattice is indeed the extrapolation to the continuum limit. But I think where there's actually room for people from the outside who might want to invest some time to think about it is actually trying to look to see what might be going on in the dispersive calculation. Because we're really in a bizarre place where for years people needed this Euclidean two-point function to shove into the loop correction to G-2. And because we couldn't do it on the lattice, we had to use dispersion relations to do the opposite of what we normally do, which is to use Lorentzian data in order to make a prediction for a Euclidean object. It's not as simple as saying, oh, thank goodness the lattice comes along, they must be right, because there's so many cross-checks on the dispersive calculation that it's very hard to see where there could really be something wrong. I mean, unless there are some experimental error bars that are underestimated by a factor of 2 or 3. So I really think there is room maybe for people outside the collaboration of 100 theorists who have worked on this for 5 years to maybe come in with a fresh set of eyes and just look at the whole thing again to try to understand what's going on. Because I suspect that if the lattice groups, as I'm guessing, are going to start converging on the BMW value with the smaller error bars, which is what all the rumors are that I'm hearing, then there's really going to be a fight. Who's right? Anyone can complain about the systematic error bars on the other guy's side. And so it'll be really important to have a physical understanding of what the hell is going on. And I think it's a beautiful, if messy, physics problem.
Thanks. Fernando?
Good. Okay.
You're muted for now. Oh, there.
Yes. Okay. Yes. Hey. Well, thank you, Lance and Nima, for such a stimulating talk, and the organizers also for raising this issue as part of the program, which I think is very important. So I think that I agree with this spirit that there should be more people worry about particle physics questions from string theory, and more phenomenologists worry about the string theory developments. So that's one of the things that I welcome from the Swampland program, is that to make clear for the people from who are just doing effective field theory that there should be some. I mean, that's not enough. So in that sense, that's good. So I just wanted to add a couple of things. One is about the future experiments. One of at the moment, I will say actions are an important thing that should be taken into account. I think it's there's so many searches for actions, and the gap is being closed, and I think that's one of the big things that can be discovered in the next few years, relatively. And I think that should be also very important for string theory, which it breaks so many actions and so on. So that's one point. The other point, I mentioned it during the cosmology discussion, but I guess many people were not there. And I find very fascinating, I think, that the fact that we can explore gravitational waves of high frequency. And so the higher the frequency, the higher the energy you can probe. And you go from megahertz to gigahertz, you cover up to the God scale. And there has been very little effort in that direction. And I think it's a great opportunity to actually push for that. There's something, of course, there is the higher the frequency, also is the higher the sensitivity. That's the problem, of course. But of course, the challenge we have is a few orders of magnitude compared to what can be seen, and is far better than the situation that LIGO had 40 years ago. So if we can start making an effort in that direction, I think that will be a big success, I mean, for the future, big program for the future. So I wanted just to advertise, we have, as Nima says, it's good to talk to experimentalists. I did, after getting to my old age, I finally wrote my first paper with experimentalists. We have this white paper on this gravitational waves of high frequency. So it is in the archives. It appeared in November last year, with setting up all the potential sources and the current efforts that people have made just individually. I mean, the important thing here is that also the higher the frequency, the smaller the device you have to find. So it will be, you are talking about things of the order 1 centimeter. You don't have to go to space or big accelerators to get there. So you just need precision. And the people who have been working on this, they have been doing it without any funding, essentially. Just so in that sense, the room for improvement is huge. So it's something that I just wanted to point out.
Hey, Fernando, that's very interesting. Maybe you can elaborate slightly. I mean, there are other methods for doing mid-frequency, which are atomic interferometry. I don't know if that's part of the things you talk about for high frequency, or if they're more mechanical.
Right. Mm-hmm. So yes, definitely.
It's more atomic atoms, or
atomic superconductors. Also, there are several
superconductors.
Right.
Yeah.
Yeah. So there are 4 or 5 proposals. They're all, and people just working, 2 people in the lab with without anybody, essentially. So I think there's plenty of room there to explore. And I think that you can test preheating after inflation. You can say cosmic strings or oscillons after fields oscillate. And so there's so many things that can be explored. And that's the difference. I mean, you have to take advantage of what the gravitational waves are.
Not sure if Gabriela is waving. Last time he was.
Not waving, but I'm ready to make a comment.
If not waving, then let's go first to Irene and then to Gabriela.
Okay, thank you. I have a question relating these naturalness issues, because I mean, at least personally, this is one of the things that I find more exciting to try to explain from string theory, whether we can try to change this idea of the quantum corrections to the Higgs wave and so on. And I Nima, I found very interesting this Atkin-Lennard symmetry that you mentioned, that comes from some years ago in the string theory. And I know there are also examples of misaligned supersymmetry that also change a bit these ideas, because some of the orders of the super trace.
Example, I should mention also Eric Poppets had an interesting example that I've not understood of Fi terms, n equals 1 Fi terms that have no reason not to be generated, but are not generated at one loop and therefore not generated at any loop order.
Okay, my question is precisely
a couple of examples.
Yeah, my question is like if people here, like, what are the examples? If we have more examples of this, I mean, do we know more examples in string theory in which, when computing the quantum corrections, to some observable, we are not going to have this quadratic divergence? Or I mean, the intuition is, I mean, it's going to change in addition to this Atkin-Lennard symmetry.
Yeah, well, I think there are these examples that there's Greg's example, there's misaligned Susie that I think is not, well, anyway, might be related. And there's this example of puppets of FI terms that are that should be generated with a quadratically divergently generated proportional to m string squared, but are not. Those are the examples in string theory. And then there's this recent G-2 example. And those are all the examples that I know.
I guess the Susie examples are maybe different from the other ones because you sometimes have non-renormalizable theories. I mean, you just have to get one thing right.
Right.
Whereas in a non-Susie case like Atkin-Lehner, maybe you have to get many things right to get many orders of magnitude suppression.
What's fascinating about the Atkin-Lehner case is that if you don't see the total derivative structure, it really looks like a miraculous cancellation between the field theory contribution and the stringy contribution, but there's a good underlying reason for it. In that case, there's a good underlying symmetry reason, and there's a sort of more mundane mechanical reason for it. And it would be, I think, interesting to find more examples, either mundane mechanical or symmetry based for this kind of phenomenon. In this G-2 example I mentioned, we only have the mundane mechanical understanding. There's no analog of the symmetry understanding. It's such a stupid example that I doubt that there's no way something as fancy as an extension of modular invariance has anything to do with it. But it shows that it can happen. And I think it would be interesting to find more examples of this phenomenon.
Mm-hmm. Maybe it is worth, because I'm sure some people might not know what this this effect is. Can you say in a few words for the non-experts what this effect is?
Atkin-Lehner symmetry.
Yeah. Oh, yeah. Go ahead, Lance. If you
want to say you go, Nima.
Yeah, I mean, I don't know if Greg is on. He could explain it better himself. But Greg had gave an interpretation of the vacuum energy, the one-loop vacuum energy, in this non-supersymmetric compactification of string theory to 2 dimensions as an overlap between 2 states, and to use that interpretation to say that if we had that there might be a good reason why the 2 states are orthogonal to each other, based on this extension of this Atkin-Lehner extension of modular invariance. I don't understand the details at all, but that was the sort of basic slogan, is that there's a good reason why the computation is interpreted as an overlap, and so there might be a good reason why states are orthogonal to each other based on symmetry. The mechanical reason is very simple. I can give you very simple examples, but probably you don't want to give me time to write something down. But let me just say that the sort of basic mechanism is really simple. I can show you a trivial, like a toy integral that illustrates the idea that you can have an integral that looks like it gives some finite non-zero answer associated with some scale. Right, just looking like it cuts off the anyway, a typical kind of integral with a scale that gives you some answer. But you can actually modify the integrand by an arbitrarily tiny amount that shows up at arbitrarily high energies, but which discontinuously changes the answer to 0. And the secret reason for it is that the integrand is actually a total derivative. And so, roughly speaking, it's like a total derivative of something that looks like x over 1 plus alpha x, where alpha is some parameter. And so, if you literally take that expression, it vanishes at 0, and at infinity, it gives you 1 over alpha. But if to the denominator of the total derivative, you just add plus epsilon x squared for an arbitrarily tiny epsilon, then it changes the behavior at infinity, and you get 0. So that shows that it's possible to have arbitrarily tiny modifications that discontinuously change the answer. And then we can go, but it's really because mechanically the object that you're integrating is actually a total derivative. Now, that example looks really stupid, but analogs of this are the explanation, or the mechanical explanation for Greg's example, or the mechanical explanation for this G-2 example, and you can interpret it in less stupid ways. For example, you can interpret the example that I just gave you, not by changing the integrand, but by changing the contour of integration from an open to a closed contour. So there are toy examples of this phenomenon, and the phenomenon has been seen in string theory and now been seen in some field theoretic examples. Maybe it's just a curiosity, but there are really concrete examples of some kind of UVIR conspiracy that actually completely cancels the dominant contributions to something that you care about, and definitely what violates Wilsonian naturals.
Thank you. And by the way, Leonardo posted on the chat the link to Greg's paper that could be helpful for some people as well. Gabriele?
Yeah. Well, first of all, I sympathize very much with what Nima has been saying. In fact, I remember we discussed this in Lausanne a few years ago, and this idea of an infrared ultraviolet connection, it's very intriguing and very interesting. Maybe related also to what Nati was telling us about IR, UV mixing. I don't know. But okay, no, I had a different remark to make. I think a very, very specific feature of string theory, which differs from QFT, is this fact that all the parameters are promoted to fields. We have all these scalar fields moduli around. And I think on one hand, these are dangerous, okay, because we know there are no long-range forces associated with these particles. But on the other hand, there can also be a very big opportunity. You may see small effects. I mean, if these fields are sufficiently light, we heard that they may even play a role for dark matter, this fuzzy dark matter, but also they can produce some longish range forces, or you can have some tiny variation of some constants. This will all be very interesting and phenomenological implication of string theory that really will make it very much more appealing, okay, if one could see something. And let me add something else. Either you stabilize the moduli or you don't. If you don't stabilize the moduli at all, you have these long-range forces that kill you. If you stabilize the moduli, in principle, you have predictions. You could predict alpha. If one day string theory would give you alpha, I think you'll convince everybody. That's my remark.
Just a tiny comment, Gabrielle. Also, I wanted to say, after Fernando mentioned it, this is something I think everyone knows, but it's worth repeating. One of the amazing things if axions were discovered, especially axion dark matter, is it would give us the first absolutely concrete, experimentally verified example of a coupling constant not being a constant, but being a modulus. And especially if we see it as dark matter, even the ways of detecting them, many ways of detecting them are looking for variations of a constant. And I think that's the gateway drug to the entire world of all coupling constants being a moduli. Of course, that's a deep reason why axions are so ubiquitous in string theory, precisely because coupling constants are a moduli. And just accidentally, these are the ones that happen to have a good reason for being light. Yes, indeed, I agree with what you said, especially looking for long-range forces. There are some tensions sometimes with the moduli problem. They're not insurmountable, but in any case, it's definitely worth continuing to look for these long-range forces associated with all sorts of moduli, not just axions. Which specifically don't give rise to particularly large long-range forces. But anyway,
let's go to Fernando, who is waving.
Okay. Yes. No, thank you, Gabriele. I would say it's nice to see you, but I cannot see you. But it's good
because maybe I'm sitting against the.
You were dark matter,
right,
Gabriela.
Perfect.
Very good. Very good. That's good. No, I think it's a very good point. But I mean, usually this moduli, once you stabilize the moduli, they tend to get a mass of the order of the gravitational mass, more or less. So a bit lighter or a bit heavier, but in that range. So if the gravitational mass is heavier than the FUTEV, then they are also heavy. But in that, they can play an important role. So as Nima said, there was this cosmological moduli problem, but if they are heavier than 30 TeV, there is no problem, and then they can dominate the energy density of the universe and so on. So in that, it's an indirect way to say that somehow string theory didn't want the scale of supersymmetry breaking to be too low because the moduli were pushing it to be heavier than 30 TeV, otherwise it would cause the universe. But they can also play an important role because precisely because they can dominate the energy density of the universe at some point. It changes the whole paradigm of just going from inflation to radiation domination. You can go from that to modular domination, part of the history of the universe. And after the last modulus decays, then you have the standard reheating and so it changes the picture of the history of the universe after the inflation. So I think I agree with you. They are the remnants of string theory, if even that the inflation cannot erase. So I think it's important always to keep an eye on them because they can have an important physical role.
No, just to very quickly clarify, there are two ranges of moduli we could be talking about. Quite light ones at around the sort of millimeter scale, a little bit heavier, that might be there if you had very low scale, comparatively low scale SUSY breaking. I think those are the ones maybe Gabrielle was imagining associated with long range forces. And the ones that you were talking about that are very naturally heavier than 30 or 100 TeV, not for overclosing the universe, but for not screwing up BBN through their decays,
also, right,
through their
exactly.
late decays. Yeah.
Right.
I think a great question is also, if you see one of these, how do you know it's a scalar or a pseudoscalar? Sometimes it comes with a tag if it's a E dot B or FF dual interaction. It says pseudo, but not always.
Right. The pseudoscalars, in that sense, thank you for the comment. The pseudoscalars can be much lighter. For instance, because once they are axions, so then you can have the mass can be e to the minus the volume or something, and the volume very large. So the pseudoscalars can be even the 10 to the minus 20 electron volts or so. Yes, but if they're scalars, then they have to be heavy. Yeah.
And also, you notice by whether they're giving you spin-independent long-range forces or not. So spin-independent long-range forces only come from scalars. Of course, even the axion is a little bit of a scalar down to almost the 10 to the minus 10 level. But the long-range force that mediated by axions, because of the theta QCD suppression, is really small. But anyway, that's the most invariant thing is, do you actually see a spin-independent long-range force if they're light?
Let's move to Miguel.
Yeah, I just wanted to quickly come back to one of Nima's challenges, the SU 2021 to 2021.
Yes.
In 9 dimensions. So I think that the status of that is really strongly dependent on whether we are assuming supersymmetry or not. If we have supersymmetry, I think there's by now a couple arguments that very strongly suggest that this thing is probably in the Swampland. So for instance, there was this paper by Kim, Tarasi, and Bafa, where they showed that if you had a theory with such a large gauge group, it would be inconsistent with. So they put an upper bound on the rank that you can have, which is 26 minus the in D dimensions for n equals 4 theories. So theories with 16 supercharges, and that's the minimum you can have in 9 dimensions, right? So
what about n equals 1? What about minimal SUSY? Yeah.
No, but that's what I mean. N equals 1 is, sorry. When
I say
minimal
4,
I mean 4 dimensions. Right. So in D dimensions, right? That's the minimum supersymmetry you can have. Right. So they say that if you have something like that, it would be pretty much in contradiction with T-duality and the Swampland distance conjecture, which is one of the best established ones. And there was also a recent paper by Kumrum and Yuta Hamada, where they studied a similar setup in 8 dimensions, and they showed that by studying the moduli space of probe brains, you can argue that you can also recover a lot of the structure of the moduli space that we see. So I think that with supersymmetry, because you have so much supersymmetry in 9 dimensions, we're actually pretty close to establishing many of these things just coming from like general principles like global symmetries or completeness of the spectrum. And without supersymmetry, of course, it's
no. I would even be happy with SUSY for that question.
Right.
Sandeep?
Yeah, thanks, Pedro. Just to come back to supersymmetry at the weak scale, I was trying to ask Lance that in the chat. Of course, you might be interested in SUSY for various reasons, but just in terms of the hierarchy problem, at what point do you think, let's say, if supersymmetry continues not to be found at the weak scale at the LHC, at what point do you feel it no longer remains viable at all as a solution to the hierarchy problem? Or have we reached there already?
Let me say the following about that. I know we don't have a lot of time, but I'll try to be brief. Of course, there's no really invariant answer to this question.
I know that. I know.
Except that when naturalness has worked in a big way before, it worked 3 times in a big way in the last century. every time it worked before, the characteristic is that people never had this stupid argument of, is 10% tuning okay? I don't know. How many things did you look at? Look elsewhere effects, stupid statistical arguments, Bayesian this, frequent this, that, all this crap. They didn't have that kind of discussion because it worked in a big way. You know, naturalness worked in a big way for the problem of the self-energy of the electron. And when it works in a big way, you know it works in a big way because the corrections are parametrically small compared to the quantity that you talk about. That's why no one had to have these dumb arguments. In the case of the mass of the electron, in the case of the charge pi plus pi zero mass splitting, which was another famous example where a hierarchy problem like arguments gave the correct answer, and for the prediction of the charm quark, from the quadratically divergent contribution to KK bar mixing. All those were examples where the new physics came in earlier than it had to, and there was a good reason for it. Okay, that ultimately the underlying theory had a small parameter, at least in the first two examples, had a small parameter that explained that. So, and from this point of view, it's not the LHC that put us in this situation. Already from LAP in anyone paying attention to the data would not have been saying in the year 1999, oh, for sure, the LHC is going to discover SUSY, for sure, no doubt. Anyone paying attention, close attention to the data would not have been saying that in the year 1999. Because already by then, this was supposed to be a theory of the weak scale of the W and the Z particles, which are at 80 and 90 GeV, not at a TeV. Okay, and already in the year 1999, everyone's favorite supersymmetric model had squarks at the TeV scale. So there was an early indication that the classic way naturalness has always worked out in a big way before was not working out this time for the case of SUSY and the hierarchy problem, indeed any natural solution of the hierarchy problem. But that being said, I want to stress, what is the magnitude of disaster we're talking about? You know, the stops would have to be at 500 GeV in order for things to be fine. The limits now are like at best 1.5 TeV. So we're off by a factor of 3. Okay, so it's not some like, oh my gosh, it's now dead by 10 orders of magnitude. You know, all of this drama is that they're 3 times later coming in than you would have expected them to be from a naturalness. But I think the qualitative differences is that now we're talking about how much tuned it is or not, if it's good or bad, and so on. For this, all I can say is that there is something a little bit invariant, at least to my thinking, about the percent level of tuning, which is roughly the neighborhood that we're in now. And that has to do with the fact that we've actually seen elsewhere in physics, one energy scale down in nuclear physics, we've seen percent level tunings in nuclear physics. And not only that, those percent level tunings seem somehow related to electroweak symmetry breaking. So they might not be unrelated to the percent level tuning that we're seeing with the Higgs. And if you've ever tried to understand nuclear physics as a graduate student, you've noticed that it's a complicated subject. You know, 2 neutrons are not bound, but a neutron and a proton is bound. What the hell is going on? What the hell is going on is that it's a fine-tuned system, and that there's a delicate cancellation between the kinetic and potential energies of the neutron-proton system that don't quite work for the neutron-neutron system. So for example, 2 neutrons fail to be bound by 60 keV. It's absurd. It's like all the scales in the problem are an MeV, and yet 2 neutrons are almost bound, but not bound by 60 keV. Normally, nuclear physicists talk about that in language of the nuclear scattering length, which is again much larger than you'd expect from the ordinary from the scales of nuclear physics. So we've seen accidents at the percent level. Of course, there are joke accidents, like the moon eclipses the sun is a percent level accident, but that's kind of a joke. This thing about nuclear physics is not really a joke, because these parameters plausibly depend on up and down quark masses, which are some things that are controlled by electroweak symmetry breaking and not by the glory of pure QCD. So I would say that we have evidence of some kind of percent level tuning involving quantities that care about electroweak symmetry breaking. And so that's about where we are now with the LHC. We're not even quite at the percent level yet, but in that neighborhood. So I think, you know, another order of magnitude, taking it to a part in 10,000, would now be a degree of tuning that we have not seen elsewhere in particle physics. But anyway, I would say there is no really invariant answer to your question, other than to say that the real bridge that was crossed was not with the LHC, but was with LEP. and was the fact that Susie was not discovered at left. That's when we knew already that the story was not like previous times that naturalness has worked before, and we have to have these stupid discussions about what is and isn't true.
So just to make the point that the LHC run is not, in the future, is not going to increase the energy more than 13 to 14. It's going to increase the luminosity a lot, but it doesn't increase your mass reach by very much for the heaviest objects, because the parton distributions fall very fast. And so if you increase the mass of a stop by a little bit near the bound, the rate goes down by a lot.
Yeah.
I mean, there may be more prospects for being clever about digging out lighter electroweak particles. They're not produced as often, and so you have to be a lot more careful. And this could be a place where machine learning and clever theory techniques could come in.
But just so you have a rough idea, the sort of the mass scale that we know now for electroweak charged particles at the LHC is maybe 500, 600, 700 GeV. Those are the kind of limits that we're talking about. The ultimate reach on gluinos will be 2.5 to 3 TeV. Okay, so there is this sort of famous factor of 5, 6 between the colored and the uncolored particles. And just to stress what Lance was saying, the reason energy matters so damn much at hadron colliders is that at a fixed mass, the rate for producing particles falls roughly like 1/4 mass to the 4th to 1/4 mass to the 5th, or going the other way, pumping up the energy, it increases like the 5th power of the center of mass energy of the machine. So that's why even a factor of 2 in energy is a humongous deal for reach. And after you're done with the energy, just collecting luminosity, it's a harder game. The kind of reach that you have scales roughly like the 4th root of the luminosity if you're doing standard statistical sort of searches for new physics.
I see. No, thanks a lot. I won't take up more time, but just to summarize then, I gather it's, let's say if it's a 1 part in 100 tune, it's not going to get so much better data-wise with more luminosity, roughly, because you won't probe the higher mass part.
I think that's
so
right.
we'll be stuck with this kind of number. Okay.
Or we might see it. I mean, we still might see it. That's the other point. I mean, that if your attitude is, well, already at a percent, it's tuned, therefore it's up at the Planck scale, that's not necessarily correct. And indeed, we've seen similar accidents lower down in nuclear.
Thank you very much, both of you.
Thank you. We have a ton of people online and a ton of cameras on, so we should definitely continue informally, but we should also, I think, maybe now stop the more formal and part of this discussion and thank Lance and Nima. And of course, whoever wants to go can go, but as long as we have people interested, I think we can take advantage of Lance and Nima and bombard them with more questions.
Happy to
So
stick
don't be
around if
shy,
there are more
especially
questions.
if you haven't participated yet, take advantage.
Can I follow up with the Nima's point?
Sure.
Just a question. Nima, so what would you were preferring this mini split or something that where the gluinos are relatively light. How do you compare that with just high energy associated breaking with everybody too heavy?
Well, I mean, I think you lose gauge coupling unification. I think that to me, what's special about split is that it's the only picture of the world I know where all of the clues, theoretical and experimental, from the past 40 years have a purpose in life. Okay, none of them were wrong. And you know, as you know very well, the attention about naturalness was never that theorists were like, oh, because Ken Wilson, we worship him like a god, we believe in naturalness, and we never question naturalness. Any idiot could and did question naturalness, especially because of the cosmological constant. We all knew there was something funny with the cosmological constant. But the reason for taking it seriously is that it bought you something concrete. And so people believed, I certainly believed, that the choice was between naturalness, which means something like Susie and unification and dark matter, or not naturalness and the standard model. And then if you took the standard model all the way up to the high scale, then why the hell did everything seem to be falling your lap with the gauge coupling unification and WIMP dark matter and so on? To me, what the revelation of split Susie was that you could have your cake and eat it too in a fine-tuned version of supersymmetry. And it would seem crazy to talk about a fine-tuned version of supersymmetry. And people yelled at me at conferences when I talked about this. Not you, but many other people yelled at me at conferences when I talked about this, because there was this heretical thing of talking about a fine-tuned version of SUSY, except of course, everyone was already talking about a fine-tuned version of SUSY for the cosmological constant. So, and from the top down, as you know very well, it's very easy to get this spectrum. That's a spectrum people got from the earliest days of SUSY breaking, because it's easier to give the scalars a mass than the gauginos a mass. So anyway, that is my attitude. I think we know so little about the distribution of vacuum on the landscape and how to think about the whole thing. I'm going to punt on that entire problem, other than to say that it makes it possible to imagine that we'll see something that looks peculiar from the standard naturalness point of view. It's definitely true that mini-split SUSY is an intermediate possibility. It's not like, oh, no SUSY until the Planck scale, or a perfectly natural thing. It's a weird intermediate possibility, but I think it's a kind of weird intermediate possibility that at least you can imagine might arise in the landscape plausibly, and it makes experimental predictions that are not wrong. I mean, that's so that's why I think I like it.
But will they never be wrong, Nima?
No, they'll definitely be wrong, because
okay, never. I mean, by the end of the high luminosity LHC.
Oh, right, yeah. That I mean, from unfortunately, and you know, this was said early on, even before the LHC, in kind of half the parameter space of the theory. It really depends on how dark matter works. In half the parameter space, the gauginos would be light enough to see at the LHC. In half the parameter space, they would not. In fact, in the simpler part, in the less Baroque part, if the bottom of the spectrum is a 1 TeV Higgsino or a 3 TeV Wino, you're not going to see the particles at the LHC. But you will definitely see them at 100 TeV collider. I mean, you cannot punt on them forever. So that's why, I mean, it's possible the LHC will see the gluino. I don't think it's very likely. It's possible. But that's why I talked about working out. I mean, I think if I work out enough, I might live to see the gauginos discovered at 100 TeV collider. I expect I will.
Don't violate our parity.
Yeah, right.
Daniel?
Yeah, hi. I'm curious, is the recording off now, or the email?
No, the recording is still on. The recording is still on.
Fuck you, Harlow.
Well, maybe I'll ask anyway. And Lance and Nima are both people I admire, so I'm curious to hear. So some people think that our field is in trouble. I'm actually not one of them. I feel like things are going well. I'm having a lot of fun. I see lots of interesting stuff going on, but surely you have heard the arguments, and I'm curious, do you think that we are in trouble? Is the field worse off now than it was 30 years ago, say, or is it better off? Yeah, what do you think?
Nima's an optimist.
Yeah, I'm not a doomsayer.
I'm not quite as optimistic as Nima.
But actually, but Daniel, I would say a general thing I'd say about this is I hate any discussion of the field as a big whole thing. I don't think about the field or the community. I don't believe in communities or fields per se. I believe in a large collection of individuals doing their own thing. And that's the real way physics has made progress for a long time. I really dislike these communal things. They tend to get mediocre and incrementalist, and I just don't like them. And so from that point of view, I don't see any difference. I mean, you know, physics is always hard. Sometimes it's easier, sometimes you have more clues, sometimes you have less clues. But I think so long as people are doing things honestly, not fooling themselves and not fooling their friends, and just working hard, then that's the best we can do at any time. Sometimes things are easier, and sometimes things take decades and centuries to work out. It's not up to you when you're born. If you're attracted to this subject, if you love trying to understand the world, you do the best you can with whatever you've been given in whatever time you're in. And so, yeah, I'm not one of these doomsayers at all. It's what I do think is true is that it is important, if we don't have experiment to like beat us over the head, it's important to kind of it's important to sort of check ourselves more often. See, are we fooling ourselves? You know, are we just like 20 people who are agreeing that some subject is cool because we're talking to each other all the time, but somehow, you know, I mean, I'm not saying there's anything wrong with that, but every now and then stop and say, you know, if I wasn't in this like club of cool kids working on this thing with 20 other people, and I zoomed out, would I actually care about it? Does it connect to things that I actually really care about the way the world works? If the answer to the question is yes, then fantastic. If it's no, you should stop what you're doing and do something else. Yeah, I don't see any problem with the collection of individuals that we have, and to the extent that they constitute a field, I don't see any problem with the field. But maybe Lance.
Yeah, well, the questions that we're all asking are extremely interesting. The question for me is, we do need some more guideposts from experiment, and they're slow in coming in. And the longer that waits, the slower the sort of progress in getting the clues to the next step. I think it's a bit of a problem. I mean, I had a student who was very good. He went into machine learning because, well, he told me the pace of development in physics seemed a lot slower. So I think it's going to be, it'll be an issue for things overall. Doesn't mean there aren't interesting questions. It means we have to think more about how to get to the answers.
Let me call David. Yeah.
So speaking of the 100 TeV colliders, I'm wondering what is the progress of that at the moment. Nima, I read an article a while back that there's one being constructed in Beijing, and you and David Gross had some funding to do with that. Wondering whatever happened to that.
Well, unless David came into $10 million recently, I'm not sure. You may well have. No, that there's nothing under construction anywhere. It's being considered seriously in China. It's being considered seriously at CERN. Absolutely no guarantees of any sort right now. At least both efforts are ongoing. The effort in China is not focused right now on the 100 TeV collider. It's focused on getting a 100-kilometer tunnel to build the E+E- Higgs factory, which will not cost $20 or $30 billion, but it'll cost around $5 billion. Yeah, they're doing R&D. I have to say they're doing a fantastic job. They've grown the size of their community there significantly over the past 5 years. They put together a truly first-rate conceptual design report. They're working on a technical design report, and COVID interrupted all large-scale scientific funding in China. But when it turns back on, there was a call in from major proposals, experimental proposals, and this is one of the clear candidates for getting funded there.
By the way, these design reports are for the electron-positron machine, right? But yeah, it enables the tunnel that you would put the proton machine in later.
That's right. That's right. From my point of view, I just want to see a 100-kilometer tunnel built somewhere on the planet. Then I can die happy, or at least go to the gym and then die happy. But yeah.
Thank you.
Nima likes circles. Some people like lines. We know they're conformally equivalent, but not in the real world. It makes a big difference.
But sorry if I can just butt in and then you can turn me off, Pedro. Talking about circles and lines, aren't they all really pyramids in the sense, this accelerator technology has been around. We've harnessed it now to its near maximum level. And that's the reason why the data is drying up. So where I'm going is, do you all know about exciting developments, ideas in wake field acceleration, lasers, and so on? Because in the string community, that's the kind of thing we don't hear about because we don't hang out with experimentalists, as Nima says. But are there interesting ideas out there which you might say?
I'm at a lab that does some of this high gradient research with plasma wake field driven and has some arms in lasers. Other labs also do a lot of laser acceleration. So it's sort of one thing to get a very high gradient for a short distance. And it's another thing to stage many of these things together, because often you have to bring in a laser beam and now you have to get it in along with the output of the previous section. And it's very tricky to do the staging, and it hasn't really, I don't think, people are trying to work on the fundamentals of getting the highest gradients possible. But then there are many more, huge tasks. I mean, some of them might just be engineering in some sense, but others are really fundamental issues that haven't been solved yet to make a working device. In other words, you need high energy and you also need high luminosity. And when you have a linear collider, which is what these high gradient things are usually focused on, means you have to have lots of particles in a small area. It's not enough just to have a few particles or to have them come out spraying out at a big angle.
And another just thing to add to it is that it's likely that when these things work, when they start really work to begin with, they won't immediately go from, forget accelerators to now we're going to have like, a 10 times bigger LHC in a football field with plasma wake field accelerators. The most likely thing they'll be used for is as afterburners on linear colliders first. So, you go through a normal linear collider and you add these plasma wake fields at the very end to just give you some extra oomph. That's very likely the way that they'll actually develop. The other theoretical thing to say about it is that the issues are about plasma instabilities. These are exponential instabilities that are not so dissimilar with the problems with fusion. So you need an idea to improve it significantly. When you're fighting an exponential, you can work very hard to improve the prefactor, but much better is to get into the exponents and to figure out something to do about the exponent.
Flatten the curve.
Flatten the curve, exactly. Yes. Flatten the curve.
Thank you.
All right, guys. I would love to sit and hang out longer, but as I was telling Lance earlier, my life has been an absolute chaos of mess over the past 10 days, and I have to go to the Department of Motor Vehicles, which gives you an idea of how terrible it has actually been. So many, many apologies, but I actually have to take off. Okay.
No, I was actually going to suggest that we thank you once more. So let's thank Nima and Lance once more and conclude the session.